אוקיי, רואים את המסך שלי?
כן, רואים.
טוב, אחלה, אז שלום לכולם, שמי גיא טננהולץ, אני אציג לכם כאן איזשהו טוטוריאל זריז על Offline Reinforcement Learning. בואו קצת רקע על Reinforcement Learning, כמובן אני אעשה את זה ממש קצר, כי אני כן רוצה להגיע לפרטים של Offline RL, אז כמובן כולכם בטח שמעתם על כל ההצלחות של Reinforcement Learning, ומשחקים, ו-Go, וכל הדברים ברובוטיקה. מה יש לנו ב-Reinforcement Learning? יש לנו סוכן וסביבה, נכון? הסוכן עושה אינטראקציות עם הסביבה, לוקח פעולות בסביבה, הסביבה עוברת בין מצבים לפי הסתברות מעבר, בהתאם לפעולה שהסוכן לקח בסביבה, ומחזירה לסוכן אובזרבציה ופרס, וככה חוזר חלילה, הסוכן לוקח עוד פעולה בסביבה, מקבל עוד פעם פרס ואובזרבציה, ומטרתו כמובן למקסם את הפרסים שהוא מקבל מהסביבה. באופן כללי, מודל מאוד כללי שאפשר להתייחס אליו, זה partially observable Markov Decision Process, POMDP, שמוגדר על ידי מרחב מצבים, מרחב אובזרבציות, מרחב פעולות, פונקציה סקלרית של פרסים, פונקציית מעבר בין מצבים, ופונקציות אובזרבציות, שכמובן כשמרחב המצבים שבין מרחב האובזרבציות, אז יש לנו MDP, ועכשיו אנחנו בהרצאה הזאת כאן בטוטוריאל כאן אנחנו נתייחס ל-MDP, אבל אני כן אגיד כמה מילים גם על POMDPs בהקשר של אופליין RL. עוד קצת נוטציות, אז מדיניות יכולה באופן כללי גם להיות תלויה בזמן, תלויה בהיסטוריה, לצורך העניין אנחנו חושבים כאן על מדיניות שהיא פונקציה של המצב הנוכחי בלבד, בוחרת פעולות, יכולה להיות סטוכסטית, יכולה להיות דטרמיניסטית, יש איזשהו דיסקאונט פקטור, מספר בין 0 ל-1, ואנחנו מגדירים את ה-value להיות הסכום של הפרסים שהוא דיסקאונטד עם הגמא הזה, עד איזשהו horizon h, אפשר גם לקחת את הגבול לאינסוף אם אנחנו רוצים להסתכל על infinite horizon, יש לנו כמובן גם את ה-Q function, שבדומה ל-value, רק שבזמן 0 בסטייט S אני לוקח פעולה A שהיא לאו דווקא משהו שהמדיניות שלי הייתה לוקחת, ומטרתנו ב-Reinforcement Learning זה למצוא את המדיניות האופטימלית שהיא ממקסמת את ה-value. כמה relations נוחים, קודם כל הקשר בין ה-value ל-Q function, הוא בסוף תוכלת על ה-Q function תחת המדיניות שלנו, וכמובן משוואות בלמן שמקשרות בין ה-Q ל-value של המצב הבא או ל-Q הבא, ויש לנו את אופרטור בלמן שככה אנחנו מגדירים אותו. אוקיי, אז זה ממש הרקע בגדול, ממש בדקה, על Reinforcement Learning. אותנו כאן מעניין Offline Reinforcement Learning. בעצם אנחנו רוצים לקשר את ה-RL לשימוש שלו עם Offline Data. אז איך הולך להיווצר הדאטה הזה? אז הדאטה הזה הולך להיווצר בתוך MDP, שהתחלנו, ה-MDP הולך ליצור לנו trajectories, מסלולים, מסלול מתחיל עם איזשהו התחול של איזשהו מצב S0, יש איזושהי מדיניות שהיא לא שלנו, איזושהי מדיניות שאנחנו נוהגים לקרוא לה PI-B, זה Behavior Policy, שבוחרת פעולה A0, מקבלת פרס R0, עוברת למצב הבא, לפי הפונקציית מעברים, שוב בוחרת פעולה, עוברת למצב, מקבלת פרס, עוברת למצב הבא, וכן הלאה. זאת אומרת, אנחנו יוצרים לנו מסלולים כאלה, אז ה-PI-B הזה יצרנו מסלול אחד, יכול יצרנו עוד מסלול ועוד מסלול ועוד מסלול, בסך הכל אנחנו מקבלים איזשהו דאטה סט של מסלולים, של טרנזישנס כאלה שנוצרו על ידי אותה מדיניות PI-B. וזה הדאטה סט שאנחנו רוצים להשתמש בו. מה מטרתנו באופליין RL? המטרה שלנו זה להשתמש בדאטה הזה כדי לפתור את בעיית RL, כדי למקסם את ה-value. עכשיו, למה בכלל מעניין אותנו לעשות את הדבר הזה? למה מעניין אותנו להשתמש בדאטה ולא בכלל פשוט ללכת לעשות אינטראקציות עם העולם האמיתי? אז קודם כל חשוב לזכור שדאטה זה משהו שיש לנו בשפע, בהרבה מאוד בעיות, ואם יש לנו אותו כבר בשפע אין סיבה לא להשתמש בו. דבר שני, לעשות אינטראקציות בעולם האמיתי זה דבר יקר, נכון? ללכת עכשיו ללמוד רכיבה אוטונומית, להוציא רכב, זה אומר שאנחנו צריכים ממש לקנות רכב, לקנות כל הליידרים, את הדברים האלה, לשלם על דלק, על בדאי, וכן הלאה וכן הלאה, זה דבר יקר לנו. סייפטי, נכון? דברים של זה, אם אני עכשיו מוציא רכב לכביש, אני יכול ממש לפגוע בבן אדם אם אני עושה משהו לא נכון, אם בתחום הרפואה, אם אני אתן תרופה לא נכונה לבן אדם, אני יכול גם לפגוע בו או להרוג אותו. אז עדיף להשתמש בדאטה שכבר קיים, שאני לא אצטרך לעשות שטויות. חוץ מזה, דאטה הרבה פעמים, יש לנו ממש אנשים שכבר יודעים לעשות דברים יחסית טובים בדאטה, אפילו אקספרטים שיודעים לעשות את הדבר האופטימלי במקומות מסוימים, אז חבל להתחיל מאפס, חבל לנסות לעשות אקספלורציה סתם, אם אני יכול כבר לנצל את הידע הזה של אנשים אחרים. וכמו שאמרתי, כבר הדאטה הזה קיים לנו בהרבה מאוד דומיינים, עם משחקים, ברפואה, רכבים אוטונומיים וכן הלאה וכן הלאה. עכשיו באופן כללי הייתי רוצה להשתמש בדאטה, ובמקביל גם לעשות אינטראקציות עם העולם האמיתי. בהרצאה הזאת ובכלל ב-Offline Reinforcement Learning, אנחנו מתייחסים לדאטה שהוא סטטי, שכבר נוצר לנו כבר על ידי איזשהו behavior policy לא ידוע, ואנחנו לא מאפשרים יצירה של דאטה חדש, זאת אומרת אנחנו לא מאפשרים אינטראקציה עם העולם האמיתי, כמובן שבאפליקציה אמיתית אנחנו כן נרצה אחרי זה להמשיך לאסוף עוד דאטה ולהמשיך את התהליך הזה, אבל כאן אנחנו מתייחסים לדאטה סטטי שלא ניתן לאסוף עוד דאטה מעולם האמיתי, אז מטרתנו היא בעצם למצוא מדיניות הכי טובה שאנחנו יכולים למצוא בהינתן לדאטה הזה, בהנחה שאנחנו לא הולכים לאסוף עוד דאטה מעולם האמיתי. עכשיו אני כן רוצה לציין שיש כאן קשר מאוד הדוק וקרוב לעוד ספרות ענפה בתחומים אחרים. קודם כל יש את Off Policy Evaluation, ש-Off Policy Evaluation יש מאות מאמרים בנושא הזה, שמדברים על איך אפשר לא למצוא מדיניות יותר טובה, אלא איך אפשר בכלל לשערך את ה-value של מדיניות מסוימת. בהינתן שיש לי את הדאטה הזה שנוצר על ידי מדיניות אחרת, איך אני יכול להגיד מה יהיה ה-value של מדיניות אחרת. אז אפשר לחשוב על זה בתור איזושהי תת בעיה של Offline Reinforcement Learning. בנוסף יש לנו את Off Policy Reinforcement Learning, שזה באיזשהו מקום יש שיגידו שזה אותו דבר. אני מתייחס ל-Off Policy Reinforcement Learning כי ההבדל העיקרי בו זה שזה אלגוריתמים שהם נועדו להשתמש בדאטה שהוא נוצר Off Policy, אבל הם לא אלגוריתמים שמאפשרים עוד איסוף של דאטה חדש. זאת אומרת, Q-Learning הוא אלגוריתם שהוא Off Policy, אבל אלגוריתם שהוא בעצמו אוסף עוד ועוד דאטה. וגם הדאטה שהוא אסף, שהוא היה Off Policy בעבר, זה דאטה שהוא יצר. לעומת זאת, ב-Offline Reinforcement Learning, א', הדאטה שנוצר לדאטה אנחנו יצרנו אותו, וב', אנחנו לא יכולים לאסוף עוד דאטה. זאת אומרת, הדאטה שיש לנו, זה כל הדאטה שהולך להיות לנו, ואנחנו צריכים להיות הכי טובים שאנחנו יכולים בעזרתו. עוד תחום שיש, זה כמובן Imitation Learning, ש-Imitation Learning מדבר על דאטה שנוצר על ידי אקספרט, מישהו שכבר יש לו את המדיניות האופטימלית, אבל אנחנו רק רוצים להיות דומים לאותו אקספרט. ודבר האחרון שיש לנו זה תחום שנקרא Causal Inference, ו-Causal Inference זה קצת נשמע מוזר שהוא קשור ל-Offline Reinforcement Learning, אבל בעצם אני רואה את Causal Inference כנושא שבעצם מדבר על מה אפשר לעשות ב-Offline Reinforcement Learning, כשיש לי partial observability, כלומר כשיש לי מצב שאני לא רואה בדאטה, אבל אותו behavior policy שבחר לי את הפעולות כן ראה חלק מהמצב הזה, ולכן הוא יוצר משהו שקוראים לו confounding. אני לא אכנס כאן לפרטים, אבל אני חושב שזה חשוב לזכור שהנושא הזה של causal inference, ששם בעצם מטפלים בבעיה הזאת, הוא בעצם offline reinforcement learning עם partial observability. אז בואו נתחיל ונדבר קצת על offline RL ולמה הוא בעצם קשה ומה הבעיות שיש. אז בואו נדבר על בעיה אחת. בואו נחשוב כאן על איזשהו setting מאוד פשוט, יש לי state space שהוא singleton, בעיית bandit, אוקיי? ואני מגדיר את ה-reward function בצורה הזאת, R של A זה mu של A ועוד רעש גאוסי עם תוחלת 0. בסדר, ואני רוצה למצוא את הפעולה הכי טובה. נכון, הפעולה הכי טובה זה הפעולה עם התוחלת הכי גבוהה. עכשיו מישהו אסף לי, מישהו שהוא לא אני, איזשהו behavior policy, אסף לי דאטה סט סופי, עם אין דוגמאות, AI, אוקיי? אז מה אני יכול לעשות עכשיו עם הדבר הזה? אז שוב, אמרנו, אם אני אמצא את המיו הכי גדול, אז ניצחתי, נכון? מצאתי את המדיניות הכי טובה. אם היה לי אינסוף דאטה כזה, אז זה לא בעיה, אני יכול לקחת את המשערך הבא, את המשערך האמפירי למיו, ואחרי זה לקחת את המדיניות שתמקסם לי את המשערך האמפירי של מיו, נכון? כאן כמובן יש לי דאטה סופי, אז גם אני אעשה אותו דבר, אני אעשה את הדבר הזה, אני אקח משערך אמפירי למיו, ואני אקח את המדיניות האופטימית, שבעצם הגרידית שלוקחת את ה-argmax על כל הפעולות. אוקיי? עכשיו שימו לב כאן שהמיו כובע הזה, המשערך האמפירי, הוא מתפלא גם עם נורמלי, עם תוחלת מיו, ווריאנס שהולך כמו 1 חלקי כמות הפעמים שהפעולה הזאת יש לי אותה בדאטה. אני גם רוצה לציין גם שמה שאתם רואים כאן, המיו כובע הזה, הוא משחק את התפקיד של ה-Q function, נכון? אם הייתי פותר כאן, האלגוריתם הזה הוא מאוד דומה ל-FQI, או אם תרצו Neural FQI, ששם יש לי מה שיש לי ב-DQN, שאני פותר בעיית רגרסיה ל-Q function, אז בעצם גם כאן זה מה שאני עושה, נכון? אני כותב איזשהו משערך ל-Q, שהוא ה-mu-head שלי, ואז אני גרידי ביחס לזה. ההבדל הוא שאני לא הולך לאסוף עוד דאטה. Okay, אני לא הולך לקחת את המדיניות הזאת, לעדכן את ה-Q ואז לקחת עוד דאטה, זהו, זה המדיניות הסופית שיש לי. עכשיו השאלה כמה המדיניות הזאת טובה. אז שוב, מה המדיניות הזאת? היא מדיניות שהיא אופטימית ביחס למשערך האמפירי שלי למיו כובע. אז בואו נראה מה קורה, מה הסאב-אופטימליות של פאי כובע שלי. סאב-אופטימליות מוגדרת על ידי התוחלת של הריוורד האופטימלי, פחות התוחלת של הריוורד שהייתי מקבל תחת המדיניות שלי. אז כמובן בגלל של הריוורד יש לי רעש אדיטיבי שהוא גאוסי, תוחלת 0, אז זה כמו ההפרש של התוחלות. אני אוסיף ואחסר את המשערך שלי, ואני אקבל כאן שני גורמים. הגורם הראשון הוא משהו אינטרינזי של הסביבה, הוא בעצם מתייחס, התוחלת היא לפי פאי כוכב, נכון? הפאי האופטימלי שלי, זה לא משהו שאני יודע אותו, ובעצם התוחלת הזאת זה משהו שאני יכול לשלוט בו יחסית טוב, אני פשוט מחפש כאן משערך שיהיה כמה שיותר קרוב למיו אמיתי. זה משהו שהוא אינטרינזי, אי ודאות אינטרינזית שיש לי, ואני יכול לטפל בגורם הזה יחסית טוב. הגורם השני הוא הגורם הבעייתי, וכאן יש איזושהי קורלציה בעייתית, כי אני לוקח את התוחלת על מיו כובע, אבל גם התוחלת עצמה היא לפי פאי כובע, שפאי כובע, תזכרו שהוא לוקח את הפעולה האופטימלית לפי מיו כובע. אז יש לי כאן איזו קורלציה בעייתית, והבעיה היא שהגורם הזה הוא יכול להיות יחסית גדול. במיוחד בגלל שפאי כובע לוקח את הארג מקס על מיו כובע. אז בואו נראה את זה גרפית. בואו תזכרו שמיו כובע הוא מתפלג גאוסית עם 1 חלקי כמות הפעמים שהפעולה נראית בדאטה. אז אם זה המצב, אז במקרה הזה, תחשבו שיש לי הרבה מאוד פעולות, או מספר מסוים של פעולות שנדגמו מעט על ידי ה-behavior policy, זאת אומרת יש לי אותם מעט פעמים בדאטה, אז מה שיקרה זה שהווריאנס שלהם יהיה גדול, הווריאנס שלהם יהיה גדול, ואם יש לי מספיק פעולות כאלה, אז לפחות אחת מהן, אני אקבל איזשהו מיו כובע שיהיה לו ערך גדול, נכון? אז אם יהיה לפחות אחד מהם מיו כובע בערך גדול, אז בסבירות מאוד גבוהה, המיו כובע הזה ייבחר, ואם מיו כובע הזה ייבחר, בעצם אני אבחר משהו שהוא יד לא טובה, ואני אבחר את אחד הידיים, בהסתברות גבוהה, את אחד הידיים שנדגמו מעט פעמים בדאטה. אז אני יותר מדי אופטימי בעצם, אני לוקח, בגלל שיש לי דברים שנדגמו מעט מדי בדאטה, יש לי איזושהי תופעה של overestimation, יותר מדי אופטימיות ביחס לדאטה שלי. מה אני יכול לעשות עם כזה דבר? אז זה בעיה שיש לנו באופליין הראל, פעולות שנדגמו מעט, אני אהיה יותר מדי אופטימי לגביהם, אם אני סתם יריץ אלגוריתמים כאלה שמשתמשים במשערכים רגילים, ולוקחים את הארג מקס. אז מה שאפשר לעשות זה להיות פסימיסטי. ואני אגיע לזה עוד רגע, רק אני רוצה להראות מה קורה ב-MDPs. MDPs יש לנו משהו מאוד דומה, הכללה של אותו סיפור, אם יש לי איזשהו פאי כובע, איזשהו משערך Q כובע, V כובע כמובן מוגדר מתוך פאי כובע, אני אגדיר את היוטה כאן להיות ההפרש בין הבלמן של V כובע ל-Q כובע, אפשר להראות שהסאב-אופטימליות של פאי כובע כאן היא גם מחולקת לשלושה גורמים הפעם, שהגורם הראשון כאן, זה אותו גורם בעייתי שראינו מקודם, קצת מוכלל יותר, שגם התוחלת נלקחת לפי פאי כובע, אבל בפנים יש לי את Q כובע, ואם פאי כובע נלקח לפי Q כובע, אז יש לי כאן איזושהי קורלציה בעייתית, הגורמים האחרים זה גורמים שאני יותר יכול לשלוט בהם. אוקיי, אז בואו נראה מה אני יכול לעשות, לדוגמה, אני יכול לנסות להיות פסימיסטי. בואו נניח, עכשיו זה הנחה יחסית קשה, נכון? אבל בואו נניח שיש לי כאן דרך לחסום את השגיאת בלמן שלי, את השגיאה של הבלמן אופרטור שלי, ביחס לבלמן האמיתי. עכשיו, יש לי שגיאה בבלמן אופרטור כי יש לי דאטה סופי בסוף, ואין לי את הבלמן האמיתי, אני משערך את הבלמן הזה מתוך הדאטה, אז בואו נניח שאני יכול לחסום את השגיאה הזאת באיזושהי צורה. אם אני יכול, אז אני יכול עכשיו להגדיר משערך חדש ל-Q-Head שלי, שהוא יהיה משערך רגיל, הבלמן על V, ואני אחסיר את החסם העליון הזה. בהנחה שאני אעשה כזה דבר, אז עכשיו אני יכול להסתכל על מינוס היוטה, שתזכרו שמינוס היוטה פה היה הגורם שראינו בתוך הקורלציה, הגורם הראשון כאן של מה שנקרא spurious correlation הזאת, אז הגורם הזה עכשיו אני יכול לפתור אותו מפורש, זה Q כובע פחות הבלמן אופרטור על V כובע, ואם אני אציב את המשערך שלי ל-Q כובע, אני אראה שכל הסיפור הזה הוא קטן שווה מאפס. אז אני הצלחתי לגרום לגורם הראשון הזה להיות שלילי, וככה לחסום אותו. איזה אלגוריתם אני יכול ליצור מזה? אז אפשר לקחת את האלגוריתם הרגיל של value iteration, על דאטה כמובן, וכאן אני יוסיף כאן איזשהו חלק שלוקח את המשערך של Q כובע שלי, ומחסיר ממנו את החסם העליון הזה, את ה-U. אחרי זה אני כמובן ביחס ל-Q כובע הזה, אני אקח את ה-arg max על הפעולות, ויקח את המשערך של ה-V שלי, בהתאם למשערך של ה-Q, ואני אחזור על האיטרציות האלה וכו' וכו'. אפשר להראות שהסאב-אופטימליות של הדבר הזה, של הפאי כובע שאני אקבל פה, היא תהיה פונקציה של אותו חסם שנתתי על הבלמן אופרטור שלי. אוקיי, אז להיות פסימיסטי באופליין reinforced learning, זה דבר שמאפשר לנו לחסום את הבעיה הזאת שראינו שגורם לנו שיהיה לנו אובר אסטימציה ב-Q function. אם משתמשים באלגוריתמים, שוב, כמו FQI, DQN ודברים כאלה מנסים לעשות רגרסיה על ה-Q function. אוקיי, אז זה בעיה אחת שיש לנו באופליין RL. באופליין RL יש עוד בעיות, עוד הרבה מאוד בעיות שיש לנו, חלק מהן יותר אמפיריות, חלק גם תיאורטיות. יש בעיה מאוד גדולה של הכללה, זו בעיה שגם קיימת ב-RL רגיל, אבל כאן היא אפילו יותר חזקה, כי כאן אני צריך להיות מסוגל להכליל גם בין פעולות, כי אני לא רואה הכל, אין לי דרך לאסוף עוד דאטה, וגם בין מצבים כמובן, כי יכול להיות שהמדיניות שלי החליטה לקחת אותי לאזור מאוד מסוים בסטייט ספייס, ואני בכלל לא יכול לראות מצבים אחרים או דברים קרובים למצבים אחרים, השאלה אם אני יכול להכליל אליהם, זו שאלה אחת. כמובן זה מתקשר לשאלה של uncertainty estimation, out of distribution detection, איך אני יכול לתת את החסם הזה על השגיאה של הבלמן אופרטור שלי שראיתי מקודם, איך אני יכול להגיד בכלל מתי אני לא יודע משהו על המודל שלי, איך אני לא יודע משהו על הבלמן אופרטור. כמו שאמרתי, narrow distributions כאן מדובר על יכול להיות שהמדיניות בדאטה שלי היא מאוד דטרמיניסטית, היא הולכת רק למקומות מסוימים, יכול להיות שהדאטה שלי הוא מאוד סאב-אופטימלי, זה גם בעיה שתהיה לי באופליין RL, כי אני לא רוצה להיות יותר מדי דומה למדיניות בדאטה, כי אז אני לא אהיה טוב אם המדיניות שלי מאוד סאב-אופטימלית. partial observability, אמרתי כבר שאם אני לא רואה הכל בדאטה, אז יש כאן בעיה של confoundness, מתקשר שוב לנושא של Causal Inference, זה בעיה מאוד מאוד קשה שיש כמעט בכל דאטה שתקבלו שהוא יהיה אופליין. וכמובן יש בעיות של זמן רציף, בעיות של חוסר סטציונריות וכן הלאה, יש הרבה מאוד בעיות באופליין דאטה, חלק מהם גם בעיות שהן לא רק באופליין דאטה. אז בואו נראה קצת אלגוריתמים אמפיריים, איזה דברים אנשים עושים היום באופליין RL. אז יש בעיקרון שתי גישות עיקריות שהיום אנשים נוקטים בה, גישה אחת היא גישה שהיא מבוססת על פרוקסימיטי, שהיא אומרת תישארו קרובים למדיניות בדאטה, ראינו שיש בעיה של אובר אסטימציה, נכון? של ה-Q function, אבל האובר אסטימציה הזאת קורית כי אני לוקח פעולות שאין לי הרבה בדאטה, אז אם אני אהיה קרוב למדיניות בדאטה, נכון? אם אני אשאר קרוב אליה, אז לא יהיה לי, אני לא אבחר פעולות שאין לי הרבה בדאטה, ואני אהיה קונסרבטיבי בצורה הזאת, נכון? אני החליט להיות קרוב למדיניות בדאטה, אז זו גישה אחת. תפתרו את הבעיה שלכם, אבל תישארו קרובים למדיניות בדאטה. גישה אחרת, היא מבוססת על uncertainty. ראינו שאם אנחנו יודעים לחסום איזשהו uncertainty, חסם על השגיאות שלנו, אז אנחנו יכולים גם אז להיות פסימיסטים ביחס לזה, או להתרחק מאזורים שאנחנו לא יודעים את המודל טוב, או לא יודעים את הבלמן אופרטור טוב, ואז גם לא יהיה לנו אובר אסטימציה, אבל זה לאו דווקא דורש מאיתנו להיות קרובים למדיניות. אם יש לנו איזשהו חסם טוב של uncertainty, אז זה מאפשר לנו עדיין להתרחק אולי מהמדיניות שלנו בדאטה, אבל להשתמש בזה במקום. אז בואו נראה דוגמאות לזה. אז הנה אלגוריתם אחד, Batch Constraint Deep Q Learning, שמה שהוא עושה בגדול את מה שהיו עושים באקטור קריטיק, רק שהוא מכריח אותנו להישאר קרובים למדיניות בדאטה. אז קודם כל הוא לומד איזשהו מודל גנרטיבי ל-PyB, ל-Behavior Policy בדאטה, הוא דוגם Batch של Transitions, ואז הוא אומר קודם כל בוא נדגום עכשיו, הפעולות שנדגום, ה-AI האלה כאן שנדגום, יהיו פעולות שהן דומות, הן פרטובציות של ה-Pi Cover שלי. אוקיי? דוגמאות שנדגמות מ-Pi Cover פלוס איזושהי פרטובציה קטנה. ועכשיו הוא עושה מה שאקטור קריטיק רגיל היה עושה, הוא עושה רגרסיה ל-Q function. הנקודה כאן שאם תסתכלו כאן על הטרגט שלו, R ועוד גם המקס, אז המקס הוא על ה-AI'ים האלה, אותו AI'ים שדגמנו, שהם קרובים למדיניות בדאטה. אוקיי? אני לא לוקח מקס על כל הפעולות, אני לוקח מקס על פעולות שהן דוגמאות שקרובים למדיניות בדאטה. ואחרי זה אני מעדכן את הפונקציות פרטובציות שלי, וגם כאן העדכון הזה הוא דואג שהפרטובציות יישארו קרובות לפעולות בדאטה. אז בעצם מה שהוא עושה, האלגוריתם הזה עושה, הוא דואג שאתם תעשו אופטימיזציה, תמצאו משהו שהוא יהיה אופטימי ביחס ל-Q function, אבל הוא מאלץ אתכם עדיין להישאר עם איזושהי רגולריזציה שתישארו קרובים למדיניות בדאטה. הבעיה עם הדבר הזה, שאם אני מאלץ אתכם להיות קרובים למדיניות בדאטה, זה אם הדאטה שלי, מדיניות בדאטה היא מאוד מאוד גרועה, אז אני בעצם מאלץ אתכם להישאר גרועים, יכול להיות שאני לא חייב לעשות את זה. אז גישה אחרת אומרת, תעשו אותו דבר, אבל במקום לאלץ את כל ההתפלגות של פאי להיות דומה להתפלגות בדאטה, תאלצו רק את הספורט של הפונקציה של הפאי שלכם. שזה מה שהאלגוריתם הזה עושה. בר אומר אותו דבר כמו האלגוריתם הקודם, אבל במקום לאלץ ממש את כל ההתפלגות להיות דומה להתפלגות בדאטה, הוא רק אומר, תתנו איזשהו אילוץ שהספורט של הפונקציה של המדיניות שלכם תהיה קרובה למדיניות בדאטה. עוד גישה להיות קונסרבטיביים, זה על ידי לעשות איזשהו פנלטי ל-Q function, להוסיף רגולריזציה ל-Q function. זכור, הבעיה שלנו אנחנו אופטימיים יותר מדי ביחס ל-Q function, יש לנו אובר אסטימציה. אז אם נסתכל על ה-TD error רגיל, ה-TD error מנסה למזער את הפונקציה JQ פה, נכון? שאני מנסה לשערך את ה-TD error הזה, למצוא את ה-Q שישערך אותו. אבל הבעיה כאן שאני אהיה יותר מדי, שוב, הבעיה כאן שבגישה הזאת אנחנו נהיה לנו אובר אסטימציה, לכן אני אוסיף איזושהי רגולריזציה ל-Q function שלי. כן, אני אמצא איזושהי רגולריזציה ל-Q function שלי. עכשיו, היו כל מיני מאמרים שהציעו כל מיני רגולריזציות שונות, אלגדייס מתחיל בכלל מבעיית לפתור את הבעיית אופליין reinforced learning בגישה אחרת, מכל מיני פתרון של בעיה דואלית, אבל בסופו של דבר הוא מגיע לאלגוריתם שהוא מהצורה הזאת, והוא נותן את הרגולריזציה שמוסיפה למזעור של ה-TD error את ה-Q function עצמו. מה זה עושה בעצם? זה דואג לזה שאין בעיה, אני מזער את ה-TD error, אבל באותו זמן אני לא אאפשר ל-Q שלי להיות יותר מדי גדול, נכון? כי אני מוסיף אותו בתור רגולריזציה. גישות אחרות מסתכלות על איזושהי מטריקה בין פאי B בעצם למדיניות שלנו, כשאנחנו רושמים אותה בתור המדיניות שהיא מקס אנטרופי. מדיניות שהיא מושרת בבעיית המקס אנטרופי, היא נראית מהצורה של אקספוננטל Q, ואז בצורה אימפליסטית בעצם אני יכול לעשות רגולריזציה ל-Q שלי. אוקיי? אז בעצם מה שכתוב כאן מצד ימין של המטריקה זה בעצם המדיניות שלי, ומה שכתוב כאן מצד שמאל זה המדיניות בדאטה, אז אני עושה implicit regularization ל-Q function שלי, ועכשיו השאלה איזה מטריקה אני בוחר, אם אני אבחור כאן או סמי מטריקה או לא משנה, אם אני אבחור כאן את ה-KL divergence, אנחנו מקבלים אלגוריתם שנקרא conservative Q learning, אם אני אבחר כאן את ה-Fisher divergence, אני אקבל כאן אלגוריתם שנקרא Fisher behavioral regularized critic. בסדר? אז זה גם גישה לעשות רגולריזציה ל-Q. אוקיי, אז זה גישות שמבוססות יותר על פרוקסימיטי. מה לגבי מה שאמרתי uncertainty? אז בואו נראה מה אפשר לעשות מבחינת uncertainty. אז אפשר לעשות גישה שהיא תהיה מבוססת על מודל. אוקיי, אני אלמד מודל בעזרת הדאטה שלי, מודל שאני אלמד מתוך הדאטה, בעזרת מקסימום לייקליות נגיד, מודל מעברים. ועכשיו אני אניח שיש לי איזשהו חסם, מישהו נתן לי איזשהו חסם, שיודע למדוד את השגיאה בין המודל שלי לטרנזישנס האמיתיים שיש בדאטה. אם יש לי דבר כזה עכשיו, אם אני יודע לחסום את השגיאה שיש לי, אז אפשר להגדיר MDP חדש, MDP פסימיסטי, שמה שהוא עושה זה הדבר הבא. אם השגיאה במודל שלי יותר גדולה מאיזשהו אלפא, אז תסיימו את המשחק, תגיעו לאיזשהו סטייט שמסיים את המשחק, שנקרא הולט, ותיתנו לי ריוורד שהוא יהיה שלילי, מינוס קאפה, אוקיי? ואז חוזר חלילה. מה הדבר הזה יעשה? הוא ימנע ממני להגיע לאזורים שיש לי שגיאה גדולה ב-P, בכך ימנע ממני את השגיאה הזאת שיש לי בבלמן אופרייטור, ובעצם ימנע את האובר אסטימציה, אוקיי? עוד דרך לעשות בדיוק את אותו דבר, זה עוד פעם לבנות מודל ל-P, להניח שיש לי איזשהו חסם על השגיאה הזאת שיש לי ב-P, ואם יש לי את החסם הזה אני יכול להגדיר reward function חדש, שמחסר את החסם הזה, שוב זו גישה די שקולה, והיא עושה בערך אותו דבר. הבעיה שלי זה איך אני מודד את ה-U הזה, נכון? מאיפה אני מביא לכם את ה-uncertainty measure הזה, אז יש כל מיני דרכים שאפשר לעשות את זה, אפשר לעשות את זה עם UCB, LCB, לא תמיד, אבל אפשר לעשות את זה, גישות אנסמבל, מונטי קרלו דרופאוט, אפשר לכתוב ממש, לנסות לשנות את ההתפלגות של הפונקציות האלה של ה-next state ולהשתמש בזה כדי למדוד uncertainty ועוד דרכים, אבל כמובן שזו בעיה קשה שעדיין לא פתורה. אז עכשיו השאלה היא, אוקיי, יש לנו איזה אלגוריתם אופליין הראל, איך אנחנו מודדים בעצם את הביצועים שלנו, אז יש היום שני דאטה סטים או packages עיקריים שאנשים היום משתמשים בהם כדי למדוד את הביצועים שלהם, אחד זה D4RL, בעיקר יש שם משימות של continuous control, דאטה סטים באיכויות שונות, כשאני אומר איכויות שונות אני מתכוון שה-behavior policy הוא לפעמים מאוד גרוע, לפעמים בינוני, לפעמים מאוד מאוד טוב. יש את RL Unplug, הדובר אחריי דניאל מנקוביץ' חלק מהעבודה הזאת, אני מתאר יכול להיות שהוא ידבר על זה גם, יש שם עוד הרבה מאוד דברים אחרים, יש שם משחקי אתרי גם Continuous Control, הם מסתכלים על כל מיני בעיות שיש באופליין RL, וזה היום שני הדברים העיקריים שאנשים משתמשים בהם כדי למדוד ביצועים של אופליין RL. נשאלת השאלה עדיין של איך אנחנו מודדים בכלל את הביצועים שלנו באופליין RL. אז בגדול, ועם זה אני אסיים, בגדול יש שני דרכים שאנחנו יכולים למדוד את הביצועים שלנו באופליין RL. גישה ראשונה זה להסתכל על סביבה אמיתית, נכון? זה ממש ללכת לעולם אמיתי ולמדוד את הביצועים שלנו. הבעיה עם הדבר הזה שקודם כל זה לא תמיד אפשרי, נכון? אם אני מסתכל עכשיו על דאטה רפואי שקיבלתי, לא בטוח שאני אוכל ללכת לבדוק מה הדבר הזה עושה באמת, אז יכול להיות שזו גישה לא טובה. בעולמות אחרים יכול להיות שאני רוצה למדוד את עצמי עם איזשהו סימולטור, אבל גם סימולטור, יש לי סימולטור מאוד מאוד כבד שאני רוצה לבדוק את הביצועים שלי, אבל גם סימולטור כבד, הוא יהיה לו bias, ויכול להיות שזה לא באמת יבדוק לי את הביצועים שלי. אז יש כאן בעיות של איך למדוד את זה בעזרת סביבה אמיתית. הדבר השני שאני יכול לעשות זה להחליט שאתה יעשה ולידציה בעזרת הדאטה שלי, בעזרת אופליין דאטה. לדוגמה, אני יכול להשתמש בגישות של Off Policy Evaluation כדי למדוד כמה מדיניות שלי טובה. מה הבעיות עם זה? אז יש כאן הרבה מאוד בעיות. קודם כל, Off Policy Evaluation זה משהו היום הוא לא סקלבילי, הוא לא... יש עוד הרבה עבודה שם לגרום לדבר הזה לעבוד, וגם כשזה יעבוד, אז יש כאן בעיה של imperfect selection, נכון? אני צריך לבחור, ה-ground truth שלי הוא לא כמו ב-Supervised Learning שיש לי ground truth מושלם, בעצם יש לי שגיאות בשיעור של ה-value שלי, ואני צריך לבחור ביחס לשגיאות האלה. שאלות אחרות זה עם איזה דאטה בכלל אני משתמש, אני מחלק את זה לטריין וטסט, עם איזה אלגוריתם אני משתמש, יש לי הרבה אלגוריתמים של Off Policy Evaluation, איזה אלגוריתם אני משתמש ספציפית לבעיה שלי, ועוד שאלה מאוד מאוד חשובה, זה איך אני עושה את הטיונינג של ההייפר פרמטרס שלי, איך אני בוחר את האלגוריתם Off Policy Evaluation, כשאני צריך במקביל להשתמש בו כדי לעזור לעשות הייפר פרמטר טיונינג, או לבחור את האלגוריתם של אופליין RL שלי, נכון? אני צריך לעשות כאן טיונינג לשני דברים ביחד, אחד שעושה את הוולידציה ואחד שעושה גם את האופליין RL, שזה גם בעיה לא ברורה איך אני עושה בכלל את ההייפר פרמטר טיונינג של ה-Off Policy Evaluation אלגוריתם שלי. אז זהו, אז אני לא יודע אם נשאר לזמן לשאלות, אבל מי שרוצה עוד לדבר איתי, אז אני אשמח לדבר גם בפרטי, לכל שאלות שיש לכם, ולדבר איתכם כמה שאתם רוצים. תודה רבה.
יש לנו זמן לשאלה 2, אז מי שרוצה לשאול יכול להרים יד בפיצ'ר של הצ'אט, ואנחנו נאפשר לו לשאול בקול. אז כן, חנן, אתה יכול לשאול.
תודה על הטוטוריאל. יש באונליין בנדיטס ובאונליין RL יש כל נושא הזה של אקספלוריישן בונוס, ודווקא רוצים לעודד אקספלוריישן, מה שנקרא אופטימיזם in face of uncertainty, ודווקא באופליין בעצם אנחנו רואים משהו הפוך, שעדיף להיות פסימי. איך אתה רואה את הקשר בין הדברים האלה, והאם אפשר לתאר איזו סיטואציה שהיא על הרצף בין, כלומר, האם יש איזה טוגל סוויץ' כזה שעובר בין אופטימיזם לפסימיזם לפי כמות היכולת שלך לעשות אינטראקציה עם העולם?
כן, אז זה בדיוק הבעיה באופליין RL, הבעיה באופליין RL זה למצוא את הסוויץ' ספוט, יש לך את להיות הכי אופטימי בעולם, ואם אתה מנסה להיות הכי אופטימי בעולם, אז אתה נתקל בבעיות האלה של אובר אסטימציה של המשערכים שלך. אם אתה תהיה יותר מדי פסימיסטי, ותגיד, אז כמובן אתה תהיה יותר קונסרבטיבי, ואתה לא תמצא מדיניות אופטימלית. זה בא על חשבון למצוא את המדיניות האופטימלית. אתה רוצה למצוא משהו באמצע, אתה רוצה להיות אופטימי, אבל גם לשלוט כמה אתה קונסרבטיבי. וזה נתון בידע שיש לך על מה שאתה לא רואה בעצם בדאטה, על איזשהו פריירים שיש לך על מה שאתה לא רואה, או איזשהו דרך שלך למצוא חסמים, לחשב uncertainty, או דברים אינטרינזיים שאתה יכול להוציא מהדאטה, כדי להיות מסוגל להגיד כמה פסימיסטי אני צריך להיות. אבל אם אתה לא תהיה פסימיסטי, אם אתה תהיה לגמרי אופטימי, יהיה לך overestimation, אבל גם אם אתה תהיה יותר מדי פסימיסטי, אתה תקבל מדיניות גרועה. אז שוב, הקושי באופליין reinforced learning זה למצוא את הנקודה הזאת באמצע, שבה אני אמצא מדיניות שהיא לא תהיה יותר מדי פסימיסטית, אבל זה באמת הקושי באופליין reinforced learning, איך למצוא את הנקודה הזאת.
אחרי שאלה אחת של נדב, זאת תהיה שאלה האחרונה, ואחר כך נעבור לדניאל. כן, נדב.
לא שומעים.
שומעים אותי עכשיו? כן, תודה. אז תודה לטוטוריאל. מה שרציתי לשאול זה לגבי POM-DP, אמרת שתגיד כמה מילים, אז היה ב-Causal Inference, אבל אם אתה יכול באיזה שני משפטים לסגור את הסטייל.
אז ההבדל העיקרי ב-POM-DP לעומת אונליין reinforced learning, באונליין reinforced learning, כשיש לנו POM-DP, אז אפשר לעשות שני דברים. אפשר לקחת את כל ההיסטוריה, או אפשר לקחת belief state, שניהם יהיו sufficient statistic ל-state, ואז אתם יכולים לפתור את הבעיה בגדול. כן, זה בעיה מאוד, זה עדיין בעיה, עדיין קשה לפתור את הבעיה, אבל אין בעיה למצוא מדיניות אופטימלית. כשיש partial observability ב-offline reinforced learning, אז אם גם הפעולה, וגם הפעולה בדאטה, וגם המצב הבא, או המצבים בדאטה, הושפעו מהחלק הזה שלא ראיתם, איך הפעולה בדאטה מושפעת ממה שלא ראית? בגלל שה-behavior policy לוקח את הפעולה על סמך שמשהו שלא ראית. אז אם שני הגורמים האלה, גם המצבים, גם ההסתברות מעבר, וגם הפעולות, הושפעו מאיזשהו גורם שלא ראית בדאטה, ואין לך איך לדעת אותו, הדבר הזה יוצר איזשהו משהו שנקרא confounding, ויש לך בעיה לעשות identifiability, זאת אומרת, גם תסתכל על כל ההיסטוריה של המדיניות שלך, כשתלך לעולם האמיתי, בגלל שהבעיה היא off policy, וזה קצת קשה להסביר את זה על רגל אחת, אבל פשוט תאמינו לי, שאם תנסה לעשות off policy, אז אתה יכול להיות מה שנקרא arbitrarily bad, בלי שום הנחות על מה שאתה לא רואה, תעשה מה שאתה רוצה, אם לא יהיה לך שום הנחות, אני יכול תמיד למצוא איזשהו פום DP, זאת אומרת איזשהו מרחב מצבים שאתה לא רואה, שבו אתה לא תוכל, שאני יכול ליצור מדיניות שתהיה arbitrarily bad. בסדר, זה הבעיה שם, וזה בלי לפרט ולהראות דוגמה, אני מסביר את זה, ומי שזה מעניין אותו, אז באמת זה תחום שנקרא Causal Inference, ויש על זה, ורואים את הדוגמאות האלה כבר במקרים מאוד פשוטים, אפילו של בנדיטס, זה פשוט בעיה אינרנטית שקיימת, שנקראת בעיית ה-confounding, ה-hidden confounding.
אוקיי, תודה רבה גיא. דניאל מנקוביץ' מדיפ מיינד, מזמן לקחת את זה מעלה.
אוקיי. רואים את המצגת שלי?
רואים, כן.
אוקיי, טוב. שלום לכולם. אני אעביר את המצגת היום באנגלית. So hi everyone. I'm Daniel Mankowitz. I'm a research scientist from DeepMind, and I'm going to be talking today and motivating challenges of real-world reinforcement learning. So a little bit about me. I'm originally from South Africa. I then completed an MSc in machine learning, robotics, and computer vision at Edinburgh University. And then I made Aliyah, and I did my PhD in reinforcement learning at the Technion with Shie Mannor. I was a Google PhD fellow, and now since 2018, I've been a research scientist at DeepMind. So in this talk, I'm going to first start by motivating the real-world challenges, or the challenges we have of incorporating reinforcement learning into real-world problems. I'm also going to talk a bit about what we do within DeepMind to try and deal with or solve these challenges. The next step, or the next part of the presentation, I'm going to be talking about the research platform that we designed in order to try and solve some of these challenges, which we call the Real-World Reinforcement Learning Suite. And then I'm going to discuss a couple of works that we've been working on that try and deal with the problems to do with robust and constrained reinforcement learning. So in a perfect world, data collection is inexpensive, it's fast, there's no noise in the data, it's fully observable, and it's generated by a stationary distribution. The constraints are always satisfied in practice by the agent, and short-term myopic decision-making is always enough. However, in reality, data collection is expensive and slow. The data is noisy, it's partially observable, it's often non-stationary. The constraints are not always satisfied in practice, and myopic decision-making is not always enough. So many applications have these properties, from recommender systems to physical control systems to resource allocation on processors, for example. And so what we decided to do, based on our experience in working with a number of different applied real-world systems, is we decided to write a paper that detailed the challenges that's preventing reinforcement learning from scaling to real-world applications. We call this the challenges of real-world reinforcement learning, and we identified 9 challenges that we think need to be solved in order to scale RL. Here are some of these challenges. You have delays in systems. You often have limited samples to mention from, so you're in the offline RL setup or computationally efficient learning setup. There's multiple objectives that you care about. The data might be partially observable. There's constraints, etc. So what do we do, or how do we try and deal with these types of problems? So the first thing is that within DeepMind, we try and collaborate with Google teams, and we try and learn a lot about their problems. we try to incorporate reinforcement learning algorithms then once we understand their problems into their applications. But the way in which we do this is we need to do application-driven research. So the idea is that once we have context for these problems, we then try and develop and publish new algorithms that are inspired by these problems and can hopefully work in these applications and also extend to external real-world problems. The critical research challenges that we are looking into or are trying to solve or at least improve upon are offline optimization, so learning from data logs. So Guy gave a great tutorial all about that. We also want to deal with robustness to non-stationarity, partial observability, and action and observation noise. It's very important in many applications that the constraints are satisfied once you deploy the agent into the real system. And in many cases, long-term planning is very important. So myopic decision-making is not enough. So how do we typically approach the research that we do? So there's a number of different products that we're engaged with. And the idea is then to look at these products and try and identify repeatable product problems that we see. And then the idea is to align our research to try and solve this repeatable product problem. We then establish well-defined long-term research goals to achieving this and corresponding metrics. And then it's really important, we've found, to establish a research environment that allows us to very quickly iterate on the research that we do. So this leads into the first or the second part of the talk, which is talking about a research environment that we developed for doing real-world reinforcement learning. Disclaimer, it is a simulation suite, but the idea is to really be relevant for real-world products and settings that we encounter. We also wanted this suite to be accessible and useful for the external community. And so the idea was that it needed to be easy to use. We needed to be able to, add a challenge with a couple of lines of code. And it also needed to be very flexible. So if you wanted to incorporate an individual challenge like a delay, you could do that. If you wanted to incorporate multiple different challenges, you could do that too in the combined setup. So what we did is we developed and we open sourced the real world RL suite. It's a simulation suite. It implements 8 of the 9 real world challenges that we mentioned in our paper on 8 different Mujoku tasks. So it's effectively a wrapper on top of Mujoku, which was the framework that was what we decided to work upon that had a lot of relevance for the products we work with. It's very flexible and easy to use. You can easily incorporate multiple challenges into the setup. And there is a Jupyter notebook in the open source version that you can use to immediately start running an agent in a browser with the setup. We baselined and analyzed the performance of a number of state-of-the-art agents, D4PG, DMPO, and MPO, on at least 18 different investigative experiments across a number of Mujoku tasks. And there's a work early on in the talk that you can take a look at that really goes into detail about the performance on each of these challenges. And then finally, we present what we call the combined challenges leaderboard, where we incorporate many of the different challenges into a single task. And we order them in terms of difficulty, so we have easy, medium, and hard. And the idea is to really encourage the external community to try and solve these challenges, where we believe that solving them will unleash a lot of, or enable a lot of applications to utilize reinforcement learning to its full potential. So how does the suite work? So there's a number of different challenges on the left that you might want to incorporate into your environment. The idea is then, if you want to incorporate action delays, you simply import the real-world RL suite, and then you call the load function, which has a delay specification dictionary. You enable it, and you set the action delay to 20 time steps. And then you kick off the agent, and you'll have an agent running an environment with a 20 time step delay. Similarly, you can run hyperparameter sweeps if you like, and you can then add a vector of delays. And the idea is then you will be able to have graphs like this, where you can see the x-axis is as you increase the delay, the y-axis is the return, and you can see the effect on different domains of incorporating action delays into your environment. So I'm just going to talk about a couple of the features that the setup has. So one of them is system delays with respect to action, observation, and rewards. So in many real-world applications, as I'm sure many of you have come across, there are action delays in which physical systems take time to execute the action. There's reward delays, often when interacting with apps that users download. They might only, they might uninstall it, they might like it, and this can all this can be really delayed in terms of their response. And there's often observation delays as well due to latency in the internal system hardware. So these are all features that are supported in the setup. So the left graph here is action delays, the middle graph is observation delays, and the right graph is reward delays. And you can see very quickly this sensitivity of different agents in different domains to different types of delay effects. And here, for example, it seems to be less sensitive to reward delays compared to action and observation delays. And the hope is that this can give you a lot of intuition very quickly as to how your algorithm responds in different types of challenge setups. You might want to incorporate notions of partial observability into the setup. This comes across quite often in many real-world systems. In recommender systems, you often don't know the mental, or you usually don't know the mental state of the user. In many physical control systems, sensors might suddenly become stuck for a period of time. They also might drop in the sense that they might just get set to an arbitrary value, or they might be uncalibrated. And so we've added the support for stuck and dropped sensors. So if you look at the graph on the left for the quadruped warp task, the y-axis is the duration of how long an observation should be stuck for, and the x-axis is the probability of the observation of that particular sensor observation being stuck. And you can see that as you increase the duration of the stuck observation and the probability of it being stuck, performance degrades, and similarly for dropped sensors. So again, hopefully a useful tool for people to work with. We also created this all challenges leaderboard, as I mentioned previously, where you have the performance of the challenges when turned off, which is in blue, and then you have the performance of the agent on each challenge when the challenges are either easy, medium, or hard. As Guy mentioned, in the RL Unplugged work, we've also released open source data sets of each of these challenges for researchers in the community or in industry to work on. Another nice tool, and this is something we're going to be adding to the open source suite, is the ability to do radar plots, where each challenge is displayed on a circle, and then you can look at the effect of increasing the difficulty of each particular challenge and compare algorithms accordingly. So for example, here, as we increase the action delay, we can see that for larger action delays, D4PG tends to do slightly better than that of MPO, but at least it gives kind of a visual representation of algorithmic performance. So in conclusion, we've developed and open sourced the suite. As I mentioned, we implemented 8 of the 9 challenges of real-world RL. Explainability is one of the challenges, where the idea is that often in many real-world systems, you need to be able to explain the performance of a particular RL agent to, for example, someone operating the system, or to stakeholders involved. And this is something really important to be able to explain effectively how your agent is doing. And this is quite abstract and is something we've left for future work, but obviously if anyone has ideas, that would be great, and feel free to message us or talk to us about that. We've analyzed the performance across these different challenges, and we've presented the combined challenges leaderboard, which we encourage everyone to try out. So I'm now going to, in the last part of the talk about 2 different types of challenges that we're currently addressing from the research perspective. And these are all centered around the notion of robust reinforcement learning. So the motivation for this is, imagine you have an arm, a robotic arm in a factory, and this arm needs to pick up a box, and this arm has a particular dynamical system, P1. Now, we want to be able to train policies that are robust to perturbations to the dynamics of this particular system. So for example, if there's wear and tear, uncalibrated sensors or broken sensors, or if a new arm replaces the old arm and has slightly different factory specifications, for example, arm P2, we still want the agent to be able to solve the task with the original policy. When the agent is unable to solve the task on a perturbed version of the original dynamics, we refer to this as model misspecification. This is something that was a theme throughout my PhD, and is something that we're making a theme in DeepMind as well. And the idea is that, as I mentioned, if the agent performs poorly on a perturbed version of the task, we have a misspecified model. So the goals of this work, or of this robustness track, is we wanted to be able to modify state-of-the-art continuous control algorithms to optimize for worst-case performance and mitigate this model misspecification. So if you look at this equation in the bottom left, the typical RL objective is we want to maximize learn a policy that maximizes the expected return. But now we have an infimum placed into the mix. So we really want to say we want to find a policy that maximizes the worst case expected return with respect to the dynamical systems that it encounters. So the algorithm that we decided to work with was called maximum a posteriori policy optimization. This is a DeepMind algorithm that's also been open sourced. It's a policy iteration algorithm for continuous control and does really well on many of the Majoku tasks. It's got two steps: a policy evaluation step, where we want to evaluate a value function for a policy pi k, where k is the current iteration. And it has a policy improvement step. So once we learn that value function, we then generate what's referred to as a proposal distribution, and we fit the current parameterized policy that the agent's learning to this proposal distribution by minimizing the KL divergence between the two. This step is repeated, and that leads to really good performance. But how do we incorporate robustness into the setup? Well, if you look, for example, at this original example with different dynamical systems corresponding to perturbations of the original system, for a given state in action, if you execute that in each of the different systems, the agent will end up in a slightly different or perhaps very different next state, as indicated by the next state set that you get on the right. So what we want to do is we want to then take the policy evaluation step of MPO, and we want to turn it into a robust policy evaluation step. So the idea is that we then want to place an infimum over the target action value function. And the idea is that for each of the different dynamics that we're including in the uncertainty set, we then want to, if you look at the bottom right figure, take the action value function that leads to the worst case expected return from each of the possible states that the agent could have transitioned to. We therefore are optimizing with respect to the worst case action value function, and this leads to interesting robustness performance. So I'll quickly dive into that. I'm first going to just give an overview of our experimental setup and then discuss some of the experiments. And our baselines were the original MPO algorithm, the robust variant, and a soft robust variant, which I won't go into detail in this talk. So typically what we do is we choose a task, in this case, cart pole, and we choose a parameter to modify. So in this case, we've chosen to modify the pole length. In this robustness setup, the agent always acts in a single environment, which we call the nominal environment. So this is a pole of length 0.5 meters. And we then create what we call an uncertainty set of 3 task perturbations of 0.5, 1.9, and 2.1 meters. The idea is then, and this would correspond to different dynamical systems, P1, P2, PK. We then evaluate the agent on an unseen holdout set of task perturbations, which we call the evaluation set. So if you look at the graph on the right, we have environment 0, which corresponds to 2 meters, environment 1, which corresponds to 2.2, and environment 2, which corresponds to 2.3 meters. And you can see on the y-axis, we show the average return. So you can see that for the original MPO algorithm, the E just stands for entropy regularized, which is a minor detail. The algorithm does really poorly as the perturbations increase, whereas for the robust and soft robust variants, they tend to do very well. And this is repeated across many different experimental domains. And one thing that was quite a nice outcome is for the walker agent, we increased its thigh length, and we saw that the robust solution was for it to drag its leg when its thigh was too large. And maybe this is something that us as humans might do as well, but it was really interesting to see that the robustness, this sort of small, simple robustness change leads to really interesting and different behaviors. So the final last couple of slides is an extension of this. We wanted to determine whether an agent can be both robust to state perturbations with respect to the return, but also can it be robust with respect to constraint satisfaction. So if you take the original equation that I mentioned previously, optimizing the worst case return, and then you add a constraint such that your worst case constraint violation, or your worst case sum of penalties, of constraint penalties, is less than or equal to a threshold, you're trying to ensure that you're robust to the worst case performance, and the worst possible penalties you get with respect to your constraints don't violate the threshold, the constraint threshold that you care about. But the first hypothesis that we had to ask is, does perturbing the dynamics affect constraint satisfaction performance? So if you look at the two figures in the bottom row, this is what we call constraint overshoot. So the green graph goes above 0 when there's violations. And the x-axis is basically increasing the perturbation to each domain. And you can see that as we increase the perturbation for these two example domains, their constraint violations occur. And we really were able to conclusively answer this question that constraint satisfaction performance is indeed affected by perturbing the dynamics. So we had to measure this performance somehow. How do we combine constraints and return? So the light bars in this figure is the return, R, and the dark bar is what we call the penalized return, which is the return, but it's penalized by the constraint overshoot, where the constraint overshoot is this little section here. This isn't the perfect metric, but it's one that we worked with and decided to use. We saw that for our variants R3C and RC, our agents were able to significantly outperform the state of the art in terms of penalized return. So this was really good to see. And we applied this across all different tasks and domains in our setup. And this was conclusively the result that we get. So really having these kind of simple types of like optimizing for these simple concepts, like worst case constraint violations and worst case return, really can yield improved performance to unseen perturbed versions of the original task. So just concluding, there are many challenges to scaling reinforcement learning to real-world applications. But a good research platform is really important to be able to iterate quickly. And this is where in our case, the open source real-world RL suite has been really helpful. Robustness and constraint research is one of the areas that we're really thinking about a lot, motivated by many real-world problems that we encounter. And yeah, for more info, feel free to contact me. Thanks.
Thank you, Daniel. I guess I have time for one question if anyone wants to have any. Please raise your hand, the participant section. Shie.
Hi. I have a question about what is the relation between classical. It reminds me classical problems in optimal control theory. That there are some methods in classical control theory that address uncertainty in the plant parameters. Can you say some words about the connection between classical control methods to these methods, to your method?
Yeah, sure. I mean, I'm not an expert in classical control theory, but there are a number of different connections between the two. I mean, effectively, both of them are performing sort of a type of planning. They're just doing them in slightly different ways. I think that in terms of its connection to solving real world problems, one of the things that we see is that for particular problems, there are certain setups where classical control is the right thing to do, and traditional sort of reinforcement learning style approaches might not be well suited to those types of problems. So I would say that classical control sort of algorithms are a tool that we should definitely be using in, or at least considering, in real world problems. And I think this is something that often gets overlooked. So I think this is a really good question, and I think that there's certainly a connection between the two from a planning perspective, and perhaps this is something we could also take offline. But in general, I think it's a very effective tool if used on the right problem.
Right. Thank you, Daniel. בואו ניקח כולם רק 2 דקות של הפסקה, וב-10 חנן יתחיל להציג את הסשן של ההרצאות הקצרות. נשתדל שנספיק גם להשאיר זמן לשאלות בסשן הזה. ממש עוד 2 דקות נתחיל לסשן שלי. אוקיי, בבקשה חנן, זמן להתחיל.
Hi, can you hear me?
כן, אני שומע.
Okay, so my name is Hanan Shteingart. I'm very glad to present here in the first IRLD 2021, and I would like to talk today on the business value of reinforcement learning and causal inference. So the outline of this talk will be that I will talk about the business need. I will talk about causal inference and RL, as Guy mentioned in the tutorial this morning. I'll talk about the great potential that offline reinforcement learning has, but its great challenges as well. And finally, I will give some ideas of how can we solve these issues. So me in reinforcement learning, in my PhD in the Hebrew University, I modeled human behavior using reinforcement learning. I also teach reinforcement learning and supervised learning in a Y Data School, which is held at Tel Aviv University. And I used our reinforcement learning to predict game level difficulty in Playtika. And today, as you can see on the top right logo, I work for Vianai. So why do we need actually something beyond prediction? Susan Ethay, which is a very famous economist from Stanford, she says there is a gap between making a prediction and making a decision. You can see this on the top right corner graph, where you can see the difficulty versus value of different analytical approaches. And when you think about descriptive, it's like tools like Tableau or any other visualization tools. When you think about predictive, you can think about AutoML, DataRobot, and other companies that solve the prediction problem. But actually what business need are prescriptive tools. They need something that will tell them how to make decision. However, when you look at the Causal survey of which approaches or which method people use when they, like data scientists use oftenly, you can not see at all methods which are related to policy issues. To maximize a KPI or to measure the effect of doing some action. So what is the business opportunity for policy learning? You can see on the right a graph which shows the value in trillions of dollars locked in different verticals in the business. This was published by McKinsey & Company. And you can see that the main fields where there are values are marketing and sales and supply chain management. And you can compare it to the other verticals, and you can see it's much bigger than all the rest. Now, what is shared between marketing and sales and supply chain management? In both of them, there is some KPI reward. You have some action that you can make. It could be a campaign, it could be a discount, it could be to change the rate of manufacturers and so on. Yeah, there is some context or state for a user or for a factory. And you have some constraints. And this actually reminds us very well of reinforcement learning. So it seems like it's a very good fit. For example, you can think on the reinforcement learning framing of interaction between a company and a user, or a customer. There is a customer, here's the environment, and the company is trying to maximize the user engagement or the lifetime value of the user. And actually, the data itself would be very complex because there are many touch points between the customer and the company. And there are many type of actions, and the timeline could look very complex, like the picture on the right, where we show a customer journey mapping or a lifetime of a user. Now, how can we optimize our actions or policies? Essentially, there are three resources that we can use. One is simulation, like mentioned by the DeepMind talk. And there is also a company bought by Microsoft called Bonsai, where they use simulation and reinforcement learning over simulation of a real environment, physical environment, to optimize a policy. So this is one way to go. Another way to go is to experiment. If you can experiment really easily, you can use something like Personalizer by Microsoft, where they use experimentation and bandits to optimize the policy. However, as a guy mentioned in the beginning of the tutorial on offline reinforcement learning, we have a lot of observational data. And this is useful also both because it's already there and because sometimes you cannot really experiment and you don't have really a good simulation of how people behave. And you cannot do all the experiments that you want due to moral reasons or business reasons. This is where causal inference really shines. Causal inference, as Guy mentioned, is really related to reinforcement learning because it talks about what would happen if we have done something else. Look at Indiana Jones here in front of the statue. He thinks what would happen if he touched the statue, or what will happen if he wants to touch the statue. But once he touches it, he can never know what would happen if he did something else. This is depicted in this figure from a causal inference course, where T represent an action, Y represent the outcome. Y1 and Y0 represent the outcome if you would do action T equals 0 or T equal 1 respectively. But actually from the data, you don't know what would have happened if you have done something else from the action that was really taken place. Why are we talking about causal inference? Because actually causal inference and reinforcement learning are really related, although these two disciplines have evolved very independently. And only like in recent years, there seems to be some merge and wedding between these two fields. And I strongly feel that there could be a lot of potential in looking further and the interaction between these two fields. For example, Elias Birnbaum talks about how these two fields can actually improve result. And as a side note, from a cognitive, as a person who did his PhD on cognitive science and neuroscience, there is also some relation to how animal and human behave. It seems like causal learning is more related to fast learning, which is like in a higher type of animals, and reinforcement learning represent more slow learning, which presented in a lower form of animals. Sorry. There seems to be some issue with the presentation. Okay, so for example, causal bandits. If you look at causal bandits, it was shown both in 2016, 2018 that you can actually improve bandit performance if you take the causal structure of the problems into account. Now, offline RL, as Guy mentioned in the tutorial today, is very promising because, as Levin says, offline reinforcement learning algorithm could be a powerful decision-making engine. And in a very successful paper and also blog post that I recommend everyone to visit called worldmodels.github.io, it shows that they show that actually if you build an offline model of the world, you can actually play, instead of playing with the environment, you can play with a model of the environment and get a better result than what you would get if you just play the environment directly. So this is really promising from business point of view, because you can come to a company, take their offline data and show that they could have actually do better just by using their offline data without doing any experimentation. I have some technical issue with the presentation, sorry. Now, there are great challenges as well. As Guy mentioned, there is a distribution shift, and there are important sampling variants, and there are high barrier. And from my point of view, there is no easy framework like Scikit-learn, where you can take offline data and tell it, find me a better policy. It doesn't work so easily. How can we solve this? So there are many solutions, like Guy mentioned, but one method which I see orthogonal to the thing that Guy talked about is to use domain knowledge. Like you can come to a person, and usually domain experts, they can tell you what are their heuristic agenda or heuristic policy. And it was shown in a paper in 2019 that you can actually use this initial domain knowledge policy to train a reinforcement learning agent, which is warm started by the domain knowledge expert, the expert to the domain knowledge. And this is, they call it Prolonet, and you actually can converge much faster and get better performance. This is interesting because you can come to a company, interview the domain expert, come up with some initial policy, and only train from this point and forward. So why did I give this talk? First, I really enjoy reinforcement learning. I love it, and really excited to be a member of this conference. But there are also other things that I would like to talk about. First, we need people who know reinforcement learning. You're welcome to go to this link and see the job post that we have. We call for academic collaboration. This field, as you know, is very hard. If you are working in the academia and you're looking for collaboration with industry, we'll be happy. And if you represent a business where you have some KPI that you would like to optimize, we will be happy to chat. Thank you very much.
תודה חנן, thank you. זמן לשאלה אחת אם יש מישהו. אז אני מצביע ב-participants. בסדר, אם לא, אז אנחנו נעבור לרן לב.
שלום לכולם, שומעים אותי?
כן.
מעולה, אני אשתף את המסך. טוב, אז שלום לכולם, אני לוי, שמח להיות כאן. אציג לכם היום את המחקר שעשיתי תחת הנחייתו של פרופסור חנוך, בנושא של השמה ברשתות סלולריות משולבות רכבים. אז מהי מערכת סלולרית? מערכת סלולרית מורכבת ממשאבים ובייס סטיישן שמכיל אותם. יש יוזרים שמגיעים ועוזבים, וכמות המשאבים שכל יוזר צריך תלויה במיקום שלו. יוזר קרוב ייקח קצת משאבים, יוזר רחוק ייקח הרבה משאבים, והשאלה שנשאלת במערכת כזאת היא, מגיע יוזר, האם לקבל אותו או לא. אז מה הבעיה במערכת סלולרית רגילה? שכמות המשאבים מוגבלת, והיא לא עומדת בעומסים שהאופרטור לא חזה. והביצועים והאלגוריתמים במערכת כזאת בסופו של דבר חסומים על ידי איזשהו חסם תיאורטי, לכמה יוזרים אפשר לשרת. אז הפתרון שהוצע בשנים האחרונות הוא להגדיל את הקפסיטי של הרשת הסלולרית על ידי שימוש ברכבים ובאנטנות החזקות שלהם, כך שאם יוזר יבצע שיחה דרך מכונית לבייס סטיישן, הוא ייקח פחות משאבים. וככה נוכל להגדיל את כמות היוזרים שאנחנו יכולים לשרת באופן תיאורטי. המחקר הוא עבודת המשך למחקר מעמיק שעשה נדב לוי בתחום. בשורה התחתונה לא ידוע לנו על מחקר שפותר את בעיות האדמישן והאסיימנט במערכת עם אתגרים כמו שלנו. אז מהם האתגרים? האתגר העיקרי במערכת כזאת הוא גודל הסטייט. במערכת סלולרית רגילה מספיק לזכור את כמות היוזרים שיש לנו מכל סוג, אבל במערכת כמו שלנו צריך לזכור לא רק את הכמות, אלא את המיקומים הספציפיים של היוזרים והמכוניות, שזה מגדיל אקספוננציאלית את מרחב המצבים. אז אנחנו בעצם מציעים לפצל את הפתרון לשני אלגוריתמים שמחוברים באופן חלש. יש את אלגוריתם האדמישן שאנחנו פותרים עם MDP קומפקטי וסטייט קטן, ויש את בעיית האסיימנט שיש לה סטייט מצבים גדול, ואנחנו פותרים באמצעות Deep Reinforcement Learning יחד עם Imitation Learning, והיום נדבר על מה עשינו באסיימנט. אז אם נסכם בקצרה את התרומות שלנו, אנחנו מציעים אלגוריתמים ל-Admission ו-Assignment, ככה שאת אלגוריתם ה-Assignment אנחנו פותרים באמצעות Deep Reinforcement Learning, שם אנחנו מציעים שיפורים בעולמות ה-RL וה-Imitation, ואנחנו מבצעים ניתוח ביצועים ובודקים כמה יוזרים אנחנו משרתים בפועל, אז אנחנו משווים בין מערכת סלולרית רגילה למערכת סלולרית עם רכבים, שם אנחנו רואים שניתן לשרת כ-30-40% יותר יוזרים, ואם נוסיף את האלגוריתמים שאנחנו מציעים, אז נקבל תוספת של עוד 10-20% בכמות היוזרים שאפשר לשרת. אז אלגוריתם ה-Assignment, אני אזכיר, השאלה היא לאיזה מכונית לעשות Assignment, אחרי שהחלטנו שאנחנו מקבלים את היוזר. אז יש לנו כמה אלגוריתמי בייסליין, יש לנו את האלגוריתם הגרידי שמקצה למכונית הטובה ביותר, האלגוריתם הרנדומי שמקצה למכונית רנדומלית, והאג'נט שמקצה לבייס סטיישן בלבד. הגרידי הוא בייסליין יחסית חזק, שאר האג'נטים הם יותר לניתוחים מתמטיים. אז זה סכמת האלגוריתם שאנחנו מציעים. הארכיטקטורה מבוססת על אלגוריתם של וולף פרדינגר, שמבוסס על DDPG, שמבוסס על אקטור קריטיק, עם שינויים וחידושים שאנחנו הכנסנו. השינויים מתוארים והחידושים מתוארים בצבע כחול. אז אני אתאר את סכמת האלגוריתם, אז תהיו איתי. אז מתחילים מסימולציה שבנינו, שמהסימולציה אנחנו מוציאים את הסטייט הלוקלי סביב היוזר, שהסטייט הזה מכיל את המכוניות סביבו. הסטייט הזה נכנס לסטייט אנקודר, שמוציא representation בממד נמוך. את הסטייט בממד נמוך אנחנו מכניסים לרשת אקטור, שמוציאה את המיקום הספציפי של המכונית שנבחרת, ממש את המיקום של המכונית, זה ה-assignment. הבעיה בתוצאה הזאת שיכול להיות שהמיקום לא חוקי, אין שם מכונית, או שהמכונית לא פנויה, ולכן אנחנו משתמשים ב-KNN כדי למצוא את המכוניות הקרובות והחוקיות. לכל סט של state ומכונית, אנחנו מחשבים את ה-value באמצעות רשת קריטיק, ולוקחים את ה-action עם ה-value הכי גבוה. ה-action חוזר ל-environment, שמשם יוצא reward שהצבנו, ולאחר מכן אנחנו לומדים. את הלמידה אנחנו מבצעים באמצעות הלוסים הרגילים, פלוס לוסים של teacher, שכאן נכנס החלק של imitation learning, שגם שם אנחנו מציעים כל מיני שיפורים. אז אם ניכנס קצת לזום של האלגוריתם, אז יש את DDPG, שהוא לוקח state ומוציא action במרחב רציף, לאחר מכן הגיע מאמר מעולה שמציע פתרון עם המרה למרחב דיסקרטי. האלגוריתם שלנו צריך שהאקשנים יהיו גם במרחב דיסקרטי וגם חוקיים, אז מבחינה טכנית אין כאן הבדל גדול, אבל קונספטואלית העניין של צעד חוקי או לא, הוא חשוב להרבה בעיות ומשחקים. מבחינת לוסים, אז יש את הלוסים שהציגו במאמר של וולף פטינגר, שיש את ה-Temporal Difference Loss לקריטיק, ואת הלוס של האקטור שרוצה למצוא את האקשן עם הvalue הכי גבוה. אז רובכם יודעים שלא פשוט לאמן Reinforcement Learning, ולכן החלטנו להשתמש במגוון שיטות. השיטה הראשונה היא להשתמש ב-Teacher, ב-Imitation Learning, ובתור ה-Greedy Agent שיהיה כ-Teacher, בגלל שהוא בייסליין מאוד חזק. אז אחד המאמרים הידועים בתחום מציע פתרון שנקרא DQFD, שמשלב את ה-Teacher בלוס של הקריטיק. בפועל מה שהוא מנסה לעשות זה להרחיק את ה-value של האקשנים של ה-Teacher מהאקשנים האחרים, על ידי כל פעם בחירה של אקשן מסוים. הלוס הזה הוא טוב, אבל יש לו מספר חסרונות. החיסרון הראשון הוא שאנחנו לומדים לשפר את ה-values של האקשנים שהם יחסית רחוקים ופחות רלוונטיים. והבעיה השנייה היא שאם תשימו לב, הלוס הזה מזכיר קצת את ושסטריאן גן לוס. הלוס הזה פחות יציב אם הפונקציה הנלמדת היא לא כליפשיץ. במאמר המקורי טיפלו בזה על ידי לעשות קליפינג למשקולות, אחרים מוסיפים פנלטי לגרדיאנטים, אנחנו מטפלים בזה בדרך אחרת. אז מה אנחנו מציעים? קודם כל נבחר את האקשן עם ה-value הכי גבוה, ושנית אנחנו ננסה לגרום לכך שה-value של האקשן של ה-teacher יהיה קצת יותר טוב מהאקשנים האחרים, אחרת פשוט לא נשתמש בלוס הזה, ואנחנו יכולים לעשות את זה כי יש לנו את ה-Temporal Difference Loss בנוסף. אז זה הלוס של הקריטיק הסופי, ה-TD לוס הרגיל ממושקל עם ה-teacher loss, ובנוסף אנחנו מגדירים loss לאקטור, שמשקלל בין האקשן שנבחר לאקשן של ה-teacher. נשים לב שהמשקול בין הלוסים של ה-teacher ללוסים הרגילים, יורד ככל שהאימון מתקדם, כדי שנוכל בסופו של דבר לגבור על המורה. אז אם אנחנו משווים בין הלוס של DQFD ללוס שלנו, אנחנו רואים יציבות גדולה יותר בתהליך הלמידה. אז אם נסתכל על הלוס של האקטור כפונקציה של הטריינינג סטפ, ניתן לראות שהוא באופן כללי נמוך יותר, וכאן ניתן לראות את ה-Standard Deviation, שמראה שהלוס יציב יותר, ושני הגרפים בעצם מראים שהאימון עם הלוס שלנו מספק אימון יציב יותר, ובמציאות זה קריטי לאימון והתכנסות של רשת נוירונים לפתרון טוב. אז אני אדלג. אז ב-RL גם קשה ללמוד State Representation, ולכן החלטנו להשתמש באוטו-אנקודר, כדי לשפר את הלמידה ולהוציא Representation בממד נמוך. השתמשנו באוטו-אנקודר שמתאים לבעיות RL, שמוציא state מסטייט את הסטייט הבא ואת הריוורד. ובמאמר המקורי הם השתמשו ב-L1 loss, שהוא עובד טוב למקרים סטנדרטיים. במקרה שלנו יש לנו קלט שהוא ברובו ספרסי, ושמנו לב לתופעות משונות במהלך הלמידה. אז אם למשל נסתכל על הקלטים מצד שמאל, ועל הפלט מצד ימין, נשים לב שלכל הקלטים מצד שמאל יש בדיוק את אותו L1 loss, עבור כל הקלטים, ללא תלות במיקום של הערכים, וכאן נתקענו באיזשהו מינימום לוקלי. אז ניסינו weighted L1 loss, שממשקל את הערכים הרלוונטיים, למשל בתמונה, והוא אכן עזר. מצד ימין רואים את הפלט של הרשת, שהוא קרוב לקלט, אבל לא בדיוק, היה איזשהו אזור שהרשת הרשתה לעצמה קצת יותר לטעות. אז מה האינטואיציה? אנחנו רוצים למשקל גם איפה שיש ערכים חיוביים וגם מסביב אליהם, במשקול שהוא קצת יותר חכם. אז איך נעשה את זה? באמצעות קונבולוציה. אז אנחנו מגדירים לוס חדש, שאנחנו קוראים לו weighted convolutional L1 loss, שלוקח מצד שמאל את הקלט, ומבצע עליו קונבולוציה כדי להגדיר מטריצת משקולות B, וכאן כבר קיבלנו תוצאות הרבה יותר טובות שקרובות לקלט המקורי. אז ככה זה נראה באופן יותר פורמלי. זה מבנה הרשת, רשת מאוד כלילה, רשת, יש לנו את האנקודר, דיקודר, ואת החלק של האג'נט שמוציא לנו value ו-action. אז אם נסכם את התרומות שלנו ב-assignment, אנחנו מציגים את הקונספט של אקשנים לחוקים ב-DDPG, אנחנו מציגים שיפורים שיכולים לעזור באלגוריתמי imitation, ולוס ממושקל באמצעות קונבולוציה שיכול לעזור בבעיות ספרסיות. אז performance evaluation, אנחנו רוצים לבחון איך מכוניות תורמות, לכמה יוזרים אפשר לשרת, ואיך האלגוריתמים שלנו תורמים. אז צריך להגדיר מה זה load במערכת כמו שלנו.
אנחנו צריכים לסיים, אתה יכול לסגור את זה?
אז אני אסיים בקצרה. אז כאן רואים את הפערים בין האלגוריתמים שיכולים להגיע מ-30-40% ללא מכוניות, ועוד 10-20% לאלגוריתמים שלנו. ואני אסיים, תודה רבה.
תודה רן, אם יש לנו שאלה, נסו אחת. כן, בנימין.
משהו קטן שלא הבנתי, כשדיברת על השווית את הביצועים של הלוס עם הטיצ'ר הזה על האקטור, בעצם הראית שהלוס עם מה שהוספתם הוא נמוך יותר מהלוס בלי מה שהוספתם. לא כך הבנתי, כי ב-DDPG הרי הלוס הוא פשוט ה-Q של הקריטיק, הלוס כאילו של האקטור הוא כאילו למקסם, הוא ה-Q של הקריטיק, אז לא כך הבנתי מה זה אומר שזה נמוך יותר. כאילו, אם מפחיתים איבר...
אז נכון, אז עקרונית אתה צודק, מבחינה תיאורטית אין הבדל משמעותי, כי שני אלגוריתמים צריכים בסופו של דבר להתכנס לפתרון האופטימלי, אבל מבחינה פרקטית זה מאוד חשוב שהלוס יהיה נמוך ויציב, אחרת הרשת לא תתכנס לפתרון טוב, וזה מה שראינו בפועל.
אוקיי, סבבה, תודה.
אוקיי.
מעולה, אם יש עוד שאלות, יש עוד זמן אולי לעוד אחת? בסדר, אז בנימין הוא גם הדובר הבא שלנו, אז זמן להתחיל.
סבבה, אני אשתף את המסך. אתם רואים את המסך? אוקיי, אז טיפה על עצמי, קוראים לי בנימין מנלה, אני עתודאי, משרת היום בתקשוב, כחוקר בצוות דאטה סיינס. בנוסף, אני גם עובד בסטארט-אפ בשם דיפ טריידינג, של ים פלג, למי שמכיר. פה אני עכשיו אציג לכם מאמר שמתאר את החצי הראשון של התזה שלי, שביצעתי תחת ההנחיה של דוקטור ארמי ביז, במסלול משולב של מחלקות לאנסטסיה וניהול, והסטת מערכות מידע בבן גוריון. המאמר פורסם לאחרונה בז'ורנל בשם Neurocomputing. אז רגע לפני שנתחיל, אני רק אתן איזשהו אינטרו קטן למי שלא מכיר את האלגוריתם Hindsight Experience Replay, או בקיצור HER, שפורסם בשנת 2017 מ-OpenAI. אז אני בטוח שלפחות רובכם מכירים את הערך ואת היתרון שבשימוש בפונקציות תגמול בינאריות, אבל יש לזה גם איזה דאונסייד שזה פונקציות תגמול שמאוד קשה ללמוד מהן, בגלל הבעיה באקספלוריישן. אז לצורך כך מגיע אלגוריתם HER, שמאפשר לימוד עם פונקציות תגמול בינאריות, ספציפית בבעיות מונחות מטרה. מה זה אומר? בעצם האלגוריתם משתמש בניגוד לאלגוריתמים מסורתיים, שלוקחים כישלון, מכניסים אותה לבאפר, פשוט לומדים מה לא לעשות. האלגוריתם הזה גם משתמש באיזה מין שיטה של מה אם. מה הכוונה? אם לדוגמה יש לנו איזשהו רובוט שצריך לדחוף דיסקית למטרה, אז בניגוד, והוא ניסה ונכשל, אז בניגוד לאלגוריתם מסורתי שתכניס את הדוגמה הזו כדוגמה של כישלון, וינסה עד שיצליח להגיע לדוגמה מוצלחת, האלגוריתם HER יגיד, אוקיי, נכון, נכשלנו עבור הבעיה, עבור המטרה הזו, אבל כן הצלחנו עבור מטרה אחרת, עבור מטרה אלטרנטיבית. אז בואו נכניס את המטרה האלטרנטיבית, זה נקרא virtual goal, נכניס את הטרנזקציה הזו עם ה-virtual goal שבפועל הצלחנו להשיג, ועם reward חיובי שמסמן שהצלחנו להשיג את המטרה הזו, בצורה כזו האלגוריתם לומד להגיע להמון נקודות במרחב, ומתוך כך גם להכליל לנקודה המקורית. אז האלגוריתם טוב, אבל יש לו כמה בעיות, אנחנו ספציפית התמקדנו בשתי בעיות שהן גם ציינו ב-Request for Research כהמשך למאמר. העניין הראשון זה איך בעצם בוחרים את ה-Virtual Goal הזה, אנחנו הגדרנו אסטרטגיה חדשה שנקראת Instructional Based Strategy או בקיצור IBS, והפחתה של ה-Bias שהאלגוריתם הזה יוצר. אז הנקודה הראשונה, כמו שאמרתי, האלגוריתם מתייחס לטראג'קטורי שבפועל הוא ראה, ולוקח את הנקודה שהוא בפועל הגיע אליה, ומתייחס אליה כ-Virtual Goal. אבל חוץ מהנקודה שהוא בפועל הגיע אליה, יש לו עוד נקודות, כל הנקודות לטראג'קטורי. ובעצם נשאלת השאלה, איזה נקודה כדאי לבחור בתור Virtual Goal. אז במאמר הם מציגים אסטרטגיה יחסית נאיבית, שפשוט בכל נקודה בוא ניקח באופן אקראי, יוניפורמי, מתוך כל הטראג'קטורי העתידי, אבל אנחנו חושבים שזה לא אסטרטגיה טובה במיוחד, לא כל הנקודות שוות, ואנחנו בעצם מגדירים לכל נקודה את ה-instructiveness שלה. כמה היא יכולה ללמד אותנו, ומתוך כמה שיכולה ללמד אותנו אנחנו מגדירים את ה-weight, שלפיו אנחנו דוגמים, במקום דגימה יוניפורמית. אז את ה-instructiveness אנחנו פירקנו לשלושה מרכיבים. הרכיב הראשון זה בעצם מה אנחנו צריכים ללמוד, שזה ההתפלגות של המטרות. אם תסתכלו פה כאילו על מין top view של מה שהיה מקודם, אז אם יש לי את המטרה, אבל המטרה היא מטרה אחת מתוך כמה. אז יש לנו את ההתפלגות של המטרות, וזה מה שאנחנו צריכים ללמוד. יש לנו גם את מה שאנחנו יכולים ללמוד, שזה חוץ מהמקום שבפועל הגענו אליו, זה גם מתייחס ליכולת ההכללה של הרשת, ואנחנו קירבנו את זה מהתפלגות גאוסיאנית, שבעצם אומרת שאנחנו יכולים ללמוד טוב את הדברים הקרובים, ופחות את הנקודות הרחוקות מהווירטואל גול הזה. אם נחבר את שני הדברים האלה, בעצם אנחנו מגיעים לרלוונטיות של הנקודה, כמה היא רלוונטית לבעיה שלנו. אבל חוץ מזה צריך גם להתייחס למה שאנחנו עוד לא יודעים. אם כי יבלנו הרבה נקודות באזור מסוים, ופחות נקודות באזור אחר, יכול להיות שנעדיף נקודה שהיא פחות רלוונטית באופן אובייקטיבי, אבל מלמדת אותנו דברים חדשים שלא ידענו עד עכשיו. אז אני לא אכנס בדיוק למתמטיקה שעשינו פה, כי מקוצר הזמן, אבל אז שילבנו את שלושת הפרמטרים האלה, ולפי זה הגדרנו את החשיבות של כל נקודה, ומתוך זה דגמנו בצורה יותר מושכלת את ה-Virtual Goals. השיפור השני שהצענו לאלגוריתם המקורי, הוא Filtered Hair, שזה בעצם, אנחנו מפלטרים, אנחנו מסירים דוגמאות שמעלות את הבייס של הלמידה. Hair באופן, כשמשתמשים ב-Hair, באלגוריתם Hair, באופן טבעי נוצר בייס, בגלל שאתה משחק עם ההגדרות של הבעיה, ואתה יכול להגיע לטרנזקציות שלא היית מגיע אליהן בעולם האמיתי, ואתה בעצם לומד טרנזקציות שלא היית אמור ללמוד, ואם יש הרבה כאלה, זה עלול ליצור בייס באבלואציה של הרשת. הסיבה שזה קורה, אחת הסיבות שזה קורה, אחד המצבים שבהם זה קורה, זה בגלל האלגוריתם מניח שהמצב שאתה מגיע אליו הוא תמיד התוצר של הפעולות שלקחת, אבל זה לא בהכרח המצב. אני אתן לכם שתי דוגמאות. בדוגמה הראשונה אתם יכולים לראות ילד שחובט בכדור, עכשיו נכון, הוא פספס את המטרה, אבל הוא הגיע לנקודות קרובות, אז אפשר להשתמש בטראג'קטורי שלו כדי ללמוד איך להגיע לנקודות שבפועל הוא הגיע אליהן, ולהכליל מהנקודות האלה למטרה אמיתית. אבל גם יכול להיות מצב אחר, יכול להיות מצב שהילד מראש בכלל פספס את הכדור, או הרובוט בכלל פספס את הדיסקית. במצב כזה, המיקום של הכדור הוא לא התוצר של הפעולות, אלא פשוט התוצר של ה-initial state. בצורה כזו נוצר איזושהי טרנזקציה מוזרה כזו, של state action reward state, גם כאילו, וגול, כי בכל טרנזקציה מגדירים את הגול שרצינו להגיע אליו, מגיעים לאיזו טרנזקציה מוזרה עם virtual goal שהושג כבר בטרנזקציה הקודמת. בעצם ככה גם הגדרנו וככה פילטרנו את הדוגמאות האלה. הוספנו תנאי לאלגוריתם, תנאי ממש פשוט אבל שנתן בוסט רציני לביצועים, שאם ה-virtual goal הושג כבר בסטייט הקודם, אז אנחנו מתעלמים מהדוגמה הזו ולא מכניסים אותה לבאפר. במאמר גם הוכחנו ברמה המתמטית המוטיבציה עם שימוש ב-important sampling, למה בעצם זה נכון לעשות את זה. אבל בכל מקרה זה שיפור מאוד קטן לאלגוריתם, שורה אחת, if אחד, שנותן בוסט רציני לביצועים. כדי לבחון את האלגוריתמים שלנו, בנינו 3 סביבות חדשות, לא יכולנו לבדוק על הסביבות המקוריות, כי הן לא תתאימו לאלגוריתם של IBS, כי הוא צריך התפלגות שונה ל-initial state ול-goal distribution. אז בנינו 3 סביבות חדשות בפייגם, לא פחות קשות. הסביבה הראשונה, הסביבה הפשוטה ביותר, זה hand task. יש לנו יד שמסתובבת במרחב עם שליטה על ציר ה-X וציר ה-Y. היד צריכה להגיע לכדור, להיסגר מעל הכדור, ולזרוק את הכדור לכיוון החור השחור. המלבן האדום זה בעצם טווח התנועה של היד, איפה הוא יכולה להגיע. והמלבן השחור זה ה-goal distribution. היד צריכה לזרוק תוך התייחסות לגרביטי שכל פעם מופעל על הכדור. המשימה השנייה ברמת הקושי שלה, דומה מאוד למשימה הראשונה, אבל עכשיו יש לנו קיר בין היד ובין החור השחור. כלומר, היד צריכה ללמוד להשתמש יותר בכוח המשיכה ובקירות מסביב כדי להצליח להגיע למטרה. הסביבה השלישית יותר מדמת סביבה של real world scenario, שבה יש לנו רובוט, זרוע רובוטית, שאפשר לשלוט לה ב-joint velocities, ועל ידי שליטה ב-joint velocities אנחנו רוצים להביא את ה-end effector לכדור, לתפוס את הכדור ולזרוק אותו לכיוון החור השחור, שוב על ידי שליטה ב-joint velocities. על כל אחת מהסביבות בדקנו את 4 הקומבינציות, שזה ונילה הר, האלגוריתם המקורי, הר עם IBS, filtered hair ו-filtered hair עם IBS. כל קומבינציה כזו הרצנו 10 פעמים על כל סביבה כדי להגיע לתוצאות יותר רובסטיות. אתם פה יכולים לראות את הריצה, כמובן בצד השמאלי העליון זה האלגוריתם המקורי, השמאלי הימני העליון זה עם IBS, התחתון זה filtered hair, ואחר כך זה filtered hair עם IBS, כמובן שבהתחלה לא מצליח בכלל לפתור, אבל אחרי 50% מהאימון, האלגוריתם שלנו כבר מגיע ל-44% הצלחה, בניגוד לוונילה הר שמגיע לרק 2% הצלחה. אחרי 100% מהאימון, ונילה הר עדיין תקוע על 3% הצלחה, בעוד האלגוריתם שלנו כבר הגיע ל-75% הצלחה. אם נסתכל רגע על הגרף של הביצועים, כשציר ה-X זה סייקלס, כל סייקל מכיל 16 אפיסודס, וציר ה-Y זה success rate, כלומר כמה מתוך האפיסוד בסייקל הסתיימו בהצלחה. אתם יכולים לראות מהגרוע לטוב שהוונילה הר נשאר ממש על האפס, הר עם IBS היה קצת מעליו, פילטרד הר מעליהם, ופילטרד הר עם IBS הביא את התוצאות הטובות ביותר, עם כמעט 80% success rate. הקו המודגש חשוב להגיד זה התוצאה החציונית, והצל זה בין האחוזון ה-33 לאחוזון ה-66. בבעיה השנייה, אפשר לראות תוצאות דומות, כמובן בהתחלה מן הסתם אף אלגוריתם לא יצליח לפתור את הבעיה, אבל אחרי 50% מהאימון, האלגוריתם שלנו כבר הגיע ל-60, אתם רואים את זה או מניח שרואים? האלגוריתם שלנו כבר הגיע ל-13% success rate אחרי 50% מהאימון, ואחרי 100% מהאימון, כל האלגוריתמים עדיין נשארו על 0% הצלחה, חוץ מהאלגוריתם שלנו, השילוב של שני הפתרונות האלה, שהצליח יחד לפצח את הבעיה, ולהגיע ל-42% הצלחה. שוב אפשר לראות תוצאות דומות גם בגרף, שכל האלגוריתמים יחסית תקועים על 0, ורק השילוב של שתי הפתרונות מצליח לפצח את הבעיה, ובצורה קונסיסטנטית להגיע לתוצאות גבוהות בהרבה. המשימה השלישית, שוב בהתחלה כל האלגוריתמים נכשלים. צריכים
לסכם רק, להתחיל לסכם.
כן, אני בדיוק מסיים. ואחרי, בסוף האימון, הפתרון שלנו הגיע ל-35% success rate בהשוואה ל-5% בוונילה הר. אותו דבר אפשר לראות גם בגרפים. וזהו, אז לסיכום, הבאנו שתי פתרונות, שתי שיפורים לאלגוריתם הר המקורי, שמצליחים לשפר משמעותית את הביצועים. תודה רבה, ושאלות?
זמן לשאלות, זמנים להרים יד בפרזידנס. טוב, אני רואה שאין שאלות, אז בואו נעבור לדבר הבא, דין צדוק.
Good morning, everyone. Can you hear me and see my screen?
Yes, both.
Okay, great. My name is Zadok. I'm a graduate student at the Technion from the Computer Science faculty. I'm here to present you a paper that I've been working on under a research internship at Microsoft Research under the supervision of Dr. Daniel McDuff and Dr. Ashish Kapoor. And the name of the paper is Modeling Effect-Based Intrinsic Rewards for Exploration and Learning. To get this done in 10 minutes, I try to change a bit the structure of the presentation, so bear with me. So what we were trying to do is to create a policy that will investigate the things that we can learn from infusing an intrinsic reward that is based on a positive emotions, just as curiosity and satisfaction. So our paper is basically about building a policy that is based on the effect-based reward, using it to collect data and pre-chain general representation. and then create experiments that will show that we can solve downstream tasks, which means like computer vision tasks such as depth estimation, sense segmentation, and another generative task, and then show that a model that is being built from a better data set can solve those tasks just more efficiently. So what do we mean by curiosity and satisfaction in terms of exploration? Spontaneous smile behavior has been linked to curiosity and satisfaction when driving in the field in other papers. And we wanted to show, so what we did is to collect data set from a couple of subjects in which we recording them while they're exploring the field. And then we used those spontaneous smile gestures to understand their satisfaction from exploring the field and how the human acts, and we want to use it as a reward for some policy. So what we did is to take, instead of building on general reinforcement learning algorithms, what we did is to take an off-the-shelf policy and just add a reward as another decision-making structure. So basically what we have is a base policy, which is a very simple policy, which when it's on imitation learning, the policy gets an input, which is basically an image, an observation image, just like in reinforcement learning, and outputs a vector of probabilities for each of the actions. So our task is just to choose the action with the highest probability, and this is how we explore the field. What we did is just to add a simple component in which we add another factor of the reward function, which means that for each one of the predicted actions, we want to compute the reward for it. And then the decision will be made by the linear combination between the reward and the policy itself. So this is, of course, not exactly feasible in real-world scenarios, but this is in simulation. It is feasible, and theoretically, it managed to. We can show how how it can affect the results of the policy. So the environment that we were using is just a simple maze. The maze is constructed of walls from different sizes and random cells, so it will be different from one step to another. And the agent itself is a small vehicle that can maneuver between those cells and has 5 actions for the execution in which he must choose from. And this is how exactly we were experimenting and exploring the field. And now we will get just back to the results, and we will discuss how we've managed to get some results. So basically, when we talk about coverage, what you can see here is that the vehicle is exploring, and what we relate to as coverage is a circle surrounding the agent with a radius of 3 meters. So we evaluated our model with a basic imitation learning model, and a previous work that was done by the co-authors, and some other very simplistic policies, just like random driving and stray driving. So what you can see here is that we measure the average duration of each policy. What do we mean by average is that we executed it for a large number of trials, that's like 30 times. And for each trial, we measure the duration in seconds, the coverage in squared meters, the coverage is the same circles I was talking about, and the average coverage per second, and of course the collisions, which is just like the termination of each trial. So what you can see here is that IL plus one is actually a previous work that was done by the same co-authors, and this talks about negative reward, which is based on fear, and it's nervous signals that are based on just like negative based reward. So you can see here that when we are trying to play safe, the model does hold on for longer times, but when you can you can take a look at the coverage and see that actually it was exploring less of the field on average. And what we saw is that sometimes the agent itself doesn't know how to get out of dead ends and circling around dead ends, and the effect-based reward is able to explore the right way to get out of the dead end. So it was really interesting to see it, and you can see the huge difference between the coverage per second between IL+1 and effect-based. Another way to show it is the heat map of the vehicle when we randomly put it in the environment. The map is on the left. The green area is the navigable area in which we sample random points to start from. And you can see how the more the policy gets better, the more the heat map gets more less sparse and more explorative, and we can see more just more trajectories that were performed by our agent. Another way to show it is just a small example of what happens when we get into a point in which we can turn left or right, and the decisiveness of the policy is that sometimes the policy can be undecisive and doesn't know where to turn, and what it will result in is just in a collision, but where the reward itself is being more about what's the right path to explore and what path looks more interesting to me in a more intrinsic manner, then the effect-based is clearly more influencing in this scenario. The last one, and we just wanted to show how the effectiveness of using the data that was collected from those trials. And the data set is just the images were captured from the camera that is on the vehicle. We used a variational autoencoder to learn the presentation of the data set. So we used each one of the policies. And what we did is to start by training for frame reconstruction, in which we just want the model to reconstruct frame from the environment, and we did it for all the policies that we are evaluating on. And following that, we wanted to see how we can use it to solve downstream tasks. So basically, if we take a variational autoencoder and then we retrain only part of it to solve another task, which can be just like depth estimation, you probably can't see it, but there's a depth map in here showing a slightly the wall that is coming in front of us, and scene segmentation that can allow us to segment the walls, and sketch to image translation, which is a more generative task that if we give contours to a model, then how can we regenerate the image? And here we can only retrain the encoder. So this is what we did, and what we want to show is how much episodes we need on average for each one of the policies. And what we saw is that on average, for longer policies, the data set that is being recorded from the effect-based policy is giving a better loss on average for a short number of episodes. Of course, that the gap is being smaller the more we add more episodes. So the data set is being built. And that's it. And one more thing. So this is just examples of what happens if we just try to show on what examples do we have mistakes on our end and on imitation learning, for example. And we can see that on better representations, we can see a better contours of the walls. And sometimes the representation itself didn't even get exactly the representation of the structure of the upcoming environment, just like here, in which we can see a different wall on the side, or of course the depth itself can be seen as more accurate on a better representations. That's
great. Thank you, Dean. If anyone has any questions, that would be great. Omri.
Hey, great talk. I see that you use the Unreal Engine, as do we in our company. I just wanted to ask, in terms of how fast can you train? Like Unreal is like a real time, and yeah, you can just speed up a bit the world time, but usually it's not enough, and usually you need to train lots of agents in parallel. So how did you approach that? Like, I know it's technical and not related to...
That's a great question, actually. This was half of the work was on investigating the reinforcement learning algorithms that were done, and we were trying so many times. Yeah, I mean, my advisor, Ashish Kapoor, is the one who made SIM and has a long road on reinforcement learning algorithms to SIM. Basically, we found out that after 48 hours of DQN with TensorFlow, you get something that is still much less better than a simple imitation learning model, and we want to show the effectiveness of the reward itself. So this is why we built a policy that is based on imitation learning and not reinforcement learning. But you're correct. I mean, some policy like that will take a couple more days. There's also an implementation for distributed reinforcement learning that can be uploaded to a batch of servers and shorten the time, but that was...
Okay, but this means that if you use DQN, that means that you add a discrete action space, and if I remember correctly, you can control this car continuously from -1 to +1 with the wheel.
Yes, you're correct. But what we did here is just to simplify it and use a discrete action space for the imitation learning as well. The code is available and the paper is available too. I can show you everything if you want later on.
Okay, thank you.
Sure, you're welcome.
Thank you, עמרי. תודה דין. אנחנו נצא להפסקה של 10 דקות. נחזור ב-11 לקיינות של אביב תמר. טוב, ברוכים השבים, ותודה שחזרתם אלינו. שמח להציג את אביב תמר. אביב הוא חבר סגל בפקולטה להנדסת חשמל בטכניון. הוא עשה את הדוקטורט שלו גם בטכניון, סיים לפני כמה שנים, והיה בפוסט-דוק במעבדה של פיטר אביל ב-UC ברקלי. אביב זכה במספר פרסים, בין השאר ב-Best Paper בניפס 2016 על מאמר Value Iteration Networks, ובמקרה הוא גם המנחה שלי, אז אני מתכבד לאביב את הבמה מכאן.
תודה רבה, אור. תגידו, אתם רואים את המצגת ושומעים אותי?
גם וגם.
אחלה. I'll switch to English now. So today I'm going to talk about learning to plan and planning to learn. And well, it's an RL day, so you know that RL is about sequential decision making, and you probably have heard about some of the application that we have for RL. And well, you know, in general, for solving decision making problems, we have two main approaches. One is through reinforcement learning, another is through planning. And by planning, I mean methods where you first kind of define a model of your problem. So here is an example of a PR2 robot that is trying to set up a dinner table. And our model for this problem consists, for example, of the states of the robot and the world, its configurations. And in this model, we assume that we know how our actions are going to change the state of the world and what they're going to do. And once we have such a model, or we can kind of ask questions like, what is the sequence of actions that is going to bring the robots to a particular configuration or set up the dinner table, etc. And this is a very well-studied problem. It's been studied in various different disciplines like classical planning, task and motion planning, optimal control. We know a lot about this problem. These fields are mature. We have off-the-shelf algorithms, have guarantees, almost everything we want. But the problem is that, well, the reason that we're not done with sequential decision problems is that in most cases, it's very hard to define these models. So what should be the state space, for example, for a deformable object? Or how do I map for my perception system to a very convenient state space? Or, well, knowing the dynamics models in many problems is very difficult. And even if you have all of these, just doing the planning computation could be sometimes too slow for you to handle. An alternative to this manual modeling that has, dominated many other decision-making fields like object detection and speech recognition is to rely less and less on models and more on deep neural networks that map raw inputs directly to decisions. And for decision making, we can also do this. This is what you know as reinforcement learning or imitation learning. We're going to take our whole decision making algorithm and just replace it with a deep neural network that maps our observations to some actions, with the hope that this neural network will learn to pick up on the important patterns in our data that lead to good decisions. And how can we train some decisions? Well, we can do reinforcement learning, train it by trial and error. And if you have some expert, you can do imitation learning. Maybe you might think that training a decision-making system using trial and error is a very weird thing to do. But the beautiful idea here is that by removing ourselves from the need of a model, we can let the neural network pick up on the important signals in our data that lead to good actions. And this is sometimes very difficult to do manually. Of course, well, if you're here, then you know that our job is not done. Reinforcement learning works with a lot of handcrafting, and there are several difficulties. For example, the decisions that we get are generated by some black box neural network. It's very hard to get generalization to different problems. And training this often requires a lot of data and time and expert reward design. And getting RL to work is an art by itself. So let's for a second look at humans to get some inspiration. It's clear that we learn from trial and error, we process raw sensory inputs, but we also plan. You can see this when we make once-in-a-lifetime decisions, but we also do this every day because trial and error is, let's be honest, is quite a bad approach for making decisions or learning decisions. And obviously, we can generalize pretty well. Usually, once we see a new problem, we can solve it in a single or just a few attempts. We're going to ask the question how to combine planning and learning to design algorithms that generalize better, are more interpretable, and more efficient. And specifically today, I'm going to talk about two main topics. The first is how can we use neural networks to learn planning computations? And the other is how can we use planning to improve our learning? We're going to do this using a Bayesian reinforcement learning formulation. I'm going to start with learning to plan. I'll start with some background. I'm sure you all know this because this is our reinforcement learning day, but I'm going to go over it quickly just for completeness. So in RL, we have formal definition is a Markov decision process. We have states and actions, transitions. Our goal is to find a policy that minimizes the expected sum of costs. And this is what actually makes this a sequential decision process, because we need to take into account how our actions affect the cost that will appear later on in the state that we're going to arrive in. A very important concept in RL is the value function, which is the minimum sum of cost, expected sum of cost that I can get from a particular state. And Bellman's equation is a very important concept that tells us something very nice. It tells us that the value function of a particular state is equal to the immediate cost that I can get plus the best value function that I get from the state that I reach. So it's easiest to see this in kind of this navigation example, which means that the value of a state is the immediate cost plus what is the minimum sum of cost from the next state that I reach towards the goal. Another thing that we're going to talk about in this talk is neural networks, in particular convolutional neural networks. And probably you all know this, a convolutional network, well, it was designed for object recognition tasks where you get an image and you try to identify what is in the image. And usually it works by processing the image by a sequence of feature extractions by convolutions and dimensionality reduction using, for example, max pooling. And at the end, we kind of stack all our features together and have some linear mapping that gives us a probability of the output of what is in the image, a class of an object. And once you train this using supervised learning, we know that these feature maps tend to learn up useful features. For example, edges and corners in the lower layers and object parts in higher layers. Right. So we're going to first ask whether neural networks can learn planning computations effectively, and how can we use that? So remember that we said that we're going to replace planning with this neural network. Think of this convolutional neural network that just maps our observation to an action. And now instead of asking what is the class of the object in the image, we're going to ask, given this observation, what action or what probability of action should I take? In order to train such a network, we need something to back up on. And in reinforcement learning, this could be minimizing the expected sum of costs. That gives us one signal. In mutation learning, we could look at our data and try to maximize the log likelihood of the good actions, for example, the actions that an expert took given these particular observations. And the thing is that in both of these cases, our data tells us the tasks that we train on. So we know, or we have some signal about what to do in the particular task that we saw in our data. The question is, how do we generalize to different tasks? So how does the neural network know what to do when the task changes? And when we look at this problem, we wanted to kind of ask the simplest question we can think of. We threw these neural networks at probably what is the simplest problem in RL. It's called the grid world. In this grid world, there is this red object that needs to navigate to this green goal position between these black obstacles. And the neural network can see everything. It sees the map, it sees the starting position, the current position, and the goal position, and it just needs to output a particular action to take. And we trained this on supervised learning, orientation learning from shortest path, using a network that, well, at the time it was considered deep. Calling this a deep network these days is probably a joke, but these very similar networks were used to solve Atari games at the time. So we thought, well, why not just apply to these very simple grid worlds? And when we tried this, we trained it on various different maps that were randomly generated. And the neural network was pretty good at solving all these training maps. But when we gave it a test map that it hasn't seen before, it really wasn't good at that. So it couldn't kind of pick up the very simple logic in this problem, which is go around the obstacles towards the goal. So we wanted to ask why this happens and kind of find a solution towards it. And our inspiration came from inverse reinforcement learning or inverse optimal control, where the idea is that, well, we thought that what should happen here is that the network should kind of look at this observation, this map, figure out some kind of model, which is, there are some obstacles and some free segments, and then planning that model a trajectory towards the goal, and that should give it an action. And then if the observation changes, the model will change and the plan will change as well, and then we should be good. The question is how to derive such a model using a neural network and how to grapple through it. Let me tell you about a particular way to do this, and a particular planning algorithm that we used. It's called value iteration. Value iteration tries to calculate the optimal value function by an iterative procedure where in each step of the algorithm, you go over all of your states and update your value function estimate by minimizing the cost toward a particular neighbor in your system. Here, we just one of the neighboring pixels in this map, plus what you think currently estimate is the value or the shortest distance from that pixel towards the goal. If you have stochastic conditions, this is very similar. You just need to kind of take an average over your neighbors and x values. And when we looked at this kind of computation that goes on in value iteration, our insight was that this is very similar to the computation that goes on in a convolutional neural network. What you actually have here is a sequence of linear operations, sort of convolutions, and then maximization or minimizations in this case, which is kind of similar to max pooling. So you can actually write, for this particular instance of a grid world, the value iteration algorithm exactly is a particular type of recurrent convolutional neural network, which maps from your current value estimate and a cost using these convolutions, which are actually corresponding to the transitions in your model, to some new value function by taking a minimization over the particular action that you took, and feed this back into your current value and repeat. And the computations that you get here are exactly the computation that you get when running the value iteration algorithm. You can actually generalize this idea. It doesn't have to work on grid worlds because what you have in value iteration is just a combination of minimizations and linear operations, which we know that we can backprop through. So with this understanding that this particular planning algorithm is equivalent to the computation that goes on in a ConvNet, we went on to design something called a value iteration network, which takes as input your observation, maps it to some reward function using a Shannon ConvNet, then applies this planning computation, and then from that planning computation output, the value function, it outputs an action. The question is what happens when we train this on our data? So what we're actually learning here is how to map our observation to a planning computation so that the output of planning in this in our learned model would mimic the actions that we saw in our data. When we ran this on different maps in this grid world setting, we got significant better performance than these reactive neural network baselines that we tried. The reason is that, well, on small maps, everything kind of works because you kind of memorize the possible trajectories. But once you increase the map, this doesn't scale well. And the value iteration network actually learned the underlying logic of the computation much, much better. Here's an example. In red is what our neural network predicted, and in blue is the actual shortest path. So you see that it didn't learn the actual shortest path, but it learned the underlying logic of the problem, which is go around obstacles in a quick way towards the goal. And we can even interpret what it learned here, because we can visualize the reward that it learned. Now, and you see that it learned to give a high reward at the goal, negative reward on the obstacles, and a small negative reward in all the free space, which leads to calculating a short path towards the goal. Now, I emphasize, this wasn't given as input at any point to the neural network or the training algorithm. It learned to pick this up because this is one way to explain how shortest path trajectories are formed. Varied networks were then used in various follow-up works. For example, even on this grid world setting, people use it to, for example, navigate in buildings from first-person view, as you see here, and navigate in dense crowds, autonomous driving application. The idea that you can actually backprop or differentiate through a planner is a bit more general, and we have applied it, for example, for MPC using LQR planner, and other researchers have applied it to various different other planning algorithms. The main point in all of these works is that once you have some good idea of what planner is suitable for your problem, this inductive bias is can generate a very significant boost in performance. Of course, this is not a silver bullet. Sometimes you don't know what is a good planner for your problem, and then this probably won't work well. Right, so now that we understand that neural networks have a fundamental capability to represent planning computations, we can ask how to use that. What we've looked at is how to use neural networks to increase the speed of planning computations. So the idea here is that in many cases, you want to solve similar planning problems. For example, think of this robot that needs to navigate this warehouse. Maybe every day it would need to navigate to a new position, and maybe some of the obstacles are going to be different, but we're not going to change too much about the warehouse. Now, a standard planner that needs to solve this problem, we treat each planning problem and solve it from scratch. What we can do instead here is we kind of replace the planning algorithm by a deep network, train it offline on many solved instances of these problems using, say, imitation learning or reinforcement learning. This would take a long time, but then once we see a new problem, we just run a forward pass of the network. This is very fast, and we get an output. We should potentially also use it as a heuristic to improve standard planning algorithms, and I'll show exactly how. But first, let me just convince you that this can actually solve interesting problems. So on the right here is a motion planning problem from our RSS paper. And you see, this is a 4 degree of freedom arm that needs to navigate to the yellow goal here. And you see, it can navigate between very dense obstacles. On the left is a problem called Sokoban. The idea is that you need to move these purple objects to the green goal positions by the red agent, but the agent can only push them. So this makes for kind of an interesting planning problem where you don't want to get stuck in corners, for example. And what you see here is just the output of a trained neural network that was trained using imitation learning. And you see that it exhibits something that looks like very long-term planning, at least 30, 40 steps into the future. So the point here is that if you think about the architecture well, these neural networks have some capability to represent non-trivial planning computations. What you should be asking is how well this works. And I can give you some numbers. Here's an example. If we train it on 9,000 maps, we solve 97% of problems in Sokoban with one object and 87% of problems with two objects, which are much harder. What does it say? It's a bit hard to interpret what these numbers mean. I think a more informative measure would be, well, if this neural network really captured the patterns of how a good plan looks like here, we should be able to use this knowledge to improve standard planning algorithms. For example, using a heuristic. This would give us 100% success rate guarantee if our planner is complete. But then we can ask, well, how does this heuristic improve our planning speed or the planning quality? And this is what we did here. On the x-axis, what you see is the planning length. This is a measure of the quality. We want it to be as short as possible. And on the y-axis is the number of states that we explore during the search. And of course, we want this to be as low as possible too. This green dot represents the llama planner, which is an optimal planner, which we use to generate our data. Obviously, it generates the shortest plan length, but it also takes a very, very long time. You can see here that the y-axis is in log scale. A star that uses our neural network as a heuristic does almost as well in terms of quality, but several orders of magnitude faster. So this shows that the neural network really did pick up some patterns of how a good plan looks like here. We really wanted to interpret what the neural network learned here. How does this good plan look like? When we try to do this using some techniques to figure out what the neural network learned, well, we didn't really have much success. Apparently, it's very hard to interpret what deep learning does. But we did have one interesting insight. So here is a graph that shows on the left the distributions of all the planning problems that we can solve. And on the x-axis is the length of the plan. And on the y-axis is the success rate of our neural network in trying to solve this problem. And you see that, well, this is expected. The longer plans are actually harder for the neural network. This makes a lot of sense. On the right plot, however, the y-axis is the same, the success rate of the neural network. The x-axis is how long the planner takes to solve this problem. And again, it's kind of a monotonically decreasing, which makes sense, but there's a very strange anomaly here. There are some problems that are very easy for the neural network, but very difficult for the planner. Maybe, can you guess how these problems would look like? And I'll give you an example. Here's, on the top is a map that the llama planner takes a very long time to solve. And on the bottom is a plan that it takes very short time to solve. So I think that the map on the top looks at least much easier. And the reason is that there are a lot of open spaces, which intuitively makes for an easy problem. But for the planner, it also means that there's a very high branching factor, which leads to slow planning. I find it kind of comforting that the neural network will kind of figure out how to use or identify that these open spaces are actually easy, so that when using that as a heuristic, the planner takes, when the neural network kind of picked up that these easy problems or open spaces are easier to solve. All right, to summarize this part, by thinking about the architecture of neural networks, we identified architectures that are suitable for planning computations, and we see how to use this to improve standard planning and how to use neural networks that learn planning computations. Next part of the talk is going to be about some newer research about subgoal trees. Let me just motivate it. Well, we spent some time thinking about this problem of learning to plan. And after thinking about it for some time, we identified it's something a bit odd in the way that we were approaching the problem. The reason is that planners are, in principle, multi-goal. They need to solve any goal that you give them. But reinforcement learning is actually a single goal formulation. If you think about the MDP, we have a single cost function. How did we resolve it so far? Well, we just added the goal as part of our state observation. And then we train it using reinforcement learning. But then we ask whether this is actually the optimal thing we can do here. So I think that not. And let me give some motivation from deterministic problems. So in deterministic MDPs, the value iteration algorithm is exactly the Bellman-Ford algorithm for finding a single goal shortest path problem. And we know that this has a worst case running time of n cubed. By attaching the goal as part of the state, we effectively run Bellman-Ford for each possible goal in our system, which has a worst case running time of n to the power of 4. And this is the approach that we did, and this is the approach that many popular algorithms in reinforcement learning do, like Hindsight, experience replay, universal function approximators, and many, many others. But the catch is that, well, at least for deterministic problems, we know that we can do much, much better than n to the power of 4. So an all pairs shortest path algorithm like Floyd-Warshall can solve the problem in n cubed. This means that there is some structure in the problem that we're missing out on when we're trying to solve it using the standard reinforcement learning formulation. What we're going to suggest is something almost heretical. We're going to ask, well, let's forget about the Bellman equation and try to derive a different formulation of reinforcement learning starting from a different first principle, the all pairs shortest path. And let's see if that can give us a framework that will solve multi-goal RL with some advantages. Let me first give a bit of definitions. We're going to consider the all pairs shortest path problem on a graph. We have a directed weighted graph where the costs are the edges between the nodes. We assume that the costs are non-negative. We have n nodes, and the cost from a node to itself is 0. And the graph is fully connected. So if we have an unconnected edge, we replace it with a very high or infinite weight. Our problem is to solve for the shortest path between any state, any node and any other node in this graph. What we're going to do is we're going to define a dynamic programming principle for this problem that's going to be compatible with function approximation for using reinforcement learning based on a new dynamic programming idea that we call subgoal trees. What is a subgoal tree? Well, it's a new way of representing a trajectory. And let me motivate it. So how do we represent a trajectory or think about a trajectory in the standard reinforcement learning formulation? What we do is say, given a goal in my particular position S, what is the next state in my plan? And after I figure that one out, I ask what is the next state and what is the next state and so on. And this is how I derive a complete trajectory. In subgoal tree, we're going to ask something different. We're going to ask, given my state and the goal, what is the middle state between them? That's going to break up our problem into two different and independent problems. And we're going to ask what is the middle state in each sub-trajectory. And so on, using this divide and conquer principle. And once we figure that one out, we're going to get a complete representation of our trajectory. The next thing I want to do is we're going to write down a dynamic programming principle, something like the Bellman equation, but for subgoal trees. So we're going to define the value B sub k of a pair of states as the shortest distance between them in 2 to the power k steps or less. And what this satisfies is this equation shown here in purple, which reads that the shortest path between, say, two pairs of a pair of states in, say, 16 steps or less can be written down as the shortest path that goes through some waypoint SM, where this waypoint is 8 steps or less from the start and 8 steps or less from the goal. And obviously, if we take k to be 0, in one step, we can only get the actual cost. This is the first line here. So this gives us a new dynamic programming equation for subgoal trees. Now we can ask what is the computational complexity of this or running subgoal trees, And because the longest, shortest path in any graph could be at most n nodes, then we only need to run this dynamic programming iteration for log k times or log n times. And in each iteration, we go over all our states, we go over all our middle states and over all our goals, and that gives us n cubed log n. So this in principle is much better than n to the power of 4, which is the standard approach in using the Bellman equation. So there is some promise here that this approach will actually be better. And I'll say that this dependence on k is going to be very important in a few slides when we're going to analyze the error propagation. Okay, so what we really care about in RL is how to handle large state spaces using function approximation. And the question here is, how does this dynamic programming formulation handle approximation? What we're going to ask is, given that we apply this subgoal tree operator T, which does exactly what we've seen before, and we have some error when we apply this operator, how does this error propagate once we run the dynamic programming iterations? So if you look at this equation, in the first step, each of these segments is going to have some epsilon error. Once we apply this, that means that each value function here can have at most epsilon. So this combination or this addition is going to have at most 2 epsilon. And once it's again, we have at most 4 epsilon and so on. Since we run this log n times, we have n epsilon in total. If you run the standard Bellman equation, error propagation, at each step you get at most epsilon from this value function because it only appears once, but you run the algorithm for n times, so you get again n epsilon. So at least it looks like the error propagation is very similar. But the real question is what happens about when you try to use this approximate value function to derive a trajectory. We're going to be greedy with respect to this value function, and then once we calculate the error in the resulting trajectory, what we need to sum is the sum of errors that we get. So here in the subgoal tree, in the first subgoal, we're going to have the biggest error, but then in the subsequent subgoals, we're going to have half of that, and then half of that, and so on. And once you sum these errors, you get n log n. In contrast, for the standard Bellman equation, the first state is going to have the largest error. The second one is going to have n-1 epsilon, and so on. This decrease is linear. So once you sum that up, you get n squared epsilon. What this means actually is that once you use subgoal trees, you have much less drift when you try to use your approximation to derive a trajectory. There's a very strong advantage to using subgoals, at least in goal-based reinforcement learning. This is something that is kind of a thorny issue in RL. We all understand that subgoals are a good thing, but it's very hard to prove that this actually happens. Okay, once we have this formal framework, we can go on to derive algorithms. I won't go into the details, I'm just going to show you results. So this is kind of an adaptation of fitted Q learning to this subgoal tree operation. The only difference is that you replace the dynamic programming equation for Q learning with the dynamic programming equation for subgoal trees. And here's an example in a kind of a simple 2D continuous maze. So what we show here are these subgoal tree value functions for the different Ks. So remember, K kind of encodes the reachability. And what we show is the value function for reaching a goal that is here at the top right corner. And we see that once we increase K, we can reach the goal from more and more positions in this maze. And for a large enough K, we can reach it from anywhere in the maze. And the value function is kind of smoothly increasing, smoothly increasing function towards the goal along this path. We compared our algorithm to a very equivalent algorithm based on the Bellman equation, and we got much better results. And it turned out that at least this really corresponded to our theory, because what the standard algorithm learned is something that, well, it could solve for very short goals, but for very distant goals, it completely didn't know what to do, just wandered around and tried to avoid obstacles, which is derived from the fact that once you use an error, or you have an error in your value function, this could be very detrimental to your algorithm that tries to use this value function to figure out the actions. You can also derive policy gradient formulations of the problem using neural networks, to use neural networks. So you can write down, you can think of a policy, stochastic policy that selects a sub-goal given a start and a goal. And you can write down a policy gradient formulation for it where you try to maximize or minimize the expected cost using your trajectory. And you can read our paper. It breaks up very nicely using something kind of similar to the standard policy gradient theorem, but with a different breaking of the trajectory into sub-goals. And you can apply all the standard tricks that we know from policy gradients, like baseline, structuring, etc. And we did that for a problem that, for motion planning for a 7 degree of freedom robot arm. You see here, we want to kind of move between every possible state to every other state, represented as blue and red dots here. And we're going to predict sub-goals and use some linear motion between the sub-goals. The question is how to predict sub-goals such that linear motion doesn't hit the wall and the robot doesn't hit itself during the motion. And here's an example. This is the starting state. This is the goal. And these are the sub-goals that predicted. And you see that once you execute the motion, you get using a linear trajectory, you get that it moves towards the goal without hitting the obstacles. And this last transition, it seems quite long, but actually this is interesting. The neural network learned that this linear motion is okay between these 2 points, so this is a feasible sub-goal. We compare this to other approaches that are not based on sub-goal trees, and we got much, much better performance. And here's an example of this working on different goals and different starting positions. This was the whole point here, to show that this actually works on various different goals and various different starting conditions. All right, to summarize this part, we propose a new framework, new reinforcement framework that is suitable for goal-based planning, which has a very different first principle, which is the all pairs shortest path problem. We proved that this is more efficient, and this is a basis for many different algorithms and new theory that can be developed for this setting. In the future, we're going to look at stochastic systems. This is a challenge, and how to devise exploration strategies for this. And there's a recent work from a group at Berkeley that use a very similar idea using images, planning in image space. Right, we've talked about learning to plan. Next part of the talk is going to be about planning to learn. And let me motivate this with an example. Why should we plan to learn? So let's consider a very simple setting where you have a particle that needs to navigate to some goal. This is a 2D domain. And if you run reinforcement learning on this problem, well, what it would do is eventually, well, in the beginning, it doesn't know where the goal is. It would randomly explore. Eventually, it will visit the goal, and then it will learn kind of zone in on it. And at the end, it would learn to go directly towards the goal. Now, what if I told you that you don't know exactly where the goal location is, but you know that it's going to be somewhere on this half circle? And the way I'm telling you this is that I'm giving data for many different RL agents, each one trained to solve a different goal on this half circle. And you get all the training logs from this. Can you design an agent from this data that solve this problem much, much better than this naive exploration that we saw earlier? Well, here's one thing you can do. This is very simple. From this data, you can kind of figure out where the goals could be, which is somewhere on this half circle. Then what you can do once you see a new problem is you can sample some possible goal from this distribution, pretend that this is the correct goal and try to go there, and then update your posterior probability That means that if you actually saw the goal, that you know that you should go back there. If you didn't see the goal or reward there, then you know that you should never visit that place again and go somewhere else. This is actually an instance of something called Thompson sampling or posterior sampling, which is one way of solving this problem. And it looks like a very reasonable approach to do in this setting that I told you, because at least the trajectory that we want to learn look very much like the trajectory that we have in our data. And several works start to do this in this offline setting. Now, but what I claim is that this is not the optimal thing what we want to do here. What we really want to do is explore along the half circle. I mean, what I would do is that I would go do something like this, search along this half circle until I find the goal. And that's why I identified it, I would want to go directly towards it. This is much, much more efficient than just naively searching for a goal on this half circle. The problem is that this is much harder to do from our data. This is called Bayes optimal exploration, but the reason that it's much harder to do is because this trajectory looks very different than the trajectory that I have in my data. So this seems like a difficult problem. Before we show how to solve it, let me convince you that this is actually a good problem to tackle. I think it's actually one of the most important problems that we want to solve right now for several reasons. The first is that collecting offline data, which is the setting that we have here, we first train standard agents, we get the data, and from this we want to figure out what is the exploration strategy. This is a very safe and manageable way for many, many applications. And in many applications, exploring from scratch is just too slow to be of any value. And the idea of a task, like a goal position, is very general. It doesn't have to be a goal position. It could be a particular robot type. It could be a profile for a patient. For example, think of a medical application. We want to suggest a treatment for a patient, but we don't know the patient's condition. So we need to kind of figure out actions that tell us some information about the patient and quickly, and let us solve his problem. In an online shopping application, for example, we don't know what the customer wants to buy, but we don't want to spend too much time. We want to quickly suggest items that give us some information about what is, or kind of lead us fast to making a deal. So in all of these problems, we have offline data, and we want to learn to explore very, very quickly. I'll quickly go over this. So in standard RL, we have kind of two ideas for exploration. The standard setting is that we don't know anything about the problem. This is what we usually do. And the idea there is that we don't want to waste time on states that are either not informative or don't have reward. And then you can write regret bounds or path bounds for these problems. The problem is that usually these methods are just too slow to be practical. Another approach is the Bayesian view, where you have some prior over MDPs. And in this case, you can actually plan to obtain the best exploration. So for example, in the circle, by knowing where the goal could be located, we can plan a very, very effective exploration strategy. Another thing is that the Bayesian RL formulation, which is also known as meta reinforcement learning these days, makes explicit an optimal trade-off between exploration and exploitation. So the idea is we have some prior over MDPs, and we want to maximize our expected reward where the expectation is taken over MDPs from this prior. And this is essentially a POMDP, so this makes our optimal policy history dependent. But the nice thing about it is that it is a very clear optimality principle for exploration and exploitation. Now, I don't have much time, so I'll quickly jump over to our results. So there has been very recent works that show this connection between Bayesian reinforcement learning and meta-RL. And we used these ideas to extend them to the offline setting, I invite you to read our paper. I'll just quickly jump to the results. So I'll kind of explain what is the difficulty here. There are easy problems and difficult problems. Easy problems for this Bayesian RL setting are problems where the optimal solution or the data that we have covers all the states that let us identify between the different problems. So for example, if this half cheetah needs to learn a particular velocity, whatever it does, it's going to visit states that go in the same direction. So it's going to have a very clear signal of or reward of whether it's doing good or bad in the data. In contrast, if you're trying to reach a sparse goal, if you see different goals, it doesn't tell you anything about where the other different goals could be, or what they could be. And this leads to some kind of identifiability problem, which we formulate in our paper. And this is a very different reason that sparse problems here are much more difficult than dense problems. But you can read the paper and see how we solved it. Let me just show you some results. Here is this 2D agent that learned from offline data of moving to these different goals. And after learning, it learned this kind of nice trajectory that surges along the half circle once it finds a goal, and then it moves directly towards it. And here's the same thing with a much more complex robot. This is an ant robot, and a very similar problem. It had a sparse reward on this half circle, and it learned to kind of navigate on this half circle, find the goal, and then when this goal is found, it just learns to go directly towards it. Now, I emphasize, we didn't tell it anything about how this problem looks like, or there's no prior information at all that we manually baked into the algorithm. We just showed it trajectories of RL agents trained on solving these sparse reward problems. Each one is just a standard RL algorithm. And from this data, it learned the exploration strategy that's relevant for this task. So I'll conclude here because I'm out of time. But what we proposed here is the first offline deep Bayesian RL algorithm. And I think it's a very important setting to consider because we want to explore very fast in the real world. And often what we have is only some offline data that we can make use of. Something that was a challenge here that I didn't have time to talk about is something called MDP ambiguity, which makes this offline problem very difficult, but we came up with some data collection strategies to overcome it. And something that we are thinking about in the future is how to kind of use these ideas to learn world models that let the agent very quickly identify what is the model that it's currently facing and solve it. This is it's a key problem in many RL tasks and specifically in continual learning. Okay, thank you all. I'd also want to thank all my collaborators.
All right, well, we have time for a few questions. Please use the raise hand feature to ask them. So.
First of all, thank you. It was very interesting. I wanted to ask about the error propagation, if you were able to spot any disadvantages in relation to the Bellman equation, and if so, did you consider like mixing both of them or somehow smart combination of both of them?
Well, that's a very, very interesting question. We're actually thinking about it right now. So one thing you can do is predict instead of, well, if I go back. One second to find it. So we're predicting the middle segment, and Bellman equation kind of predicts the first segment. And one thing you can ask is, well, maybe if I train a neural network to predict something in between the middle part and the first part, I can maybe use some uncertainty estimate to decide what I'm most certain about. So maybe I'm think about, for example, an agent in a maze, and it can only go in particular direction. Then maybe predicting the next segment is very easy because it doesn't have anything else to do, because it's kind of trapped to do only that. But maybe in some situations, you're in predicting the middle segment is very clear because there's some bottleneck that you have to go through, and that's going to be easier than predicting your current action. So you can think of training an agent that can predict what is a next step in say t time steps, and use some uncertainty estimate to choose how to construct your trajectory, so that you always start from the most certain parts of the trajectory and then build your trajectory onwards. So I think it's a very interesting direction to tackle.
Thank you.
All right. Thank you, Aviv.
Thanks, Aviv. Oh, can you hear me?
Yes.
Okay, great. I'd welcome our next speaker, Gal. Aviv, can you just stop the sharing?
אני הולך לדבר באנגלית, אבל אני אגיד, כיוון שזה כנס עברי, כמה מילות תודה לאמריקנים. יש פה המון משתתפים, האמת שזה הפתיע אותי. ושומעים אותי, נכון?
כן, שומעים.
אז כל הכבוד על הארגון, ותודה אביב על השיחה. And I'll take it from here in English. So let me share my screen. Can you see it?
Okay.
Okay. So hi everyone, I'm Gal Dalal from NVIDIA Research, and I'll be presenting our work, learning and planning in delayed environments with non-stationary Markov policies. This is joint work with Esther and Shie, and this is going to be published in iClear this year. Okay. So the delay is very common in real-world problems, such as autonomous driving. There's still relatively little work on it. Here we consider a constant delay of m steps. And in the figure, you see a robot which observes the present, but it needs to take a decision that will be executed only in the future. That's the top view. Below, we have an equivalent situation. So that's actually identical in every aspect, except for how we think of the problem. There we have immediate execution, but that is based on observations received with delay. By the way, if you have small interruptions, you can feel free to interrupt, because I think I can do it in like 12 minutes.
Can you increase the size of your screen? I think it's only partial.
How is this? Better?
Yeah, better, thanks.
Okay. So let's begin with an example of a two-state MDP. The agent is in S0. I mean, if the agent is in S0, it should take A0 to receive a reward of 1. If it is in S1, it should take A1. However, if we have delay in this problem, the agent has to guess where it really is. And this makes this very non-trivial, even this very simple MDP. So we analyze this and we quantify the trade-off between the level of stochasticity that is represented here by P and the delay that is M. And it turns out
that the optimal return can be written as a simple, and this is the optimal return that I'm showing here in proposition 1. This is the following simple expression. It's just this fraction that depends on P and M. And you can see that this is maximized at 1/1 minus gamma. Okay, so I colored blue and red here the P and M. And you can see that if P goes to 1, meaning we have a deterministic problem, or alternatively, there's no delay where M goes to 0, then we get the best case of 1/1 minus gamma. This is what we can achieve. However, for the complement case, where the second term in denominator decreases to 0, meaning if M goes to infinity, or alternatively, P goes to half, then the return is only half of what we can achieve. And there's a continuum between that half of 1/1 minus gamma to 1/1 minus gamma. Okay, so this is a nice example to start with the trade-off between stochasticity and delay. And this is how delay can impair us. Okay. So the immediate approach to handle delay that is often considered is to augment the state to include the last time actions and to implicitly infers the future state. So we begin with results that are the first tight bounds for this augmentation approach. We have lower and upper bounds for the number of iterations to converge in a planning algorithm, where in this case, we analyze policy iteration. And these are the results that we have. So the first result is a lower bound, which goes exponentially with the delay. I would say this is the more important of the two results, where the second result is a matching upper bound up to a factor of A. And the conclusion here is clear, right? Augmentation is not scalable. This explodes with the action space size. This is kind of a folklore result, which we formulated here. And apparently this is the first result of a kind in this on a planning algorithm. So we have those results and we show this in simulation as well. Now, what if we do not augment the MTP? So for that, I'll begin with a reminder of the possible types of policies. And we have this diagram. Stationary policies, the green stationary policies, are a subset of Markov policies. Markov policies in general can be non-stationary, but Markov policies mean that they only depend on the last state. Now, Markov are a subset of the general class of history-dependent policies. And in each such category, we have a subset of deterministic policies. A classic result is the existence of non-stationary optimal policy, stationary optimal policy for non-delayed MDPs, and that's the green arrow that we see here. Now, what if we have delay? So we have new results. I'll show them more formally next. But it appears that the optimum, what we managed to prove is that the optimum actually lies in the Markov policy space, and stationary policies are not sufficient. So let's see this. A bit more formally, if we have a history-dependent policy pi, for that there exists a Markov policy that reproduces the same process distribution, that is pi prime. So the first result basically tells us that we can shrink the space, the search space, from the general class of history-dependent policies to only Markov policies. This is kind of analogous to how with no delay, we can shrink the general space to only stationary policies. Second, there exists an MDP with stationary policies being suboptimal. That means that stationary policies are not good enough. And this is the cost that we saw in the previous figure. Now, we also have a delayed value function. For that, we need to have some initial queue of action distributions that are given to us, because remember, we have delay in the system, so we need to begin at some point with some previous actions. And second, okay, so this is the delayed value function. Now we have this result
where the delayed value function satisfies some generalized Bellman recursion. I didn't give you the whole complex expression here. But using this, we can prove that the optimum is attained with deterministic Markov policies. And this is theorem 5. In fact, it is enough, again, to search the deterministic Markov policies and not the whole space of randomized Markov policies. Okay, now we get to the algorithm. So we have a DQN-based algorithm. It consists of a forward model that is learned together with the Q network. And each time we make a decision, we iterate through the forward model m times to infer the future state. So this is a one-step forward model that we iterate. This is this xm here to say that we know that the delay is of m steps, so we kind of look into the future m steps ahead. Now also, we have this replay buffer shift here. Notice that for st plus m, rt plus m, we attach at. So we keep this buffer and we shift the actions as if they were taken m steps before. So we had some theory, now we have an algorithm, and let's see the experiments that we conducted with this algorithm. So we actually show a lot of experiments. We have a tabular maze, the physical acrobat and cart pole, and of course Atari. Our algorithm is in green, and the comparison is to DQN, which ignores the delay, and DQN that concatenates past actions, meaning the augmentation approach. And as you can see in the convergence plots for in the rows for maze, cart pole, and Pac-Man that I'm showing here, and in the columns, we extend the delay from 0 to 5 to 15 to 25 for the columns. As we advance with higher and higher delay, the gaps between our algorithm in green and the two others increase significantly. So those are some convergence plots. Now we have, we increase the delay and we measure the performance for higher granularity of delay up to 30. And we see how brittle the other approaches are to delay, while our algorithm in green shows competence. You can see even that here the augmentation approach in the tabular case of maze, it just breaks. It cannot, due to the increased complexity, the runtime is inevitably too long. So because we have this exponential increase. So for maze, we have a tabular experiment, but for the other two, we have a DQN-based experiment, which has function approximation and doesn't have this issue with the augmentation. Okay. Next, we test for misspecified delay. So specifically, you see on the y-axis different delay values. Okay. 1 minute including questions or not including?
Not including.
Okay. So we train with a delay of 10, and we load the same agent with differently delayed environments. And I think this one is really interesting. As you decrease the delay, the performance actually increases more than the originally trained environment, right? So we train it with delay of 10, but we test it on shorter delays, and the results indeed improve. And this is because our algorithm completely decouples from the delay it was trained on. The forward model is trained on a single step and is tested only on single step predictions. And this plot, this final slide summarizes all of our comparisons. So we have many games and domains. Our approach outperforms roughly 95% of the time, slightly more. And in the paper, we have some additional experiments to exhibit robustness to added noise, errors in the forward model, and more comparisons. Okay, thank you. So,
great, thanks. Any questions from the audience? Feel free to raise your hand. I'd like to ask one question. Do you see any future directions for this line of work?
Yeah, definitely. Well, we only experimented, and actually, we're using DQN, so this is not really valid for continuous action spaces. And I think it's interesting, especially in the context of robotics, where delays are significant and AVs as well. And there, the problem will be slightly different. Many of the concepts will be similar. And if we use this FOR model, then we can even handle varying delay. So this is another extension, but the more interesting extension, I think, is for continuous action spaces. And also ideas of how to combine this with researches. This can also be, making this more powerful, perhaps.
Great, thanks. So now we'll move to the next, to Yonathan. Thanks, Gal.
Sure.
Let's see.
Hi. Hi, can you hear?
Yeah, we can hear you.
Great. So should I share my screen, I guess?
Yeah.
Let's see.
And we can see your screen too.
Awesome. Yeah, let me turn on the video if I'm doing that. All right, so hi everybody. I'm Yonathan. I'm from Microsoft Research. I'm a postdoc there. And I'll talk today about a joint work together with Nadav from the Technion, Adi Rupa from a group in Microsoft, and with Shie Mannor from the Technion as well. So the title of this talk is Confidence Budget Matching for Sequential Budgeted Learning. So before I will dive into what the confidence budget matching means, let me talk a bit about general sequential decision-making algorithms. So the setting of sequential decision-making algorithms, the feedback model. When we have a bandit feedback, goes as follows. We have an agent. The agent interacts with the world, with the environment. And at the 10th episode, the agent sees some side information, which is the context. Then the agent picks an action. And finally, the agent observes some form of reward feedback that it gets from the environment. And in this work, we consider the bandit feedback model, which means that we only observe feedback on the action that we took. The goal, at least the common goal, is to minimize the cumulative regret that measures by how much we regret on the actions that we took relatively to the optimal thing. Okay, so of course, so in this work, we are considering the sequential budgeted decision-making problem. So what's the problem in sequential decision-making? The problem is that feedback in a lot of different cases has a price, meaning the reward feedback that we always assume to get in sequential decision-making is a bit problematic in several problems. So for example, we can think about recommendation systems. Would we use any algorithm that should solve sequential decision-making problem? Then we would ask from each user for a feedback on the quality of the recommendation system. That's obviously problematic because this might annoy clients. Clients can refuse to supply this information and many other problems. And I guess that in fact, in most of the problems in which an algorithm interacts with a human, with a person, we usually have some form of limited reward feedback because we don't want to ask from the person how well we did. Okay, so that gives us the motivation to define the sequential budgeted learning model. So in the sequential budgeted learning model, as we saw before, we interact in episodes. At the 10th episode, the algorithm or the agent observes some side information, the context, it takes an action. And unlike before, unlike the usual setting, the agent observes the total cumulative budget before it can query the reward feedback. And then if there is a spare budget, the agent can choose whether it wants to query for reward feedback or whether it does not want to query for reward feedback. And the notation here of BT, it means, so BT is the cumulative budget that we have, and the spare budget is the difference between the cumulative budget and the budget that we used until the 10th time step. And so that's just a matter of definition here. So keep in mind that BT is the cumulative budget. And the goal, as usual, is to minimize the regret. Okay. So in this work, when we mainly focus on studying two generic approaches to solve sequential budgeted learning problems when the rewards are stochastic. So the first approach is the greedy approach, meaning we query for reward feedback as long as we have spare budget. If we can pay, if we have enough money to pay, we can we just pay for a new information, for a new reward from the user. That's the first approach. And the second approach is the confidence budget matching, or CBM. And generally speaking, in this approach, what we do is we query for feedback if the confidence of the action that we chose is large. So we try to ask for feedback only when our confidence is large and we are uncertain of the quality of the action that we took. Okay, so let's start with the first approach, and we'll talk a bit about our results. So as I said before, the greedy approach, it means that as long as we have spare budget, we just query for feedback. So algorithmically speaking, we can think of some form of reduction. So assume that we have any base algorithm A that gets a context and outputs an action. So the greedy reduction for the budgeted learning scenario goes as follows. So we interact in episodes, we observe a context, and we see the current budget. And if there is a spare budget, we just act with A and ask for reward feedback. And if we don't have spare budget because we wasted everything, then we do something, then we use some other policy that is a function of past experience. I won't get into the details here, but you can definitely check the papers. And the overall result is that this generic approach performs well. And by understanding a bit better what well means, I suggest, I highly recommend for reading the work. So if the contexts are stochastic and the budget is chosen by an oblivious adversary, then the greedy reduction performs well. That's the result here. So under these two assumptions, we can definitely use the greedy reduction and get a well-performing algorithm. But of course, and unfortunately, the greedy reduction really fails if we break either one of these assumptions. If the contexts are not stochastic or the budget is not chosen by an oblivious adversary, then the greedy reduction can really fail, and it fails, and we quantify like by how much it fails in this proposition. So if an adaptive adversary controls either the contexts or the budget, then although we have a linear budget, our budget grows linearly in time, the regret that we suffer is still linear. which means that this approach really fails if we break either one of the assumptions. And the conclusion that we arrive is that we need some alternative to the greedy query rule that intentionally stores budget. And that's exactly what the confidence budget matching scheme principle is doing implicitly. So in simple words, the confidence budget matching principle tells us that, it tells us the following thing: query for reward feedback if the applied action has large confidence interval relatively to the inverse budget, to the inverse cumulative budget. So a bit more concisely, in this approach, we try to match our confidence to the inverse cumulative budget. So that's in words what happens here. And algorithmically speaking, we think about the following scheme. So we interact with episodes. We take any optimistic algorithm, and in the approach, and the algorithm goes as follows.
1 minute.
Okay. We observe a context, we act with some policy, and if the confidence is larger than the inverse budget, then we ask for feedback. That's, yeah. Okay, the key result here in this work basically is that the confidence budget matching approach performs well, even if an adaptive adversary manipulates contexts or budget. And we focus in this work on bandits, linear bandits, and reinforcement learning settings. So the takeaway message, I guess, is that use the CBM query rule, which query for reward feedback if the confidence is large than the inverse cumulative budget. And future directions that I find interesting is try to think what happens for Thompson sampling and not for optimistic algorithms for CBM. And as well, like studying many other variations of this problem, corrupted or adversarial feedback with context and problem-dependent bounds. And that's it. Thank you very much.
Thanks, Yonathan. If there's any questions, feel free to raise your hands. Meanwhile, I have one question. Can you give some practical application of this budget setup?
Yeah, I guess like any form of any setting in which you interact with a person, like and I think that in any such problem, we would like to have some form of limitation on the amount of feedback that we ask from the user. Like for example, when you take actions, if some new person arrives and interact with your system, you want to be able to understand whether you want to ask for feedback on the system, whether the system is nice for him or not, or you should not do that. That's in a very high level perspective, I guess.
Okay, thanks. So I don't see any other questions. I guess we'll move to a lunch break and we'll reconvene in the regular hour. So you have 10 minutes left to eat at 1 and 10 minutes with Professor Shie Mannor. Bye, guys. אוקיי, ברוכים הבאים חזרה, אני מקווה שלכולם היה טעים. אני מתכבד להזמין את פרופסור שי מנור. שי הוא חבר סגל בטכניון וחוקר באנווידיה, עם עשרות מאמרים בתחום, שכבר הספיק לגדל דור של חוקרים בארץ, כולל אותי. שי מתעסק בנושאים רבים ומגוונים, רשתות, רכבים אוטונומיים, אלגו טריידינג, ערים חכמות ועוד. שי, בבקשה.
תודה, אסף. I will switch to English, even though it might be a mistake. Thank you for organizing it. It's a pleasure to see all those familiar faces, even if it's just remotely. So today I'm going to tell you my research philosophy about risk and robustness in RL. And I think I'll try to explain why RL works when it does. And to me, the reason is that we build robust architecture and robust policies. So just to fix ideas, so RL is really about sequential decision making. Some examples of this is Tetris. This is a classical example. There are bricks that go down, and you need to clear rows. This is perhaps more interesting. This is an American put option. There is a given strike price K. And there is a maturity time duration T, and basically it's a contract that gives you the right to sell a stock at a given price, strike price K, until the maturity T, and the objective is usually to price the option, so that to sort of to compute how much does the option worth. It's stopping decision, and then a pinball domain. Another very famous robotic domain. Here you want to get the blue point to the red goal, and basically like a pinball, everything shakes around you. So if you're going to go through the lower tunnel, then there is a chance you're going to hit the wall and be considerably delayed. But the higher tunnel above is much safer, but it takes longer to get there. So those are classical sequential learning problems. And in the classical setting, we have a controlling agent, and then there is a controlled entity. The agents can choose action, they observe something about the state and gets a reward. So this is a classical setting. And in today's talk, we'll consider the case where we know the state, we know the action, so the state space is known, the action space is known, but we're not really sure what are the transitions, the dynamics of the controlled entity, and what is the reward function. And throughout this talk, we'll focus on the classical objective of discounted, expected discounted, cumulative discounted return. And I should say that this is a famous saying I like to quote. We don't really believe that the world behaves like an MDP, but we hope that this is a somewhat useful model. And this comment by the famous statistician Box gives us a hint of what we're trying to do. We're trying to build models that are useful, and to make them useful, we'll need to equip them with a level of robustness. So what happened in the last few years? So we have a lot of algorithms. This is a very partial taxonomy of RL algorithms, but we have much fewer real-world successes. So if you want to count the real big success of RL, then with the exception of perhaps trading, I don't think we are seeing lots of impressive successes. And I think the question is why, and what should be done to remedy this situation. So let me give you one example of why we're not doing things right. So let's agree on the next 3 sentences. So I'm sure you agree that playing, let's say, chess well is something only smart people can do. I'm sure you agree that almost everybody can tell a joke. So the logical conclusion is that computers must be really good in playing chess. Well, I don't know if you've seen a computer telling a joke. It's usually not very funny. So what is happening here is that we're making a reductionist fallacy. We assume that something that is easy for us to do, or easy for most people to do, is also going to be easy for computers. And that's something that I think is just not true. So to stand on the shoulders of giants, the firm is saying that everything should be made as simple as possible, but no simpler. And there is a recent book by Shie, who was the director of the Media Lab at MIT. And basically his point is that in AI in general, and for us in particular, I think, we're trying to reduce policy to believe that things are much simpler than they really are. And the truth of the matter is not always, things are not always simpler than they really are. And perhaps the dream that an RL agent will roam the world shortly is not likely to actually work out. So this is when I grew up, I wanted to build one of those three. You can imagine which one. And we're very far from it. So this is where robotics is at the moment. And we're not very good. Like, we don't know how to build very sophisticated agents. And if you want to talk about the dancing AI robots from Boston Dynamics, then it took them a year and a half to choreograph with really special high-end choreographer and artist. So we're just not very far, and we're just very far from where we would like to be. And just to remind you, in '57, in the summer of '57, a group of professors at MIT, including my personal hero, Norbert Wiener, sat down and said, well, this all AI things, we'll get it figured out in half a year, maybe a year. So things are a little bit more complicated than they might seem. So going back to RL, the way I view things, there are three types of RL problems. There are static problems. In the static problem, basically, I don't care about anyone else. Here I am Pac-Man, and the ghosts are static. They don't move. Those are really planning problems, which I can, if I want, try to mimic, to portray them at the learning problem, but they're essentially planning problems, and they can be more or less difficult. But I don't care about anyone else, and all the other agents are simply non-existent. And then there are dynamic problems. In dynamic problems, there are ghosts, but the ghosts do not react to me. So basically, there are other agents that are moving around, but I don't really care what they do. I just need to view them as an abstraction. And then there are counterfactual problems. So in counterfactual problems, actually everybody reacts to everybody, like in the real world. And in the case of Pac-Man, this is how Pac-Man behaves, right? When Pac-Man is getting close to a ghost, then the ghost is going to try and eat Pac-Man. However, if Pac-Man ate an apple before, then Pac-Man can eat the ghost. So those are the three types of RL problems. I think we're very good at static problems. I mean, we're getting there. At dynamic problems, we're not there yet, and trying to solve counterfactual problems, this is just something that is very, very far from us at this point in time. But a good example, by the way, would be driving. A static view of driving is that I'm trying to drive from point A to point B, and I'm just me on the street. There is no one else, no pedestrians, no other vehicles. For dynamic problems, there are other entities on the road, but they don't react to me. They don't care. I mean, they do whatever, and I can predict what they're doing. And counterfactual, that's a real problem that we're trying to solve, where there are other vehicles and pedestrians that behave according to my own behavior. So this is a problem I've worked on in the past, still does. This is if you try to view the autonomous vehicle as an RL problem that I think initially there was some hope that end-to-end would work. It doesn't. And if you want to solve it as an RL problem, you have a very long tail of interesting or less interesting events that you need to take care of. And the reason that we're not seeing an RL system right now for those problems is just that there is a very long tail. Not to mention that defining what is the actual RL problem is a difficult task. So what I'll advocate for today is the view of RL, or the usability of RL in a somewhat less ambitious goal than AI. Certainly less ambitious goal than artificial general intelligence. And that of controlling agents that has to interact with other agents, human or not, that extend it. And the way I think about those problems, that the controlling agent is not going to work in vacuum. I mean, they will have to keep interacting with the extending agents, telling them what is happening, communicating with them, and also controlling the entity that they're actually there to control. So extend intelligence, or EI, is the design of systems that are part of other more complex systems and have to be responsible, aware, and robust elements. And if you think about how to build an EI system, then the following 5 principles come that are sort of the basic 5 principles. This is, by the way, this is the ring of power. So those are 5 principles that are intertwined in each other, and they are awareness. Basically, you need to know how well you're doing, and you need to know what is happening to the other agents. Accountability, meaning you can explain why you did what you did. Adaptivity, meaning you can function under other conditions, not expected ones, or either predictable or harder to predict. I think those 3 are kind of well addressed in the community. The next one is, I think, the most important one, which is poorly addressed, the life cycle consciousness. Basically, debugging an RL system is a bitch. It's hard, it's annoying, it takes a lot of time, and we don't have the right tools for that. That's something that I think that if you ever want to have RL agents that roam the world, then we'll definitely have to be much better in that. And of course, scalability with data and compute power. So those are the 5 principles. And every research that I've been doing in the last 5 years or so is measured according to the contribution to those 5 principles. So in this talk, we're going to talk about risk sensitivity and robustness, and that's going to focus on adaptivity, naturally. Of course, we'll have eye for scalability. Non-scalable RL is not too interesting. And to some extent, also accountability and awareness. Awareness is a byproduct, and so is accountability. You can explain what you did by referring to adaptivity. I chose a particular action because I had to adapt. Or an awareness, if you think you're completely off track, then you can explain that. So this talk from now on is going to be about risk sensitivity and robustness. So why should you be risk sensitive? So look at the images we have here. We have this blue dot and the red target, and you want to get from the blue dot to the red target. So we have 2 choices to make, right? We can choose the upper route, which is going to take longer on expectation, but seems that it's very likely that by a given time, say the time here, we're going to get to the target. Or we can take the lower route, which may get us faster, but there is some chance that we're going to hit a wall, and then everything is going to be delayed. So why should you be risk sensitive? Risk sensitive buys you robustness because, at least on an intuitive level, what risk sensitivity buys you, that it gets you to where you want to go with very high probability. If you're not too ambitious, it will not maximize your expected return. And what we're going to do is we're going to propose 2 approaches for robustness and risk sensitivity. And then eventually I'll show you that, surprisingly, this is kind of the same thing. Okay, so let's talk about the type of uncertainties. So this is Daniel Mankowitz, not surprisingly, also discussed that. So I'll go briefly now. There are 3 types of uncertainties. There are uncertainty in the parameters. So I know the model. I'm just not sure exactly what are the transitions and the rewards. And this is sort of, somebody asked Daniel, though, this is a very old roots in robust control. You try to find the best policy under the worst possible parameters of the expected discounted return. And then there is inherent uncertainty. So now we're just saying that there is a cumulative reward. It's not stochastic, but expectation does not quite catch what we're trying to optimize. In the example here, there are two policies. Both of them have the same expected return of 0. One of them poses very little risk. Basically, I can only lose $1. And the other one can pose a much more significant risk. I can lose $1,000. So if I'll ask any of you to play a game which of the games you would prefer, most of you will probably choose policy 1. That sounds pretty harmless. The worst thing that can happen is that you're going to end up with $1 less in your pocket. But then policy 2, that might be a little bit more painful. So in inherent uncertainty, we're trying to defend against extreme outcomes that even though in expectation things can still be favorable, the extreme outcome can be quite unfavorable. And the way we write it with a risk measure. So instead of looking at expectation, we have a risk measure. Here's an example from finance. This is known as the Markowitz risk-adjusted risk measure. It's expectation minus something times the variance. And this is a way for us to defend against the unluckiness. And then a third type of uncertainty, that's what's known as model uncertainty. Here, the model itself is not known. So we don't even know what is the right way to model our data. And we have to handle model mismatch one way or another. So imagine that you have here several models that are completely different. Those are different beasts. And you need to find a single policy that would address all of them together. That's something that at least currently the community is doesn't know how to handle very well, and it's an active topic of research for us as well. So risk sensitivity is important whenever the cost is failure is high. Examples are given here, but there are many others. I should mention that the model is never known because you always create a model from relatively few samples. So there is always some uncertainty. And as I said before, we focus on adaptivity and on scalability. So at this point, you can ask, well, maybe we can solve it directly. Maybe there is a solution. So the short answer is that there is no solution. That all the problems that we're going to mention today are going to be very hard computationally. Certainly when the number of states is not minute. So when the number of states is even in the few thousands, the problems are going to be very hard. So forget about optimality. Okay, so I'm starting now to discuss two works from my group, and those works are the first one. The first line of works is about robust MDPs, and then the second line of work is going to be about risk. So we'll start with robust MDPs. I'll start with explaining the model and how it works. So this is really a planning problem. So we're not going to talk about learning today. And this is how you model an MDP. So I'm currently, the system is a state S0, and then it can transition to S1, S2, and S3. This is sort of the transition probability for moving to S1, moving to S2, and moving to S3. And what we know is that you never know what are the transitions are precisely. There is always some uncertainty. Here it's depicted as confidence intervals, but there is always some ambiguity. And there is this phenomena that we showed a long time ago called uncertainty amplification. So when you have a small mistake in the beginning, it can accumulate because you're looking at a discounted return, and it can correlate over time, so that eventually you're going to get a large impact on your return. And there is an issue of rolling disasters, and especially relevant for power grids, which we're not going to get into today. So what happens in a robust MDP? In a robust MDP, we have state and actions, and as before, we also say that the rewards are known because it doesn't really matter It's if you know or don't know the word, it's going to lead to similar algorithms, but you're not sure what are the transition probabilities. So here, when you look at the transition probability, you're not really positive whether it's 0.2 or 0.25. So the transition probabilities are assumed to belong to some uncertainty set. And the objective is the worst case objective. So you look for the best policy under the worst case parameters of the expected discounted return. And if you like, you can think about it as a game where first player chooses the policy, and then nature chooses the realization of the model. Okay, so would you solve such a problem? So you can try to, for a fixed policy, do something which is like robust value function. So the value function for a policy pi is the worst. You look at the expected return, but now it's under the worst possible model. So the way you should think about it is that if there is a player, the player chooses a policy pi, and then nature, knowing what pi is, chooses the worst possible point here in this uncertainty of in this transition probability uncertainty. So and this transitions continue, and then maybe it's S3, there is another set, but still the adversary knows pi, and it can choose the worst possible model. Okay, so this leads to the robust Bellman equation, which is for a fixed policy, and that's it's written here. It's a nonlinear set of equations, still governed by a contraction operator, so it's still easily solvable. And for small problems, indeed, it has been solved 15 years ago, and either by value iteration or by policy iteration. But for large problems, it hasn't been solved to date, or at least until we did this line of work. So how do you solve such a problem? Given the features that were generated one way or another, let's look at linear function approximation for the sake of simplicity. The value estimate is the features times the weight vector, and we try to select the weight. For the standard non-robust problem, it's very simple. I have the value function. I can sample trajectories using this policy, and I can sample 100, 1,000, 1,000,000 trajectory, depending on how much money and time I have, and I can regress W according to the equation here. So according to this linear function approximation, I can regress, and if I have something which is nonlinear, I can also do it. And this is a celebrated fitted value iteration or fitted Q iteration algorithm that we all know and like. But for a robust problem, I cannot sample trajectories because, to remind you before, I follow a certain policy, and then nature or an adversary has to choose the worst possible realization against me. And basically, I don't know how to do that. I don't know how to sample the worst case model because I don't have access to it. So our approach is basically to bootstrap. So this is a Bellman equation. And to solve the linear approximation, what we're doing is the following. We start from some random initial point. We pretend that our value function approximation for the previous iteration was good. And then, given that it's a good approximation, we can iterate the regression targets and solve it again. And we can do it over and over again, solve for WK plus 1, do it again, assume for WK plus 2, and so forth. So using this age-old idea of bootstrapping from statistics, we can, in fact, solve robust MDPs. And you can get convergence, you can get error bounds, and basically you can derive a deep algorithm for that. And everybody's happy. So you can solve a fairly substantial problem using bootstrapping here. Okay, so let's run it through an experiment. So here the question is, this is the American put option we discussed before. And the question is when to execute. I need to find a policy that executes given the current state, which is essentially the price and the remaining duration. And you can formulate as an MDP, and then there are different models for simulations that you can consider. So we did the following. we estimated price transitions from historical data, and we simulated the model. And what I want to show you here is an interesting phenomenon which I do not know how to explain beyond hand waving. So we build a model. What we see here, this is a number, and this is the probability that you're going to make more than $8. So just note that in an option, you never lose money because you're not going to execute when you're underwater. So the true model, the transitions depend on price with some complex mean reverting model. The estimated model that you have constant transitions, and we robustify this estimated model. So the point of the group summary is that we have a mismatch not only in the model parameters, but also in the model class itself. So the model that is misspecified in a very awkward way. We're not even using the right model for the data. And what we see here is that the robust policy dominates the nominal policy. So this is a policy that is using the mean reverting model and estimates things from data. And of course, since I am the one presenting the graph, this is the best graph I could present. But this phenomena of having a model that is significantly better than the model that we use to actually model the data. However, once we robustify the model that we got the data from, we get better performance. It's something that we've witnessed in many applications. So in some sense, robustness buys you resilience to model misspecification. And as I said, we don't have a solid theoretical explanation for that. So now I'm going to switch gears and talk about a risk-sensitive approach. But now it would be a good time to stop and answer any questions. So if there are none, I'll continue to talk about it. Sure.
Shai, you mentioned an algorithm with robustness to the confidence in the transitions, right?
Right.
Does it matter how the confidence intervals look like? If they are
yes.
Rectangular or not? Does it affect?
So it does matter. If they're not rectangular, then in principle, hell can break loose and all the demons can attack you, and you will not be able to solve the problem. It's going to be very hard very quickly. If it's rectangular and convex, then it's a fairly easy problem.
Do you think that with recent, I mean, the work itself is a few years old, maybe with deep, you can tackle this kind of solution easier?
I don't think so. I think that it's the issue is not of the computational issue is out of precision more than anything else, and of constructing the uncertainty set. So I don't think that a deep method would help. In fact, deep methods work here almost transparently. So there is nothing here that is unique about depth of the network.
Okay, thanks.
Okay, so I'm going to talk about risk-sensitive policy granite. I'm going to talk about.
Oh, wait, Shai, I see there's another question here from Roy. Yeah.
Is it okay? Is it a good time?
Yeah, please.
Yeah.
Okay. Regarding the robustness work, if I understand well, then you're making some compromise because the bottom line is that if you still look from a expectation perspective, you're suboptimal if you robustify the policy. The implications are, for example, for autonomous driving, if you're being too cautious, then the behavior that you're going to expect is going to be over conservative to the point where maybe a product, it won't suffice for a product that people sit in the car, right? It wouldn't be a human-like behavior. So my question is, am I correct in the sense that it hurts the optimality eventually? And is there a scale maybe instead of doing not robust versus robust, maybe there's a scale of how robust you want to be?
Yes, so there are works. So the short answer is yes. If you're going to try and be robust for everything, you should stay home and hide under the bed. The robustness is always depends on how you define your uncertainty set. And toward the end of today's talk, I'll show a more recent work that addresses that at least to some extent. There's certainly a trade-off between robustness and performance. This has been proven formally by us and by others for different models. Moreover, there are other approaches which are pseudo-robust, so approaches that are trying to do what's known as distributional robustness. There is a paper from my group with Esther and Daniel Mankowitz, Esther Derman and Daniel Mankowitz from I think UAI 2 years ago, if I recall correctly, which tries to do that. So basically, the short answer is there has been a lot of work on trying to relax robustness assumptions and also trying to reconcile expected performance and robust performance. Okay, so we're going to talk about the CVAR now. So let's, since we're not all economists, let's remind ourselves what is a conditional value at risk. So if you have a random variable x and you look at the alpha quantile, say 5%, then the alpha CVAR, the alpha conditional value at risk, is the conditional expectation of this variable, given that it's lower than the quantile. So the way you should think about it, if alpha is say 5%, then I'm looking at what happens in the worst 5% of the events, and that's what I'm trying to optimize against. Some people call it expected shortfall, and the idea that when you look at tail events which are not, or even not really, really rare, but still not very common, then the CVAR is going to be more sensitive than the average return. And estimating the CVAR is trivial. If estimating the mean, the empirical mean is just the average expectation is just taking the empirical mean, then estimating the CVAR is simply looking at your samples, taking the alpha and worst samples and averaging on them. Okay, so we encode the policy, say by a deep network, and then this encoding affects our payoff function and also the stochastic system. And the standard objective for us is to maximize the parameters, usually of the network. The risk sensitive is just objective would replace, or the CVAR objective would replace the expectation with a conditional value at risk at a given alpha. So that's pretty simple. The notion of CVAR has been central in economics, especially in portfolio optimization. And previous work has discussed the issue of optimizing a portfolio mostly. But when you optimize the portfolio, usually you assume that you have no effect on the market. So with no market effect, it's really just the payoff itself. So people have derived different optimization approaches. But we, being engineers, we have to consider that the policy is going to affect both the payoff function, but also the stochastic system. So what do? We provide a new formula for estimating the gradient of the CVAR and sampling-based estimator, and then everything else falls from usual standard stochastic gradient descent. So if you want to use PPO or TRPO or your favorite policy gradient-based algorithm, you're most welcome to do it, but just replace the gradient with the CVAR gradient. So let's do some equations. So let's remind ourselves, how do I estimate the gradient of the expected return? So this is basically calculus 101. The gradient of the return is the integral from -infinity to infinity of the return. And under some conditions, I can pull the gradient in, do the usual trick of multiplying by the PDF, and basically this lends itself to the classical Lior ratio method, when I take the gradient of the log of the distribution times the value itself. So this is how we do gradient estimates, classically so. So how do I estimate the gradient of the CVAR? So maybe I should look at the alpha and worst samples and do the same thing. Maybe that's going to work out well enough. But surprisingly, and now I remind you of calculus 102, this is not the case. And the reason is Leibniz integral law. So to remind you, when I do an integration from minus infinity to q, where q depends on whatever I integrate over, I have to do this correction, this Leibniz correction. And this correction implies that I have to take the gradient of the quantile itself. And this is essentially simple calculus. And once you do that, then you can rederive a formula for the gradient of the CVAR, which is very similar to the gradient of the usual expected return. This is the black part here, but you need to deduct from it the quantile. And if you do that, then essentially you're all set. And you have a formula for the gradient, but then the natural question is, well, we don't have the quantile. Had I had the quantile, I could the problem would have been much easier. So what I really need to do is I can only have the empirical quantile. And it turned out that if you do that, then that's also okay. It gives you some bias, but it's not too large. And the formula is really you sample and estimate the empirical quantile from the data. You sort, you select the alpha and worst elements, and you're all set. You estimate the CVAR gradient. Hanan? Can someone unmute him?
Just a moment.
Does this look similar to the reinforced algorithm, like from Williams?
Exactly. So this is exactly like the reinforced algorithms, but with the reinforced algorithms is optimizing the expected return. And what we're doing here is we're optimizing the CVAR of the return. Okay. So that's nice. Let's see what happens in Tetris, so we get some understanding of the way things work. So this is the Tetris domain, and we compare two things. We compare the standard policy gradient in red, and in blue we have the CVAR optimizing. And this is a histogram. So the average reward of the red is higher than the CVAR average reward, which is what you would expect. So when you play Tetris, and if you're aiming for average reward, then that's probably your best bet is to actually optimize the average reward. Let's look at the quantiles. So in the quantile, the quantile of the CVAR is also lower than the quantile of the policy gradient. So that doesn't seem right, but that's just the way it happens. But now let's look at the worst possible events. So this is like the really nasty events when I was unsuccessful at clearing lines for Tetris. So the CVAR is in here, again, in blue. This is the extreme part of the histogram. The CVAR is in blue, and the standard policy gradient is in red. So we see that there are much more events that are red than blue. So what this lends us is that when you optimize the CVAR, you're not going to get high average reward. Rather, you're going to get much less embarrassment and much less events on the lower side of your tail. Okay, so at this point, I want to sort of give you a result, which I'll state without proof. So remember that I said that the risk awareness is really leads to robust policies, and I kind of hand waved my way through it. So this is a result that is proven formally. So if you have multiplicative perturbations, so basically you have a model, a nominal model, which is written here, and you allow perturbations that are multiplicative. So you take the value and you multiply it by some delta. Delta is going to be the multiplicative perturbations, and across all your states, you tie all the perturbations in such a way that the overall product is less than delta. So this can be, the delta can be more than one, less than one, but your only restriction is that this multiplication is less than some predefined eta. So what it means is that you cannot, or it's not possible for everything to go wrong at the same time. So if your nominal model cannot, not everything bad can happen simultaneously. And that's considered called delta eta, the set of all possible perturbations. then the result that we have, and this is one instance, a relatively simple instance, is that if you'll optimize the nominal model, and then you're going to look for the conditional value at risk at 1/eta percentile of the cumulative return, it is precisely equal to the robust return against the worst possible model for this particular set of perturbations. So what this result tells us is that if you want to optimize, if you're optimizing the CVAR, what you're really solving is a very particular robust optimization problem. And vice versa, if you're solving a very particular robust optimization problem against this particular uncertainty set, then you are actually solving the CVAR. And this result is a special case of a much more general result that ties all risk measure of a particular type, in parentheses I say convex coherent risk measures, to robust optimization. So basically there is this equivalent that runs through and through. Okay, so in the remaining time that I have, I'm going to briefly talk about two recent works that each of them tackle one of the main problems that are left. One is the uncertainty set construction. So I was asked before, where do I get this uncertainty set from, and why wouldn't it be very conservative? And the second is about online adaptivity, meaning how do I construct the uncertainty set as I go along to match what I see in the trajectory. So for choosing the uncertainty set, we have a model which we call the trembling hand model. So you want to choose pi, and with high probability, alpha is, say, a very small number, pi will be chosen. But with small probability, somebody else is going to choose what will happen against you. And this is our uncertainty model. And this leads itself to an algorithm that we call the action robust DDPG. Basically, you train an actor, and then you train an adversary against this actor. This is the adversary that will play with the small probability alpha. You train a critic for the joint policies, for the mixed policy that sort of trembles with a small probability to what the adversary chose, and that's a policy that you use. And this is just to show you some results. So if you have this is from a Hopper, and this is sort of using standard approaches, and this is using our approach. Yellow is good. Red is bad. This is a noise probability, so this is a chance that you're not going to get what you want, and this is a relative mass of the two objects. So the point 1 and 0 is sort of the classical. This is here. This is what you would classically get. This is after not too many runs, and you can see the reward and the relative mass. So what this tells you is that when you choose a robust policy, you get very good transfer to new domains, because even as you increase the noise probability or the relative mass, you still get good performance. Interestingly, it shows you that you don't need to define your uncertainty set. An uncertainty set is going to be defined automatically for you. And for this problem, all that you needed to do is to define the alpha parameter, the trembling parameter. So I think this is a fairly interesting and strong approach to create a uncertainty set. It's almost like guns, but applied specifically for RL. Okay. In the interest of time, I'll skip this one. I think the slides are going to be online, so I'll just mention what it is about. We have this thing called base adaptive decisions. Those are decisions that you want to make online, because the model is as you get data from your model, get samples, you can modify, or you hope you can modify the model. Instead of trying to do the Bayesian thing all the way, we have a pseudo Bayesian approach, and we offer a robust alternative. This is the robust alternative, means that we construct an uncertainty set as we go along. Maybe I'll just show this slide because it's kind of interesting. So you get observations, you get a hidden layer, and then and this hidden layer, some of them may be shared. you get a Q layer and a variance layer. And this Q layer is going to be the expectation, and the variance layer is going to be the level of uncertainty as you're going to choose a control by maximizing a sampled version of this normal random variable. And that's a pretty simple approach to implement. But if you do that, you get fairly high resilience to changes as you go along.
1 minute.
Yeah. So I'll skip that, and I just want to conclude. The take-home message of this talk is that you should solve robust or risk-sensitive MDPs. They're really two sides of the same coin. You can call them risk-sensitive, you can call them robust, whatever makes you happy. But they're scalable, they work, and they even have some theoretical guarantees. And you know, one way of thinking about this whole work is how do I regularize, and how do I get generalization for RL? So the answer for me is that you need to build robust policies, or equivalently risk-aware policy, and that's a form of regularization. And just an epilogue. So at least the way I view research is that RL is a combination of 8 things. It's data, it's representation, and algorithms. I think we're pretty good at algorithms. We're getting there at representation. And then the 5 principles of extended intelligence, which are awareness, accountability, adaptivity, being able to work the life cycle, and scalability. And I should mention that from quite a few years of experience, RL work best when you have a highly stochastic environment, and preferable with a simulator, and when your control is high throughput. However, the real world is neither, so we need to build a new science to account for that. And with that, I would conclude. Thank you for your attention.
Great, thanks, Shie. So we don't have much time. We don't have time for questions, but I'm happy some of us got to ask during the presentation. Let's move on to Lior. Great, thanks, Shie.
Thank you.
Hi, can you see my screen?
Yeah, we can see your screen and we can hear you.
Hi, so I will start. So I'm Lior. I'm a PhD student of Shie at the Technion. And I will present a work on an apprenticeship learning, which is also together with Tom Zahavi from DeepMind. We were interested in this work to understand how to efficiently learn to imitate an expert and do that, perform well during the learning process. So for those of you who aren't aware of the imitation learning model, let's do a quick recap. Usually RL is based on the MDP model, which basically means here that we have some form of costs which we use to define our task and to optimize our policy. So we find a policy which minimizes the cumulative costs. However, in many real-world scenarios, we don't really have a clear cost to optimize the policy with. Fortunately, we can do this thing in another way by having some samples from an expert, which performs the task in our MDP. And what we would like to do is to somehow imitate or perform as well as the expert. So this work focuses on online imitation learning, which means that our agent is allowed to interact with the environment. And it's not the same as offline RL, in which we just have a bunch of expert data and we somehow need to figure out how to make a good policy out of it. We can actually learn the transition model and move around in the environment, and we just need to imitate the expert. What we will discuss today is, first, we'll introduce the notion of regret for an apprenticeship learning agent. And then we'll analyze OWL, an online apprenticeship learning algorithm, which is efficient and convergent. And then we will show that the OWL framework allows us to derive a neural network variant out of this algorithm, and we will compare it and show that it outperforms some baselines. So, as I told you before, in imitation learning, we don't have any costs. And there is a need to define some other sense of optimization criterion. So what apprenticeship learning suggests is to try to be as good as the expert for any cost signal in some predefined cost set. And this optimization problem is defined in the following manner. This is a min-max game between two players. A cost player, which for a given policy tries to find the worst case cost, the cost in which the expert is better than this policy. And a policy player, which tries to find an optimal policy for this worst case cost. So we try to be as good as the expert for any cost. So there are a bunch of prior works which deals with solving the AL optimization problem. However, they have some drawbacks. So the first one is that they're not really practical in the sense that all these algorithms require to solve an MDP in each iteration. And this does not really allow us to be able to use these algorithms in more complex scenarios. Furthermore, this algorithm assume that the transition model is known. So they are not meant for a scenario in which we can actually move around and interact with our environment. And lastly, they give a pack-like convergence guarantees, which do guarantee that the final learned policy is good with respect to the L objective, but they don't guarantee that in between, while learning, we're trying to be still as good as the expert. Only the final output of the algorithm. So our main contribution in this work will be, first, we devise a more practical algorithm, which does not need to solve an MDP in each iteration. An algorithm can also operate when the transition model is unknown, and we'll have on and regret guarantees for this algorithm, which means that we measure the performance of our algorithm while we learn. So to this end, we first define the apprenticeship learning regret. So this regret, we feel that it makes sense with respect to the AL problem. What we do is we measure the agent performance of the learned sequence of learned policy with respect to the expert. And the performance is measured, because we don't have a cost, it is measured on the worst case cost. So this is different than the usual online learning definition of the regret with respect to some optimization problem. But we actually show in our work that these two regret definitions are equivalent. And we use this equivalency to use some development in online learning and show that the AL problem can be solved using two no-regret algorithms, which are running simultaneously. The first is a cost. Is the way we update the cost. So we update the cost by using a mirror descent update. And also we need to update the policy, and we'll do that again with some stable no-regret algorithm based on the mirror descent for policy optimization. And this thing is what preventing our need to solve the MDP in each iteration. We do stable updates for the policy instead of fully finding the optimal policy for a specific cost. So, and how can we do this policy optimization procedure? So differently than regular RL, here, because we learn the cost signal during the algorithm run, then the costs change between iterations. And this is equivalent to having to solve an adversarial MDPs in which the costs change. And also, we deal with a case where the model is unknown. So we need to add some form of exploration, which is done by using optimistic UCB cost bonuses to the cost that we generate using our cost generator. And actually, we don't need to reinvent the wheel here. The OPPO or POMD algorithm is already doing that, solving these two problems. And that's what we use in the policy optimization procedure. So overall, the OWL algorithm looks like this, at least in high level. So it made of two steps, an evaluation steps in which we need to estimate the gradient of the AL objective with respect to the policy and the costs. And an improvement step in which we use these estimations to update both the policy and the costs in each iteration. Again, we update the policy using the mirror descent policy optimization update, and the cost just using regular mirror descent. And this algorithm leads us to the following convergence theorem. So we can show that the regret of the apprenticeship of the OWL algorithm grows sublinearly with an amount of interactions with the MDP, together with a linear error term, which arises due to the fact that we have a finite amount of trajectories and not the distribution of the expert. Before I conclude, as I promised, our approach is more practical than former approaches, and it allows us to implement an OWL variant, a deep RL or deep imitation learning OWL variant using two neural networks. The first is a cost network, which is trained taking gradients with respect to the AL objective, with respect to the costs, and a policy network, which is a policy optimization which is trained by policy optimization using a mirror descent-like algorithm. And our deep imitation learning scenario here is really close to that of GALE, generative adversarial imitation learning, which is a very common imitation learning procedure. So in GALE, they alternate between two steps, or they also have two
1 minute.
networks. Okay, we're about to finish. So in GALE, the cost network is based on a GAN, and which learns to discriminate between the agent and the expert, and the policy network is trained according to the GAN. So I skip this slide, and what we show that using our algorithm outperforms the use of GALE. Perhaps because it's more theoretically grounded and less heuristic. So I would just conclude in saying that OWL is a general framework to do apprenticeship learning or imitation learning. It has a theoretical side. We can implement OWL in a theoretical manner to show a convergent AL algorithm, but it also has practical implications, and it allows to do imitation learning in a scalable environment. That's all. If you have any questions, I would like to answer.
Anyone has any questions, feel free to raise your hand. Okay, so great. Thank you, Lior. Now Asaf, Yon.
That's all the share screen.
Yeah, Lior, can you stop your screen?
Sure.
Great. Thanks a lot, Lior. Okay. Asaf, we can hear you and see your screen.
מעולה. יופי, אז שלום לכולם, תודה למארגנים שהרימו את זה. אז אני אסף קאסל, ואני אדבר על Online Policy Gradient for Model Free Learning of Linear Quadratic Regulators with Square Root of T regret, שזה עבודה בשיתוף עם המנחה שלי, תומר קורן. אז מה אנחנו מתעניינים? כמו בכל שאר היום הזה, אנחנו מתעניינים ב-Reinforcement Learning, ונסתכל לדוגמה על הבעיה הבאה. נניח ואנחנו רוצים לשלוט ברחפן הזה, רוצים לתכנן איזשהו סוכן שבהינתן המצב הנוכחי הוא בוחר פעולה UT, נגיד את התאוצות של הפרופלורים, ובתגובה המערכת תעבור למצב הבא XT+1, נגיד מיקומים ומהירויות, ותספק לסוכן איזשהו פידבק קוסט CT שמשקף כמה טובים הביצועים הנוכחיים שלו. הדבר הזה באמת דוגמה ממש קלאסית של RL, והדרך הכי סטנדרטית למדל את זה על ידי Discrete Markov Decision Process. כשהפיצ'ר שפה חשוב לנו זה העובדה שהוא דיסקריט, כלומר שהמרחב מצב ופעולה הם מרחבים דיסקרטיים וסופיים. אז הדבר הזה הוא כמובן נחקר המון, וזה מודל מאוד גמיש ומעולה, אבל כל התוצאות שלו תלויות מאוד חזק בגודל בעצם של מרחבי הפעולה והמצב. ובדוגמת הרחפן פה, הדברים באופן טבעי הם רציפים, ולכן אפילו אם נעשה להם דיסקרטיזציה, נקבל שהגדלים האלה הם מאוד גדולים, לצורך העניין אקספוננציאליים בפרמטרים טבעיים של הבעיה. ולכן מעניין אותנו לחקור בעצם דוגמאות של Continuous Markov Decision Processes, ואחת הדוגמאות הכי קלאסיות לזה זה ה-Linear Quadratic Regulator, שזה איזשהו מודל שהוא שאול מהעולם של בקרה. אז פה בעצם המצב XT הוא ב-RD ו-UT הפעולה היא ב-RK, הפונקציית מעברים של המערכת היא ליניארית במצב הנוכחי ובפעולה הנוכחית, ונוסף לרעש אדיטיבי WT, והמחירים הם קוודרטיים במצב והפעולה הנוכחיים. אז במקרה הזה אם אנחנו רוצים לעשות תכנון, לפתור את הבעיה, אז באמת נקבל שהפרמטרים או הקושי של הבעיה תלוי בפרמטרים טבעיים כמו D ו-K והם נורמות של מטריצות, ובנוסף משהו מעניין פה זה שידוע שהמדיניות האופטימלית היא בעצם פונקציה ליניארית של המצב הנוכחי, כלומר אפשר לבחור את UT להיות איזשהו K** XT, כש-K* זה משהו שאנחנו יכולים לחשב באופן יחסית יעיל מהפרמטרים של המערכת. אז עד עכשיו תיארנו איזושהי בעיית תכנון שזה נחמד ויפה, אבל מעניין אותנו ללמוד את הבעיה, וספציפית מעניין אותנו באמת הקריטריון של חרטה. שפה אנחנו אומרים, אנחנו בהתחלה לא יודעים את A*, B*, Q ו-R, והיינו רוצים למזער את סכום המחירים שאנחנו סופקים, תוך כדי שאנחנו מבינים איך אנחנו באמת צריכים להתנהג. והדרך הסטנדרטית באמת לעשות את זה זה על ידי חרטה, שמשווה את הדבר הזה למחיר של אורקל, שבעצם יודע את הפרמטרים האלה מראש, את A*, B*, Q ו-R, ולכן הוא יכול לחשב את K*. אז כדי שהאלגוריתם שלנו בכלל יהיה הגיוני, אנחנו מצפים שהחרטה תהיה תת-ליניארית. אז זה אומר שאנחנו לפחות מתכנסים לביצועים של האורקל באיזשהו אופן אסימפטוטי, וכמובן שנרצה תלויות פולינומיאליות בשאר הפרמטרים של הבעיה, ושהאלגוריתם שלנו יהיה יעיל, שפה אנחנו מתכוונים בזה לאיזשהו פולי-טיים וממורי. בנוסף, מבחינת האובזרבציות, אז בחלק מהמקרים מסתכלים על בעיות שיש לנו משהו שהוא כמו סימולטור, ולכן אנחנו יכולים לעשות ריסט לבעיה מתי שבא לנו, אבל פה אנחנו מעוניינים בעצם ללמוד בצורה שהיא אונליין, מסינגל טראג'קטורי, בלי שום מיפוסים של המערכת. ודבר אחרון זה שהיינו רוצים להבדיל בעצם בין שתי שיטות קלאסיות של RL, שהגישות הן מודל בייסט ומודל פרי, כשבמודל בייסט בעצם בגדול אנחנו רוצים ללמוד קודם כל את המודל של הבעיה, ואז באיזשהו אופן לבצע תכנון כדי להבין מה המדיניות. לעומת זאת במודל פרי אנחנו בעצם מדלגים על השלב ביניים הזה, שהוא אולי עשוי להיות מיותר לנו, ולומדים באופן ישיר את המדיניות. אז מה נעשה בעצם בתחום הזה עד עכשיו? אז בצד של מודל בייסט היה המון מחקר, כבר די מבינים את הבעיה, ובאופן ראשוני הבאסי אדקורי וצ'בסוורי הראו שאפשר להשיג שורש T חרטה, אבל בצורה לא יעילה. דין נטל אחר כך שיפרו את זה לאלגוריתם יעיל, אבל עם T בשני שליש חרטה, ועבודות יחסית חדשות של כהן נטל ומניה נטל הראו שאפשר להשיג באופן יעיל שורש T. אז למה אנחנו מתעניינים בשורש T? אז באמת קצת אחרי זה גם בעבודה שלי וגם בעוד עבודה של שמחוביץ' ופוסטר, באמת הראינו ששורש T זה חסם תחתון לבעיה הזאת, ושמחוביץ' ופוסטר אפילו מראים את התלויות של המימד במקרה הזה. מהצד השני, אם אנחנו מסתכלים על שיטות שהן מודל פרי, אז שתי העבודות היחידות שהתעסקו עם זה עד עכשיו, זה העבודות של הבאסי אדקורי ושל אטל ושל קראוף אטל, שהשיגו רק T בשני שליש חרטה, עם אלגוריתמים שהם בגדול יעילים, נגיד לפחות יעילים כמו האלגוריתמי מודל בייסט. אז מה אנחנו עושים בעבודה כאן? אנחנו כמובן רוצים ומשיגים אלגוריתם שהוא מודל פרי, שיש לו חרטה שהיא שורש T, וכבונוס הוא רץ בזמן לינארי, כלומר הוא מאוד מאוד פרקטי, מאוד פשוט וקל למימוש. אז לפני שניכנס אליו בואו נבין רגע קצת מה קורה יותר בטמפלייט הזה של מודל בייסט עבור למידה של LQR. אז קודם כל מבחינה של אקספלורציה. אז מבחינת אקספלורציה בכל השיטות מודל בייסט עובדים בצורה של הזרקה של רעש מלאכותי לפעולות, כלומר היינו רוצים לשחק איזושהי מדיניות KTXT, ובמקום לשחק אותה ישירות אנחנו מוסיפים מעליה רעש אדיטיבי כדי לעשות אקספלורציה במרחב הפעולה. כמובן שאין בעיה עם הדבר הזה, זה רק תורם משהו לחרטה, וזה עוזר לנו מאוד בשיערוך הפרמטרים, אבל זה קצת פחות ברור איך באופן ישיר לשפר מזה את המדיניות שלנו. כאמור, לשיערוך פרמטרים, השלב הבא במצב הזה הוא באמת לעשות איזשהו least squares estimation כדי לקבל שיערוך של A*, B*, Q ו-R, ופה כבר יש לנו פעולה שהיא, תשימו לב שהיא לפחות אם המימד הוא מאוד גדול, היא יכולה להיות כבדה חישובית. גם מבחינת זיכרון אנחנו צריכים לתחזק משהו, גם מבחינת החישוב, ובנוסף היא מניחה בעצם באופן שהוא מאוד אקספליסיט מה המודל של הבעיה. כלומר, אם המודל הוא קצת שונה, זה בעצם יכול לשבור את הפרוצדורה הזאת. והשלב האחרון זה בעצם ה-Policy Recovery, השחזור של המדיניות, שפה יש את הכי הרבה שונות בעצם, יש שיטות שעושות את זה בצורה גרידית די פשוטה, יש כאלה שפותרות SDP ויש להן רכיב אופטימיסטי, כך או כך זה שיטות איטרטיביות שגם פה החישוב שלנו הוא לא לגמרי טריוויאלי. זהו, ואני אציין גם שבשביל ה-least squares אנחנו בעצם צריכים גם גישה ישירה לאובזרבציות ל-XT ולא רק כדי לשחק את המדיניות. סבבה, אז מהצד השני מה האלגוריתם שלנו בעצם עושה? אלגוריתם מאוד פשוט של policy gradient, אז בכל רגע נתון יש לו את השערוך הנוכחי שלו של המדיניות KT, ואנחנו עושים אקספלורציה סביבה במרחב המדיניות. אז אנחנו מסתכלים ברדיוס RT ודוגמים מהספירה ברדיוס RT יוניפורמית מדיניות אחרות. אז יש לנו KT1, KT2, KT3, ואנחנו משחקים כל אחת מהן איזשהו זמן קבוע, ומשתמשים באובזרבציות של המחירים בלבד, בלי של הסטייט, כדי לקבל איזשהו שיערוך גרדיאנט, ועושים צעד בכיוון הפוך ממנו ובגודל אטה, כדי לקבל את השיערוך מדיניות הבא, KT+1. וככה בשלב הבא אנחנו שוב פעם נדגום איזשהן מדיניות מסביב ל-KT+1, ונשארך גרדיאנט ונמשיך ל-KT+2 וכן הלאה. בעצם פרוצדורה סופר פשוטה, שימו לב שמבחינת חישובים אין פה אפילו כפל מטריצות, כלומר הכל ליניארי בגודל של המדיניות, וגם מבחינת זיכרון רק צריך לזכור את G-hat, השיערוך גרדיאנט, עד שאנחנו מסיימים להשתמש בו. זהו, חוץ מזה אין שום שימוש שהוא אקספליסיט במערכת, ב-A-star או B-star, וכל מה שנשאר בעצם כדי שהפרוצדורה הזאת תהיה שלמה ומובנת, זה להבין איך לבחור את RT, את MT ואת ה-step size של הגרדיאנט, eta. אז נתחיל מ-MT שזה פשוט, אז בעצם הפרוצדורה שהראיתי לכם בשקף הקודם, היא נראית ככה על ציר הזמן, אז אם מסתכלים על אפוק אחד של שיערוך גרדיאנט, אנחנו באמת משחקים כל מדיניות אקספלורציה KTI, איזשהו מספר מיקסינג טיים של צעדים, טאו, שטאו זה איזשהו קבוע שהוא לא גדל כמעט עם הזמן, וכל מה שנשאר זה בעצם לבחור את מספר סיבובי האקספלורציה MT. אז הדבר הזה בעצם בשביל האופטימיזציה שלנו צריך לגדול בצורה אקספוננציאלית, וזה בעצם הבחירה של MT. עכשיו לפני שנגיע טיפה לדבר אולי על איך לבחור את RT, רק נראה מה התוצאה המרכזית. אז בעצם בצורה קצת יותר פורמלית, הרגרט הוא בעצם באמת הפער בין הקוסטים שהאלגוריתם שלנו סופג CT לאורך T סיבובים, T גדול, לעומת CT סטאר שזה הקוסטים שבעצם היינו סופגים אם היינו משחקים את UT שווה ל-K סטאר XT, שאני מזכיר שאת K סטאר אפשר היה לחשב רק אם היינו יודעים את כל הפרמטרים של המערכת. והתוצאה הראשית מראה בעצם שאם נבחר את eta להיות איזשהו קבוע די קטן שתלוי בפרמטרים של המערכת, את RT להיות מספר הסיבובי אקספלורציה במינוס רבע, ואת MT שזה מספר סיבובי האקספלורציה לגדול אקספוננציאלית, אז נקבל שבהסתברות לפחות 1 מינוס דלטה, החרטה היא לכל היותר שורש T, עד כדי כמובן תלויות פולינומיאליות בשאר הפרמטרים של המערכת. אני כן אציין שהתלות במימד פה היא לא אופטימלית, וזה יהיה משהו שמעניין להבין אם אפשר לשפר אותו. זהו, עד כמה זמן נשאר לי?
דקה.
סבבה, אז בדקה אני רק אגיד ממש בקצרה מה הרעיון של האנליזה. אז באופן כללי החרטה מתפרקת לשלושה רכיבים מרכזיים. אחד זה אקספלורציה עקיפה, זה בעצם הרכיב אולי הכי מאתגר ביחס לדברים שהיו בעבר, שהאסנס שלו זה בעצם המחיר שאנחנו משלמים על החלפה של מדיניות. בעבודות קודמות בעצם החליפו מעט מאוד פעמים את המדיניות, ולכן יכלו לעשות איזושהי אנליזה נאיבית שמראה שהגורם הזה תלוי במספר ההחלפות. אבל אצלנו אנחנו מחליפים מדיניות בעצם T גדול פעמים, ולכן זה משהו שאי אפשר לספוג. אבל אפילו אם מנסים לעשות משהו קצת יותר חכם, מקבלים שזה תלוי בסכום השינויים של המדיניות, שזה בעצם סכום על RT, שזה גם לא מספיק טוב, ובעצם השיפור העיקרי שצריך לעשות פה, זה להגיע לזה שזה בעצם תלוי אחרי כל מיני ביטויי ריכוז מידה, במה שכתוב כאן, שהוא תלוי בסכום על RT בריבוע. מחוסר זמן, אני לא אספיק כל כך לדבר על בדיוק מה זה הביטוי הזה, מה שכן חשוב, צריך בעצם בעוד כמה נקודות להגיע לתלות ב-RT בריבוע, ברדיוס אקספלורציה, שזה גם באקספלורציה הישירה, כלומר הפער בין KT למדיניות אקספלורציה שאנחנו משחקים, שהיא תורמת לנו בעצם לשערוך של הגרדיאנט, וגם בסוף באופטימיזציה עצמה אנחנו צריכים להגיע לתלות ריבועית בשגיאת גרדיאנט, ולא בתלות ליניארית שאולי אנליזה טריוויאלית יכולה להשיג. זהו, נשמח לענות על שאלות אם יש לכם, תודה.
היי אסף, שומע אותי?
כן.
תודה, מעניין. שתי שאלות שיש לי זה אחת כללית, והשנייה קצת יותר ספציפית. אז הכללית היא, למה סקוואר רוטי? כאילו למה זה, יש חסמים תחתונים, והאם יש חסמים תחתונים על הדבר הזה? והשאלה השנייה היא, אם אתה בעצם משתמש באיזה סוג של הזום אופדינג בסוף בשביל לקבל את הרגרט.
בסדר, אז סקוואר רוטי, כאמור יש עבודות קודמות, גם אחת שלנו וגם אחת של שמחוביץ' ופוסטר, שזה כאמור האופטימום, עד כדי תלויות מימד.
יש לזה איזושהי אינטואיציה?
זה קצת מוזר, כי יש פה איזה מין טרייד אוף כזה, שמצד אחד הרעש הפנימי של המערכת נותן לך אקספלורציה חינם, מצד שני אתה לא מצליח להפריד באיזשהו אופן בין השערוך של A-סטאר ל-B-סטאר בלי לעשות איזושהי אקספלורציה נוספת, והיא בעצם מאלצת אותך לשערך את הפרמטרים של המערכת רק עד כדי T במינוס רבע ולא T במינוס חצי, כמו שהיית מצפה מאסטימציה סטנדרטית.
אוקיי.
זה פחות או יותר אינטואיציה. האם יש איזה שימוש בהזום האופדינג בתוצאות שלנו? בהחלט, כן. לגבי החלק האחרון. אז כן, יש פה שימושים כאלה.
סבבה, תודה.
כיף.
היי אסף.
היי.
שאלה קטנה, כמה אתה חושב שההנחה על ה-covariance matrix של הרעש היא חשובה? עד כמה שאני מבין ברוב העבודות האחרונות, ה-covariance matrix הוא זה שכזה דרייבינג את האקספלורציה, ואם אני לא טועה אצל יאסין, אני חושב שזה לא המצב, ואני תוהה כאילו, מה דעתך בנושא הזה? האם...
אתה מתכוון לרעש האינטרינזי של המערכת, לזה שהקומפרנס שלו הוא לא אורבאונדד.
כן, כן, אני מדבר על ההגבלים הנמוך של WT.
כן, האמת שזה כן, זה משהו שחשבתי עליו בזמנו, אני לא לגמרי בטוח. השיטה שלנו בהחלט גם תלויה בזה בצורה חזקה. אני רוצה להיזכר אם יש איזו עבודה של אלעד חזן גם שהצליחה איכשהו קצת להימנע מזה. אבל כן, בגדול זה די קריטי, אתה איכשהו צריך לקבל אקספלורציה של המערכת, ובלי זה יש חלקים כאלה שאתה לא יודע בעצם אם הם עוברים אקספלורציה או לא.
כן. אז אתה אומר שיכול להיות שבלי זה, אז אפילו שורשתי זה לא הלואוור באונד האמיתי.
כן, כלומר, לצורך העניין, בלואוור באונד יש באמת תלות גם במינימום value, כאילו כן. אבל זה עדיין, הדברים האלה הם תמיד עדינים, זה מעניין קצת לבדוק את זה, אבל זה בהחלט נראה שזה כל מה שאני ראיתי הוא קריטי.
כן, שזה קריטי, מגניב, תודה.
יופי, תודה רבה לאסף, אנחנו לוקחים הפסקה קצרה, אנחנו ניפגש שוב פה ב-2:30 עם שיחה מוזמנת של ישי מנצור, פרופסור ישי מנצור, נתראה.
אוקיי, טוב, אני מקווה שכולם חזרו, אז הדובר הבא שלנו זה פרופסור ישי מנצור מאוניברסיטת תל אביב ומגוגל ריסרצ' בתל אביב, עושה הרבה עבודה פונדמנטלית על אונליין לרנינג, אינפורסמנט לרנינג, מולטי-ארם בנדיט, ואני בטוח שגם שיהיה לה דברים מעניינים לספר לנו גם היום. אז בבקשה ישי.
תודה רבה אביב. Thank you very much everyone for being here. And I think it's really a great initiative and it seems highly successful, way over 100 people all the time. So Today I'm going to talk about a very recent work and a very specific work that I did with a few colleagues in both in Google New York, Chris, Dan, and Merir, and two colleagues from Cornell, Ayush and Kartik. So I'm going to talk about agnostic reinforcement learning with low-rank NDP and rich observation, and hopefully by the middle of the talk, you'll understand the title, and this is sort of where I'm aiming, right? So you heard a lot today about reinforcement learning. You heard a lot about how great it is, and it is in the center of the world. In essence, this is like a nice picture, sort of trying to say where reinforcement learning is. But given that you are in this day, I don't think that I need to sell you what is reinforcement learning and how central it is and how important it is to various disciplines. And if looking on a sort of recent success stories, and I think sort of those success stories were mentioned more than once today, the big success story in reinforcement learning are still in playing games, starting with Tesaro backgammon and leading up to the DeepMind recent Go reinforcement learning and the Atari games. Of course, sort of when we are aiming forward, really the motivation behind much of reinforcement learning is to control robots, and also sort of a few typical examples of when we're talking about controlling robots, what are we aiming for? So this is like a very brief introduction because I assumed that after I think 5 hours of already in the day, you've seen it all, and I don't need to sell to you too much anything about the RL success stories. So much of my talk is going to have a series, a sort of context, and just to make sure that we are all on the same page notation-wise and terminology-wise, let me sort of redefine again things that you saw more than once today, but just for the sake of making sure that you're all with me. So I'm going to talk about Markov decision processes. I think like almost all the talk today, maybe with the exception of the LQR, describe this model. So we have a finite set of states, I'm going to call it S, and a finite set of action, I'm going to call it A. We'll have a transition probability matrix. Those are going to be the delta. So delta is really saying that given that we are in a certain state, S, and performing an action A, what is the probability that we'll move to a state S prime? And we'll have a reward function, which could be a random variable, but for the most part, we'll sort of think about its expectation. So when you're thinking about the MDP model, you should think about sort of states are really the environment. When I'm in a state and I'm doing an action, there is a stochastic distribution of next states. So states, action, and transition probability are really describing the environment and the dynamics in the environments. The rewards are really aimed at setting the goal and the objective. And when I have a run of a policy in an MDP, I'm like this is example of a run, this purple line. So it's you start with a state S0, you do action A0, you see a reward R0, you move to S1, and that's follow, okay? I sort of assume that all of you saw this terminology, but I wanted to make sure that we have the same notation and same things in the back of our mind as we are viewing it. Okay. So now let's say one slide about learning and MDPs, tabular learning, tabular MDPs. So when we think about learning in a tabular MDP, what we really mean in most cases is that we have a procedure that we are sort of running it, and what it does, it learns both the dynamics and the rewards. In some sense, learning the rewards is both easier and not, and in many contexts, sort of secondary to learning the dynamics. And we have a bunch of classical algorithms that sort of do this task, right? Kersen-Singh E-cubed algorithms basically learns the dynamics, ignores the rewards. The R-max algorithm of Braffman and Tenenholtz really learns dynamic and rewards and focuses on the optimal policy. And in general, okay, sort of, we do know the sample bounds of learning a tabular MDP. It's polynomial in S and A. And for the finite horizon, I think the latest work that gives the tightest sample bound is by Dan et al. We also have like another stream of work, which is, I think, very related, also, which is really model-based, which is doing online regret minimization. So in this stream of work is like, we're not trying only to learn the model, but we are trying to act almost optimally in the model in the sense of the regret. We would like to compare the sum of the rewards of our policy to the optimal policy, and the main highlight, I think, in this line of research is UCRL that does achieve vanishing regret, and there are many follow-up works on various variations on it. So basically, if you run T episodes, and for the most part, I'm going to think today about the return as finite horizons. So we are rerunning T episodes of finite horizons. Those work can guarantee a square root T regret. Again, the bounds are going to be polynomial in S and A. I'm ignoring the dependency on S and A. And Azar et al. Really gave the tight regret bound here, really optimizing the terms and giving a matching lower bound. Okay, so this is like in one slide about learning tabular MDPs. But I think as many speakers today has a motivation, like you would do want to go to a large state MDP. So when I talk about a large state, it could be either exponential or continuous, but essentially it's going to be the case that you cannot really encode in a table the entire state space. So in practice, a sort of like large state space MDPs are the basic problem, and there's two sort of different approaches of handling them, and of course there are sort of things which are in between. In approximation, you are trying to approximate the value functions of your policy, or you can try to maintain a gradient and do gradient updates of your policy, and hopefully it will converge. So this is from the practice side. From the theory side, we have to admit that we have fairly limited understanding of what we can show in a large state space MDP. So this is sort of where this talk starts. And a recent sort of interesting model to start and explore the possibility of a large state space MDPs is a model which is called rich observability. So I sort of, okay, let me sort of highlight the simplest case of rich observability. It's called also block MDP. And this is the idea that a single state can have many names. So you observe various names of a single true state. So you can really assume that there is a small latent MDP that you don't observe the name of the state, but you observe sort of for each state, you do observe some unique identifier, but they come from such a large observation domain that you never see the same observation twice. And the goal is, of course, is to try and learn the MDP, or to try to find the optimal policy of the MDP where you depend only on the latent MDP parameters. Okay, so just for motivation, so why is it reasonable at all, right? So think that like in machine learning, many times that when we are thinking about the attributes, right? We select the attributes. And the usual wisdom is that, yes, we can put, it's better to add more attribute than to take less attribute, because later the learning algorithm can focus on the relevant attributes. Using this logic, right, we are really defining the name of the state. And it's probably better to sort of, if we are unsure whether some attributes are really important in defining the state, it's better to put them in than keep them out, because we do want the expressiveness. But now when we have like multiple attributes which are sort of redundant, this would lead us to the fact that we have multiple names to the same true state. Right? So the main challenge now is that although we do have a huge MDP, right, it really encodes a small latent MDP. And this is sort of started with the work of Krishnamurthy et al. 2016. And this is sort of a long list of work. And let me try to summarize what they did. I think the first work is they made two big assumptions, both that the MDP is deterministic and that they have an access to a function class, to a value function class that includes the optimal value function or the optimal Q function. And using this, they were able to derive an algorithm. The list of works here are trying to get less and less assumptions, but still almost all those works essentially need to assume that you do have a function class that describes the optimal value function and it's realizable. And in addition to this, you do need some assumptions about the MDP. Okay. So now let me sort of describe formally the rich observability, because this is sort of what I want to focus on, and then sort of I can describe our results. So in the rich observability, right, we have a huge observation space. This is X. And think of it as like infinite or exponential size or whatever. But really, you will never see the same observation twice. Policies are defined over the observations, right? So a policy would be a mapping of an observation to an action. And what we are interested in is, rather than sort of thinking about value function, is thinking about a policy class. So we are given a specific policy class, and our goal is to find the best policy from the policy class. Okay, all right? So again, if the policy class doesn't have any good policy, then we probably end up with a very bad policy. But implicitly would like to assume that this policy class has at least reasonable policies, and then we are sort of learning a very reasonable policy using this policy class. One way to think about what we are trying to do is like in supervised learning, the policy class is equivalent to a hypothesis class, and in supervised learning, we would like to compete with the best hypothesis in the class. So here we would like to compete with the best policy in the class. Okay, and our objective is going to be the finite horizon. So we are going to look at the sum of the rewards of the first H time steps. But the results do apply almost the same to the discounted setting. Okay. So what is our objective now? So we want to pack learn policies. What do I mean by pack learn? So I mean that we need a way to generate samples. So we have some number of samples which is going to be a function of the policy class, the accuracy epsilon, and the confidence delta. And now after we generated those sample trajectories, we'll have an algorithm that would run and return us a policy from that class, such that what do we want to guarantee? that with high probability, probability 1 minus delta, the value of the policy that you return is very similar to the best policy in the class. So this is the accuracy parameter epsilon, says by how much is the policy that you return worse than the best policy in the class. Okay, so this is defining what do we mean by pack learning a policy. And notice that I didn't put the sample size space into the function that generates the samples, the number of samples. And what we are aiming for is sort of a sample bound which would be independent from the state space. Okay, so this is our goal. Before going to the rich observability, let's just remind ourselves like two very simple ways of learning a policy class. The first one is probably the simplest one, is simply enumerate all the policies in the class and basically test each policy separately. So for each policy, run it for 1 over epsilon log the number of policies over delta. This would give you an epsilon approximation of the return of that policy. And of course, now choose the best policy. This would obey the pack criteria that you want, and our sample size would be, notice like the number of policies over epsilon squared, okay? So this is sort of, the weakness here is, of course, that we have a dependency on the number of policies. A different way of achieving this goal, this is from a work with Keynote and Andrew Neg. We used a sample trajectory. And here the idea is sort of use a policy which is just a random policy. Choose action randomly. And now, if you sampled something like exponential in the horizon, a to the h times 1 over epsilon squared log pi over delta, then it means that for each policy, more or less, this is going to be the number of trajectory consistent with the way it selects action. So now we get a sample bound. So the good news, we got rid of the number of policies. We don't depend in both bound on the number of states, but we are exponential in the horizon. Okay, so what am I going to tell you about here today? So today I'm going to show you for the rich observability, both an upper bound and the lower bound. And there is good news and there is bad news. The upper bound and lower bounds are almost matching. Unfortunately, both of them are exponential in the dimension D. So I'm going to define it formally in the next slide, but think of D as the number of states in the latent MDP in the rich observability state setting. Okay, so this is much smaller than really what we observe, but it's still something which can grow very fast. But from a theoretical perspective, at least we completely understand now what is the sample complexity for learning a policy class in a rich observability model. We do have extension when the MDPs is nice and with some dependency on the eigenspectrum. Near the end of the talk, I will reach it and then we can talk about it some more. Okay. So just recapping the model, right? We have a set of action, we have a set of observation, which is huge. Our objective is a finite horizon, 8 steps, and we are given a policy class. So the policy class is mapping observation to distribution over actions, and we have a transition kernel. So the transition kernel takes an observation. So remember that each observation is related, it takes an observation and an action and generates the next observation. So for a block MDP, the observation is related to a unique state. But we are going to talk in a more general sense, in which observation do not have to really map back to unique states. So now when we fix the policy, right, so we fix the way that we are choosing action, we are going to get some transition matrix, which is a Markov chain induced by this policy, right? So this Markov chain really says what's the probability of moving from observation X to observation X prime, given that we follow the policy pi. And the assumption that we make, this is the deal that we had before, is that for any policy in our class, the rank of this transition matrix, this Markov chain, is at most D. So for the block MDP, right, for any policy, in our policy class or not, the rank would be at most the number of states in the latent MDP. Okay. Okay. So now let's see, I'll try to sort of recap the model and start building the intuition of where I'm aiming, or how are we aiming to solve our problem. So let's fix a specific policy. Now, we fix a policy and let's fix a certain time in the horizon. So small h is some time between 1 and the horizon. So we can look at, so really what we would love to know is the expected reward at time h, because the value function would be just the summation of those expectations, right? Okay. So remember this sort of reward per time. This is going to be the main thing that we are going to focus on, right? Okay, but now I want sort of to move to more matrix notation that I'll be using in the next few slides. So given a policy, I can define a vector which is the reward function, right? Because this reward function for every state, for every observation X, right, given the policy, can compute the expected reward of that policy, given that we are in observation X, right? Okay, so this is a vector of the rewards of the policy. So the next step is we want to look on the observation distribution. So the observation distribution is what is the probability that at time h we are in state X. So notice that both the reward function and the observation distributions are huge. They are defined over the observations. But the point that I would like you to notice is this one, and we are going, next slide, use it very strongly. I can write the next time step distribution. So the observation distribution at time h plus 1 is really the observation step at times h times this matrix, right? The matrix T pi. So this is the Markov chain related to policy pi. Okay? And now when I'm looking at step h plus 1, I can take this matrix and raise it to the power of h. And when I multiply it by mu1, the initial observation distribution, this would give me the observation distribution at any time, let's say h plus 1. Okay, so given this reward function and observation distribution, their inner product really defines the expected reward at time h. Okay. So that's the intuition of what we'll be doing, right? So think about the reward sequence or the expected reward sequence, right? Those are the rewards at times 1 up to the horizon. Now, each one of them I can write as the initial observation times the Markov chain of the matrix of the Markov chain of the policy times the reward function of the policy. But the main thing is those transition functions, T pi, which are raised to the power of h, right? So what I would really like to claim is that when you look on this reward sequence, it's going to be autoregressive and of degree D. And one easy way to see why is to use the Cayley-Hamilton theorem. So this theorem says that if you have a rank D matrix, then and you raise it to the power of larger than D, then you can write it, the new power, as a linear combination of the D previous powers. Right? So really it says that if you raise it to the power of D plus 1, you can write this matrix as a linear combination of the previous matrices. This means that this part could be written as a linear function of the previous matrices, and therefore it's going to be autoregressive. Okay? Just as a side note, there are many proofs of the Cayley-Hamilton theorem, but one very simple way of proving it is just looking at the characteristic polynomial. And the point is that T pi to the H would come out from this characteristic polynomial is the only thing. And then it would give us the linear dependence on the other parameters. Okay, but this is a side note. Okay. So how do we want to use the Cayley-Hamilton theorem, sort of? So a more elaborate way of describing the theorem is saying you have a matrix of rank at most D, you take its eigenvalue. Actually, I want all the eigenvalues to be non-zero, so I want it rank to be exactly D. Then I can write, it's not only a linear function, but it's a very specific linear function. So I can write m to the power of D plus 1 as a linear combination of the lower powers of m. And in fact, I can write explicitly the coefficients also. So the coefficients are given explicitly as a function of the eigenvalues of the matrix. Okay. So notice that, okay, when we talk about the rewards, think about those things as T pi. Now you can multiply it by mu1 from one side and from the other side by the reward function of the policy. So those are just the expected rewards. So this implies that the expected reward are really a linear function. So here is like an imaginary algorithm. So suppose someone gave us the exact expected rewards for the first D time steps. Okay? And suppose that some magic way, we know the eigenvalues of the matrix T pi. Just remember, T pi is a huge matrix that we don't even want to think about writing it down. But suppose that in some magic way, someone gave us the eigenvalues of that matrix exactly. Now we have an algorithm. So what would our algorithm do? So basically it will take the first D rewards and now sort of unwind and compute the expected reward of each time. For the times 1 up to D, we have them explicitly. And for each time which is larger than it, we'll take the D previous rewards and we take the formula of the Cayley-Hamilton theorem, and this gives us the next reward. So essentially, if we knew exactly the first D rewards and we knew exactly the eigenvalues, we can exactly compute the expected reward at any time, h. And if we are interested in only the first h time steps, we just need to sum them and get exact value function. Okay? Okay. So this is sort of what we would like to do, but of course, we assume too much here. Okay, so what are we missing? So we are missing the first D expected rewards. So we need to estimate them, and we want to estimate them accurately. So the way that we'll estimate them is we'll use some exploration policy. The simplest one is using random, uniformly random actions. And then sort of given pi, we'll take the trajectories that follow pi and use them to estimate the rewards. Unfortunately, of course, we will have an error here. The error could be as small as we like, but we will get an error. Okay. A more confusing thing is the eigenvalue, right? We need to estimate them, but we never want to write the matrix. So we will take care of it. But what are things that we need sort of to think about when I'll show you sort of the high level of the algorithm? Really, the main issue is how do error propagates? Because in the previous slides, hopefully I convinced you that if we have no errors, then we can compute exactly things and everything is perfect. Why will we have errors? Of course, we'll have error because we are estimating the initial rewards. Okay, if we take m samples, we'll get an error of 1 over square root m, and we'll have error in the eigenvalues, which would be also a pain. But the major result that I'll claim is that the errors will increase over time, but they will only increase polynomially in the horizon. Unfortunately, they will increase exponentially in the rank. Okay, so this is a good time to switch and start describing the algorithm. So the first thing is that sort of we want like an exploration policy. And the exploration policy is a very dumb one. Just use a random policy for 3D time step. Remember, we want a horizon H, but what we are really interested in is only in the 3D first time steps, because this is where we would like to estimate the rewards. Notice that I moved from D to 3D. This would be later important, okay? So if we make a sample size which is large enough, exponential in D, we'll get enough consistent trajectory. So now for each policy, I can use the sample size, estimate the initial reward. And the main thing is sort of, I need to solve for the autoregression. And in order to have a handle for the autoregression, I'll solve it using the eigenvalues. And this will be sort of in the next 2 to 3 slides. Given that I will do it, then I sort of will assume that I have a perfect model and use it to predict. Okay, this is the outline of the algorithm. Right. Okay, so how does the algorithm really sort of work? So I'm describing the algorithm per policy. So we have initial rewards. They are just an estimator of a sample of size m, so they have an error of a scale like 1 over square root m. The main part is that we'll need sort of an optimization problem. Unfortunately, it's not going to be a convex one. But really sort of we are looking here for the eigenvalues. Those are d different numbers. They are all bounded by 1. And what we are really optimizing is we are sort of thinking that those are the true eigenvalues. We are using the coefficient of the Cayley-Hamilton theorem to produce an autoregression and then estimate the error, and we'd like to minimize the error that we get. Okay? If we had the R hat perfectly, this delta would be 0. And soon we'll sort of see what happens when it's not perfect. Okay, we solved for the initial reward, we solved for the eigenvalues. Now we're going to make a prediction as though as we have the correct model. Okay, so we are just going to run the autoregression. This is going to give us the estimates of the expected reward at each time step. We sum them up and get the expected reward, the value function estimate. Okay. I'm not really going to show you the proof, which is unfortunately covers too many pages, but I try sort of to give you sort of a highlight of how the proofs would sort of go. So the easy part of the proof is claiming that the initial rewards are all estimated well, let's say up to an error of eta. And now we are running an optimization. The point is that we can always think what would happen in the optimization if we use the true eigenvalues. Then we can claim that the error that we get is not too large. It does blow up because we do have error initially, but it will go up only exponentially in D and does not depend on age. Okay, now we are going to use the eigenvalues that we received and sort of estimate the expected reward, both for the things that we estimated initially with the autoregression, and then for the other steps that we didn't estimate explicitly. So in the first step, it's going to be something which is only exponential in D. Later, this will have a blow-up which depends on H, which goes something like H to the D, but depends on sort of the maximum error that we have here, which is something like this, okay? So when we combine everything, so notice that really what we are controlling is the eta. This is sort of the error parameter in the first 3D time steps, and this is sort of controlling how well by having more samples, we can reduce this eta. What we are suffering a blow-up of errors as the autoregression, first of all, even initially, it grows exponentially in D, and as you're going to farther and farther values, you do suffer also a loss with an error that depends on the horizon age. Okay, so this is sort of the upper bound, which is the main part. Let me sort of describe you, like in a few minutes, the lower bound, which is sort of matching. Okay, so the classical lower bound would say, two action, let's build a complete binary tree of depth H. All the rewards are 0 except for one leaf. So you have 2 to the H policies. Each policy is going to a different leaf. One of them is optimal, but you need sort of order of 2 to the H to find the optimal policy. Okay. Now, we want to do something similar yet different for a low rank MDP. So the idea is the following. We are going to build a low rank MDP for each policy, right? And basically, the upper row is going to be governed by the policy, and each time an action which is different than the policy, which if we wanted to be optimal for this MDP, we go to the lower level. And at the end, if we got to the good state, we have an epsilon bias compared to getting to the bad state. This should be B, sorry. Okay? So the idea is that a good policy should stay at the upper level. So first of all, the rank of this MDP is order of D, actually bounded by 2D. The observations are sort of just random from a huge domain. So essentially they don't convey any information. We do need to say it formally in information theory term, but you can trust me on here. Now the transition probabilities are D over H. So why is this important? Because the length of this chain is D, but I'm going to look at horizon H. So if I take transition probability D over H, it means it's sort of most of like, with a constant probability, I'll be able to reach the end of the chain. I need to make some assumption about my policy class, and really my assumption is going to be that policies are very different in the way that they choose actions. So any two policies, if you look on the number of times they disagree, it's at least a quarter of the observations. And then you can very easily pack a very large state space. So really, what would this guarantee us? This guarantees that if we take a policy, it's very likely to deviate from the optimal policy unless it's the optimal policy, right? So to get the lower bound right, we need to establish that there is a gap between the best and a non-best policy, which is an order of epsilon. Now the point is, the learner can use arbitrary policies. He's not limited to the policy class. But the point is that no matter which policy the learner will select, he wouldn't be able to rule out too many of our policies. So this parameter C is really saying how many of these policies is he able to rule out, and we'll get a lower bound, which now really scales like the number of our policies over epsilon squared. And this is sort of a bound of the number of policies that you can pack. It's okay. So this is sort of, okay. So what did we show? We showed that really the exponential dependence on D is indeed real. Okay. So before concluding, let me give sort of two additional results. So first about POM DPs. Okay. So we cannot run our scheme for POM DPs, but if we look at memoryless policies, what is also called reactive policies, so policies that depend only on the last observation, right? They don't fall in this block MTP paradigm or the rich observability paradigm, but essentially they generate a Markov chain over observations. So anything that I talked so far really applied also to POM DPs when we look to reactive policies. Essentially, if you look at their expected rewards, it's going to be an autoregressive sequence, and this is sort of the main thing that we are using, and all the tools that we are using would also apply here. Okay. Okay. We can get slightly better bounds if the MDP, let's call, is nice, right? We can get the algorithm to be adaptive to the eigenspectrum. So basically, if the eigenspectrum is nice, we can get a better approximation. For example, if the MDP is well mixing, we can get a better sample complexity bound and also a matching lower bound. Also, we can be slightly adaptive to the dimension, basically improve the bound depending on the unknown dimension. Unfortunately, in this case, we still need the sample size to be fixed in advance. It's only the case where if the hidden dimension is smaller, then we'll get a more accurate estimation. Okay, so I think I'm almost out of time, but sort of some thoughts about this recent work. So we do give a tight sample bound to a highly popular recent model of rich observability. The sample size depends polynomially on age. I guess it's not a plus that it depends exponentially on D, but this is sort of what it is. So of course, the minus is that we do get still stuck with an exponential sample bound, and the procedures that I showed you is not efficient. What I think it really opens the door to, so now it can justify to have additional assumption if you really want to get a better sample size. But from the theory perspective, we completely characterized the sample complexity. And in fact, that's sort of the characterization is really saying that the first D rewards really completely define the return. So for those of you familiar with in machine learning, learning hyperplanes, so there is, for learning hyperplanes over the Boolean cube, there is a chow parameters, which is really the correlation of each one of the dimensions with the target hyperplane. And those parameters really completely specify the hyperplane. In our case, the D first expected rewards completely specified all future rewards of the MDP. Okay, so I think I'm exactly out of time and I'm exactly done. So thank you very much, and I'll be glad to take questions if there are.
אוקיי, תודה רבה ישי. אז אסף, יש לך שאלה?
כן, ישי, I wanted to ask, I know there are some old works on representation learning, and they really remind me of the things that you are doing here, where they look at they take the feature vectors for linear function approximation, the application of the Bellman operator on the rewards for several steps. Have you connected those two topics?
So we are not doing a function approximation, and remember, sort of the main difference is that you're never going to see the same state twice. Right? So you're never going to see the same sort of feature vector. And,
yeah, definitely. It's a different setup. I'm just wondering, there is this like sub...
Okay, I need to think about it more, but off the top of my mind, I don't have a good connection. But...
Okay, thanks.
Okay, Yonathan, שאלה זריזה? יונתן?
Yes. Can I want to understand the optimization problem that you're trying to solve. So you optimize over the alphas as well?
No. The alphas are the Kelly-Hamilton functions.
So you estimate the matrix T pi?
No. I don't estimate the matrix. I'm learning directly the eigenvalues.
Directly the eigenvalues for any pi?
No. So I fix a pi, and for this pi, I'm solving this optimization problem. And in this optimization problem, like what I could have done, I could have just tried to solve a regression problem. And in practice, I expect it to work very well. The point is that by solving a regression problem, we were not able to bound the errors that you get as you unfold this. You can think of it as a time series, right?
Yes. Yeah, exactly.
So I expected to get some more help from the time series people, but we didn't get any results from there that we can really sort of...
I see. So like estimating the powers and then do a regression is not going to work.
I didn't say it's not going to work. I said we failed.
Okay.
Thank you very much.
אוקיי, אז תודה ישי, עכשיו אנחנו נמשיך להרצאות, לסשן הבא של ההרצאות, וראשון נדבר אורן פאר.
שלום לכולם, שומעים אותי?
כן.
אז שלום, אני אורן, עכשיו אני אציג לכם את העבודה שעשיתי בשיתוף עם חן טסלר, נדב מרליס ורון מאיר. לעבודה קוראים Ensemble Bootstrapping for Q-Learning, ובגדול היא מתעסקת באיך להוריד שגיאות שערוך באלגוריתמים של מבוססים על Q-Learning, באמצעות אנסמבלים. אז נתחיל. אז כולנו, אני מקווה, מכירים את Q-Learning, אלגוריתם אוף פוליסי כנראה הכי מפורסם, שמנסה ללמוד את Q-Star, והוא עושה את זה על סמך אינטראקציה וניסיון עם הסביבה, והפעלה חוזרת של האופטימל בלמן אופרטור. עכשיו, בלמן אופרטור יש בתוכו מקסימיזציה, שהמקסימיזציה הזאת גורמת לזה ש-Q-Learning יעשה שערוך יתר או overestimation ל-Q-Function. אז הסיפור הזה גורם להתכנסות איטית ולפעמים לביצועים נחותים בחלק מהדומיינס, ויותר מזה, overestimation הוא נחשב לאחד הגורמים העיקריים להתבדרות של האלגוריתמים מבוססים Q-Learning, דווקא ב-Deep RL. אז מתוך המוטיבציה הזאת, דווקא הראשונה, ב-2010 ואן הסלט פרסם אלגוריתם שנקרא Double Q-Learning, שהוא למעשה מאוד מאוד דומה ל-Q-Learning, יש פה אינטראקציה עם הסביבה ואקספלורציה, אבל העדכון של הבלמן equation פוצל לשני חלקים. נגיד, יש לנו שני משערכים, QA ו-QB, ונגיד שמתקנים את המשערך הראשון, QA, אז המקסימיזציה מחולקת לשני חלקים. החלק הראשון זה בחירת הפעולה ב-next state, שנעשית על ידי המשערך QA, ואז הערך עצמו מחושב על ידי QB בנקודה ש-A בחר. אז בכחול רואים את ההפרדה לשני דאטה סטים, כי כל פעם אנחנו מתקינים רק משערך אחד, אז הם מתאמנים על סט שונה של הדאטה, ובאדום רואים את ההבדל המשמעותי מ-Q-Learning. אז דאבל Q-Learning מתמודד עם הבעיה הזאת של Overestimation, אבל כתוצאה מכך הוא עושה דווקא Underestimation, ובאופן כללי אפשר להגיד שהביצועים של Q-Learning ודאבל Q-Learning מאוד מאוד תלויים במה שאנחנו קוראים הטבע של הסביבה, האם כדאי להיות בה אופטימי או פסימי. אז Q-Learning הוא עושה Overestimation, לכן הוא באיזשהו מקום אופטימיסט, ואנחנו מצפים שהוא יפעל טוב בסביבות שבהן אופטימיזם זה רעיון טוב, סביבות שמעודדות אופטימיזם. אני עוד אסביר בדיוק מה זה אומר. אבל דאבל Q-Learning, בניגוד אליו, הוא פסימיסט, לכן אנחנו מצפים שיפעל טוב בסביבות שכדאי להיות בהן פסימיסטים. ובאופן כללי אנחנו לא יודעים אם הסביבה שלנו אופטימיסטית או פסימיסטית, לכן היינו רוצים אלגוריתם שהוא טוב במקרה הכללי או רובסטי. אז מתוך הצורך הזה לבדוק סביבות שהן גם פסימיסטיות וגם אופטימיסטיות, אז הצענו את הסביבה הזאת שאנחנו קוראים לה Meta-Chain MDP, שהיא מורכבת למעשה מ-Chain MDP שזו סביבה די מוכרת, שבכל שלב, בכל אפיזוד, אנחנו מגרילים MDP יחיד, והסוכן מתחיל ממצב A, שם יש לו או ימינה או שמאלה, שתי פעולות אפשריות. אם הוא לוקח ימינה הוא מגיע למצב טרמינלי ולא מקבל ריוורד, חוזר חזרה לנקודת ההתחלה, ואם הוא לוקח שמאלה הוא מקבל ריוורד, גם לא מקבל ריוורד, ומגיע למצב BI, שבמצב BI יש לו K פעולות אפשריות, שלכולם אותה תוצאה, מגיעים למצב טרמינלי DI, שנותן ריוורד שהוא מתפלג גאוסי עם μi ואיזשהו סיגמה. עכשיו, ההבדל בין ה-Chain MDP הרגיל הוא שיש הרבה צ'יינים כאלה, ובכל אפיזוד אנחנו מתחילים באחד אחר, לכן כל פעם יהיה פה μi שונה. אז חשוב לבנות האינטואיציה ש-Q-Learning צפוי לתפקד טוב ב-MDP שבהם ה-μi הזה הוא חיובי, כי גם אם הסוכן יקבל פה איזה reward שלילי קטן, כי התוחלת פה היא חיובית, עדיין בגלל שהוא אופטימיסט הוא המשיך ללכת ל-DI ובסוף גם מתכנס אליו וזה הדבר הנכון לעשות. אותו דבר עבור reward עם תוחלת שלילית, בהם גם אם הוא יקבל reward חיובי קטן, הוא עדיין יגיע ל-CI בגלל שהוא כזה פסימיסט, וזה הדבר הנכון. אז זה האינטואיציה שלנו בעצם, וגם רואים את זה בתוצאות. פה יש את ה-correct action rate, בירוק, כאשר מיו שלילי, הסביבות הלכאורה פסימיות, אז אנחנו רואים שדאבל Q-Learning הוא טוב, ו-Q-Learning הוא יותר איטי, ובסביבות שהם יהיו חיובי, אנחנו רואים ש-Q-Learning הוא מאוד מאוד מהיר, ודאבל Q-Learning לוקח לו המון זמן להתכנס. יפה לראות שבאופן כללי דווקא Q-Learning, האלגוריתם הישן והטוב, נותן את הביצועים הכי טובים, ואפשר לשייך את זה לסביבה שהוא לוקח את כל הדאטה כדי לאמן משערך אחד, לכן יש למשערך הזה בערך פי 2 עדכונים, בהשוואה לדאבל Q-Learning, ופה רואים את הבייס של המשערך ממצב A. רואים ש-Q-Learning מתכנס למשערך בלתי מוטה מלמעלה, מוטה חיובי, זה Overestimation, ודאבל Q-Learning מלמטה בצורה יותר איטית. אז ראינו שהבעיה היא במקסימיזציה, אז בברמן אופרטור, אז בואו נעשה צעד הצידה ונסתכל על המקסימיזציה הזאת ספציפית בתרחיש סטטיסטי, שהוא לא קשור ישירות ל-RL. נניח שאנחנו מנסים לשערך את התוחלת המקסימלית על גבי סט של משתנים אקראיים, x1 עד xm, ונותנות לנו רק הדגימות שלהם, s1 עד sm. אז אנחנו רוצים לשערך את התוחלת המקסימלית, למצוא את התוחלת של המשתנה עם התוחלת הגבוהה ביותר, וכנראה שהדבר הכי נאיבי או מיידי לעשות, זה לעשות מה שקוראים לו single estimator. single estimator פשוט לוקחים כל סט של דגימות, וממצאים על פניהם, מחשבים ממוצע אמפירי, וכתוצאת שערוך מסבירים את הממוצע האמפירי הגדול ביותר. אז הוכיחו שב-2006 המשערך הזה הוא עושה overestimation למיו סטאר, לתוחלת האמיתית אותה אנחנו מנסים למצוא. אז בדאבל Q-Learning, במאמר, הם הציעו את המשערך שנקרא דאבל אסטימטור. שדאבל אסטימטור למעשה הוא חלק את השערוך לשני שלבים. כל הדאטה של כל משתנה אקראי מחולק לשניים, והשיערוך הדו-שלבי הוא כזה. בשלב הראשון אנחנו משייכים רק את האינדקס של המשתנה האקראי עם התוחלת הגבוהה ביותר, על סמך הסט הכחול, על סמך חצי מהדאטה. ברגע שיש לנו אינדקס כזה, אנחנו ניגשים לסט הרלוונטי, ועל סמך שאר הדגימות האדומות, אנחנו משייכים את המשערך עצמו. למשל, אם זה ה-2, אז 2 זה הארגמקס של הממוצעים על פני הסטים הכחולים, והערך שנחזיר זה פשוט הממוצע של הסט האדום הזה, של 2. אז בעבודה שם הוכיחו שדאבל אסטימטור הוא יוצר underestimation למיו סטאר, הוא מוטה שלילית. אז מה שהם עשו זה, הם לקחו בעצם את הדאטה וחילקו אותו ל2, ובעצם הקריבו חלק מהדוגמאות בשביל לשערך אינדקס, וחלק מהדוגמאות לשערך ערך. הסיפור הזה מכניס רעש, ובעצם נכנס לכל העניין של bias variance trade-off, ומתוך הניתוח של זה אנחנו הגענו למשערך חדש, שאנחנו קוראים לו ה-ensemble estimator, שזה צעד אחד קדימה של double estimator, שבמקום לשערך את הדאטה סט לשני סטים, אנחנו משערכים אותו ל-K סטים, ועושים את אותו שערוך דו-שלבי. אז השלב הראשון אנחנו לוקחים את הסטים הכחולים, מוצאים את האינדקס, ובשלב השני אנחנו משערכים את הערך עצמו על הממוצע של שאר הסטים במשתנה של האינדקס הכחול. אז כל הסיפור הזה באמת הגיע מתוך אנליזה של MSE, mean squared error, וראינו שבמקומות שבהם, כש-K שווה ל-2, אז הדאבל אסטימטור, אנחנו מקבלים אותו חזרה מה-ensemble אסטימטור, זה אותו דבר, כש-K שווה 2. אז כל הסיפור הזה באמת הגיע מאנליזה של MSE, וגילינו שכאשר יש SNR נמוך, כלומר, המשתנים הקיימים הם קשים להפרדה, ושיש הרבה רעש, אז מבחינת MSE הכי כדאי להשתמש באנסמבלים גדולים. וכידוע, RL זה סביבה מאוד רועשת, עם הרבה invariance גבוה, ולכן זה נותן מוטיבציה להשתמש באנסמבל אסטימטור בפריימורק של RL. וזה מה שהוליד את EBQL, Ensemble Bootstrap Q-Learning, שהוא מאוד מאוד דומה ל-Double Q-Learning, רק שמשתמשים ב-K משערכים, שכל צעד עדכון, אנחנו דוגמים את אחד מהמשערכים האלה, את הפעולה ב-Next State אנחנו בוחרים על ידי המשערך שאותו דגמנו, ואת הערך אנחנו בוחרים על ידי מיצוע של השערוכים של שאר חברי האנסמבל, חוץ מאותו משערך שאותו דגמנו, בפעולה שהוא אמר. אז פה רואים את הממוצע על שאר חברי האנסמבל, וזה הגרסה RLית של Ensemble Estimator, אז ראינו שיש את הסינגל אסטימטור שהוא מאוד מאוד דומה מבחינת הבלמן איקווייז'ן ל-Q-Learning, הדאבל אסטימטור הוא למעשה דאבל Q-Learning, והאנסמבל אסטימטור הוא Ensemble Bootstrap Q-Learning. ואני רואה, עכשיו רואים שמבחינת הבייס על המטה צ'יין MDP...
בוא ננסה לסיים, אורן.
סליחה?
בוא נסיים, אתה קצת עברת את 10 דקות פשוט.
אוקיי, אני מיד אסיים. אז Q-Learning הוא מוטה חיובית, דאבל Q-Learning מוטה שלילית, ואנסמבל EBQL הוא גם מוטה שלילית, כי הוא יוצא מדאבל Q-Learning, אבל ככל ש-K גדל, אנחנו מקבלים משערך פחות ופחות מוטה, שזה אחת התוצאות העיקריות של העבודה. נדלג קדימה רק לסוף, אז מבחינת דיפ, ראינו שאנחנו בכחול, אנחנו משמעותית עוקפים באתרי את דאבל DQN ואת DQN, ומה שהפתיע זה שריינבו זה אלגוריתם שלוקח עוד הרבה מנגנונים של חידושים של השנים האחרונות, אנחנו תחרותים איתו בהתחלה בלי לנצל את כל החידושים האלה, שזה היה הפתעה טובה, כלומר EBQL מתכנס משמעותית מהר יותר ממה שהיה לפני. תודה רבה. אם יש זמן לשאלות, חרגתי.
תודה לך. אסף, אתה רוצה שאלה?
כן, ראיתי שאתה בעצם משתמש בסלייס אחד בשביל לשערך את האינדקס, לא היה הגיוני לקחת את כל הסלייסים ולעשות נניח majority ולפי זה לקחת את האינדקס?
כן, אז הבחירה הזאת המוטיבציה היא באמת נבעה מדאבל אסטימטור, שאתה שומר על אי תלות סטטיסטית בין הסטים שאתה בוחר איתם את האינדקס, לבין הסטים שאתה משערך איתם את הערך. אז הבחירה של האינדקס אתה יכול לעשות עם איזה סאבסט שאתה רוצה, הם עשו את זה על סמך חצי מהדוגמאות, אנחנו עשינו את זה על סמך 1 חלקי K, N חלקי K מהדוגמאות, או 1 חלקי K מהדוגמאות.
אבל יש פה איזשהו טרייד, כלומר יכולתם לחלק באותה מידה,
כן, הטרייד אוף הזה הוא מאוד, אין מה להיכנס את זה, אנחנו מדברים על זה בעבודה, אבל הוא מאוד מאוד תלוי ב-SNR של המערכת. או כמה בווריאנס של המשתנים האקראיים, וביחס בין הווריאנס הזה לדלטה, למרחק של אחד מהשני.
אוקיי, ויכול להיות שיש שיטה שנהנית מכל העולמות ויותר חסכונית, או שזה לא...
אם אתה יודע לשערך את הווריאנס ואת הדלטה האלה, או כמה, בוא נגיד, נקרא לזה SNR, אתה יכול לשערך את ה-SNR הזה, אז כן, אתה תרצה לעשות משהו אדפטיבי, ולקחת לא n חלקי k, אלא x כפול n חלקי k לאינדקס, ואת השאר לקחת לערך, אבל כן, זה רעיון טוב.
תודה.
אוקיי, תודה אורן. עכשיו הדובר הבא שלנו יהיה שבי. רואה אותך? אוקיי.
היי, שומעים אותי? שנייה, אני משתף. רואים?
כן.
Okay. Okay, so I'm going to speak in English. Hi, my name is Shadi. I'm a master's student of Aviv Tamar in the Technion. I also work at Intel Labs, and today I'm going to present our work that we published in the ICRA this year. In this work, we focus on the data collection part of the offline robot learning pipeline. First, I'm going to... Wait a moment. There's something wrong with the presentation, just a moment. Okay, I'll do it like that. First, I'm going to present some motivation for why we approach this problem like this, and some common practices that are used today. And then I'm going to present the algorithm and some experimental results. So in general, a lot of the previous presenters touched on some of these subjects, so I'll try to go over them briefly. But I suppose you are, by this time, convinced why offline robot learning is important. It allows us to do many things. For example, collecting in a safe and controlled manner can be parallelized across robots or environments, and we can learn multiple skills or tasks using the same dataset that we collected once. Now, the data collection process in the robot learning pipeline is one of the more important parts that is usually either ignored, or in most recent studies, the typical trend was to either define environments or tasks that are intrinsically easy to construct handcrafted or manually designed policies, data collection policies, to collect the data for the robot learning, the offline learning afterwards, or either designing the task in a way that random actions can lead to a diversified data set. But we know that this is not always true, and even if you complicate any environment a little bit, it becomes difficult to define these policies that actually achieve a diverse and high-quality data set. Okay, so our goal is to hit these three main marks. One, we want a data set that has a large set of diverse behaviors in the environment that we're acting in. And secondly, we want data that is evenly distributed, meaning that we don't want to overexplore specific parts of this state space. We want to explore as much of it as possible, so we can provide data that is that provides as many different examples for the learning algorithm afterwards to learn from. And also, we want it to be efficient in a sense that we don't want to spend too much time on the not interesting parts of the state space, such as parts that are easy to reach or that are generally not interesting for solving skills or learning tasks. Just a second. Okay, so today there are many paradigms for exploration in specifically in online reinforcement learning. You would have heard about most of these, such as entropy regularized reinforcement learning in soft aprocritic, where I spoke about handcrafted and domain-specific exploration strategies. And there is count-based exploration, which works when you have either a small state space or a state space that can be compactly represented, either in a domain-specific way or some way that you have domain knowledge about how the state looks. And intrinsic motivation, in some sense, is the generalization of the count-based methods, where you take a high-dimensional state space and you try to define some function that can give you the visitation count, in some sense, about these states. And there are other algorithms, such as Go Explore, for example, that can fall somewhere between the count-based and explicit explore or exploit paradigms, where they have some domain-specific state representation, and then they use the fact that they're working with a deterministic simulator in order to do more efficient exploration. I'll expand on this a little bit further because in the next slides, because they are integral to the work itself. But first, I want to talk about one of the methods in the intrinsic motivation world that we rely heavily on in the work, which is called random network distillation. And the idea here is that when we have a high-dimensional state space, we want a way to define when a state hasn't been visited much, or in some sense that this state is novel in terms of the acting agent. So what they did is they started with a target network, which has some random initialization. And this network doesn't change throughout the training. What this essentially means is it's a mapping from the state space to some random embedding. And you have a target network that tries to predict that random embedding that's coming from the target network. And what you have, in effect, is when you see states, your prediction of the random embedding becomes better. And for states that you haven't seen much, your prediction is worse. And the reward that you define for the agent as an intrinsic motivation is the mean squared error of the predictor network output and the target network output. And this gives you, in some sense, a novelty score about each state, how novel this state is. Now, the problem with these methods is that when you give that reward to the reinforcement learning agent, the reward is non-stationary, and it means that the agent has to learn a new MDP each time that reward changes. And what this means is that the agent has a moving target. Each time a state that was, for example, at the beginning of training with low novelty, with high novelty, I'm sorry, in the later stage of the training, it will have low novelty, and the agent will need to learn that MDP from the start, from the beginning, essentially, in order to reach the new novel states in the MDP. So to put it more succinctly, what we want from our algorithm is to decouple the training of the agent, the data collection policy, from the constantly changing novelty score. We don't want our reinforcement learning to have to learn that novelty score that changes all the time. And we want to avoid the constraint of having a recitable environment, which means we don't want to rely on the fact that we can, by magic, reach states that are novel. We want to have an explicit policy that tells us how we reach states that haven't been visited before. And the third point is that we want something that's not domain specific. We don't want a representation of our novelty score or our ability to reach these novel states to be something that is specific to some domain, something that can work with the general high dimensional, for example, image inputs. So what we do is we take the novelty score from the R&D. We use it as is, as a way to determine when states are novel or not. But instead of learning this reward as an intrinsic reward, we learn a goal condition policy using self-supervised goal relabeling, very similar to Hindsight experience replay. So all we need for this is an off-policy algorithm. And then, similar to hindsight experience replay, for each state that we want to learn from, we also sample a goal from its future in the episode. And if we reach that goal, we give a reward of 0, and if we didn't, we give a reward of -1, which means that we learn a goal condition policy that tries to reach its goal in the least amount of steps possible. And the last part that's left is that once we have this goal condition policy and the novelty score, when we act in the environment, we simply give the goal as an input to the network, to the policy, to be the state and the replay buffer that we have so far that has the highest amount of novelty. So in general, it looks like this. We have a replay buffer, we have a goal condition policy that is learning from the environment, and the R&D is trained in a similar fashion to what I described before. And this R&D gives us a way to choose a goal for the agent to reach. And in some sense, this defines some kind of a curriculum for the agent, because at the beginning of training, you will be giving them goals that are relatively easy to reach from what you've discovered so far. And eventually, you will start discovering more and more from the state space. As you can see in this diagram here, the green represents the parts of the state space that we already know well. The blue is states that we visited, but we don't know very well. And the red states are the states that we don't know and we want to visit. So the idea essentially is to choose the blue states as goal in order to eventually reach the red states. Okay, so now for results, we want to test our data collection policy on our ability to learn downstream tasks. I see that I'm a little bit short on time, so I'm gonna skip ahead a little bit. So our setup is a robot's arm, a panda arm with 7 degrees of freedom, and we have a cube with the different colors on each side in front of it, and it can move freely in Cartesian space. And the observations are 48 by 48 images. Our baselines are a random policy, a policy that does random actions, and a policy that is an intrinsic motivation agent, as I described R&D initially, which essentially you give the novelty score as a reward. Now for some analysis, some results. Here are the data sets that were collected using the 3 methods, random agent on the top, intrinsic reward agent, and goal condition. And this shows you the distribution of the cube positions and the color of the top face of the cube in each of the data sets. So the data set that was collected by random agent, as you can see, it's not very diverse, it's not evenly distributed, and it also didn't reach many parts of the state space that are further away from the initial position of the cube. And additionally, we tested it on some supervised learning tasks, some very basic tasks that arise all the time in perception pipelines. For example, a classification problem that to predict the color of the upper face of the cube, and a regression problem of predicting the position of the cube. And as you can see, the results here, the MSE for the regression and the classification accuracy for the classification, and our method does significantly better with much lower variance in terms of the final results. And finally, we trained some offline reinforcement learning using the datasets that we collected. Yeah, this is the last slide. So we trained several tasks with varying difficulty of flipping the cube to specific face colors or pushing it to specific regions of the table. And as you can see, our method also always significantly improves on the final results of the downstream tasks in the offline reinforcement learning case as well. That's it. Thank you.
אוקיי, תודה רבה. למישהו יש לזה שאלה? אוקיי, אז אנחנו עכשיו ניקח 5 דקות הפסקה ונחזור לסשן האחרון ב3:50.
אז שלום לכולם, אנחנו נחזור לסשנים האחרונים שיש לנו. אז אני שמח להזמין את כרמל להציג את העבודה שלו. כרמל, שומעים.
תום?
שומעים עכשיו.
מעולה. אז אהלן, אני כרמל, אני סטודנט ב-MSc, בדיוק מסיים את ה-MSc בטכניון, במעבדה של אביב תמר. אני אציג את העבודה המשותפת שעשיתי ביחד עם ניקו גרופן מקורנל ועם אביב. לעבודה קוראים Self-Supervised Feature Learning for Manipulation with Contrastive Domain Randomization, תפורסם ב-ICRA 2021, והיא מתעסקת בעיקרה באיך ללמוד Image Representation, שהם יהיו שימושיים בשביל הראל ובשביל Planning. אנחנו בעצם שואלים את השאלה בעצם מה זה Good Representation, ואומרים שבעצם אנחנו רוצים שיהיה להם לפחות תכונות שאחד הם יהיו קומפקטיות, או שיהיה להם איזשהו תכונות סטטיסטיות אחרות, שהן יהיו אינפורמטיביות על האובזרבציה עצמה, ושנוכל להשתמש בהם בשביל לעשות פלנינג, או כדי להשתמש בהם לכל אלגוריתמי RL. והדבר השני שאנחנו שואלים בעצם איך אנחנו יכולים לנצל את העובדה שיש לנו גישה לסימולטורים פיזיקליים טובים, כמו מוג'וקו, פייבולט ועוד, בשביל בעצם להכליל בצורה יותר טובה ויותר מושכלת לעולם האמיתי. אז יש כל מיני דרכים ללמוד אותם רפרזנטציות, בגישה שהיא Supervised, אנחנו בעצם דורשים שיהיה לנו הרבה label data, לכולם ברור במה זה כרוך, זה לא דבר שהוא טריוויאלי. גישה נוספת היא בעצם פשוט ללמוד, להפעיל כל אלגוריתם RL בצורה end-to-end מאובזרבציה בממד גבוה, למשל תמונות, ובעצם החלק הראשון של הרשת הוא יהיה האנקודר שלנו, ייצג לנו את התמונות, וגישות שיש רואים יותר ויותר בשנים האחרונות, זה בצורה שהיא Self-Supervised, בעצם ללמוד איזשהו מודל של העולם, איזשהו State Representation, ועל זה להפעיל RL, או ללמוד את הדבר הזה במשותף, אבל בצורה שהיא Self-Supervised. אני אנסה להסביר חלק מהשיטות האלה, למשל אוטו-אנקודרים ו-Variational אוטו-אנקודרים, בעצם הם מקודדים את עמודי האנקודר, אחרי זה משתמשים בדיקודר כדי לשחזר, לומדים שגיאת שחזור, ואחרי זה אפשר ללמוד עוד איזשהו forward model, בעצם ללמוד מודל של העולם, כדי שאחר כך נוכל להשתמש באותן רפרזנטציות Z, כדי לתכנן איתם. שיטות נוספות בעצם עושות את הדבר הזה במשותף, אלא מקבלות אובזרבציה בזמן T, עוברות את כל התהליך עם ה-forward model, חוזרות את O של T+1, משתמשים בשגיאת השחזור, ובעצם ככה לומדים בצורה משותפת גם את המודל וגם את ה-state representation. אז זה דבר אחד. במקביל לזה בעצם עלה תחום חדש, ב-2010 הוצא דבר שנקרא Noise Contrastive Estimation. הרעיון הכללי הוא בעצם שאם יש לנו איזשהו קונטקסט, אז אנחנו יכולים ללמוד בעצם את מה שאנחנו רוצים לחזות קדימה, את P של X בהינתן C, החיזוי שלנו, ה-forward model למשל, על ידי זה שנציע לו המון דוגמאות קונטרסטיות, שליליות, נציע N כאלה, ובעצם נלמד להפריד, לעשות דיסקרימינציה בין הדוגמה הנכונה, למשל הטיים סטפ הבא, לבין כל מיני דוגמאות מטיים סטפים שונים. ב-2018 ונדר אורד הציע ממש נקרא CPC, הציע את ה-Inference Ilos, שבעצם זה softmax או log likelihood בין הדוגמה הנכונה, X של T פלוס K, כלומר לחזות K צעדים לעתיד למשל, מתוך אותו קונטקסט, לבין כל מיני דוגמאות שליליות שנמצאות. והציע את הארכיטקטורה כזאת שאומרת נלקח חלקים מהמידע, את X שלנו, אובזרבציה, פה למשל זה אודיו, נחזה איזשהו קונטקסט, נחזה את העתיד, ואז בלוס שלנו נכניס את למשל עבור K שווה 1 את XT פלוס 1, זו הדוגמה החיובית, ועוד כל מיני דוגמאות שליליות, וככה בעצם נלמד איזושהי רפרזנטציה Z, שאיתה נוכל לעשות אחר כך כל מיני דברים יפים וטובים. הרעיון הזה בעצם, אם מכניסים אותו, אז אנחנו יכולים להפוך את ה-Reconstruction Based Models, בעצם להעיף את הדיקודר, מה שמאפשר לנו אחד, אנחנו לא צריכים ללמוד את המודל הגנרטיבי של לשחזר את התמונה, ועכשיו לא צריך ללמוד כל מיני דברים שאולי לא רלוונטיים לרפרזנטציה, למשל טקסטורות וכו'. אז את הרעיון הזה השתמשו בעבודה אחרת מברקלי, שפורסמה בקורל 2020, שהם בעצם ביצעו אותו דבר, לקחו וידאו של מניפולציה של אובייקטים, של חבל ושל בד, ובעצם ככה בשיטה הזאת מתוך חיזוי הצעד הבא, forward model, למדו לייצג את התמונות בצורה שהיא אפקטיבית לפלנינג, הם השתמשו באותו influence loss, כמו שרואים פה, ועמידת H, שזה עמידת סימילריטי, שנכנס ללוס, זה בעצם פשוט ה-L2 distance בין הרפרזנטציה האמיתית, הייצוג של הבא, למעט מה שחזינו עם ה-forward model, שלמטה זה במונה, ובמכנה יש את המון דוגמאות שליליות, שנלקחו או אפיסודס אחרים, או מטיים סטפים שונים. זה למשל דוגמאות לתוצאות שהם קיבלו עבור sim to real, ומה שמעניין פה זה בעצם ה-sim to real gap. כאן נכנס בעצם המוטיבציה לעבודה הנוכחית שלי, שכרגע אני אציג אותה, שבעצם אנחנו רוצים לנצל את העובדה שיש לנו גישה לסימולטור פיזיקלי, כדי לצמצם אותו sim to real gap. בעבודות הקודמות, תמיד ה-sim to real gap, כמו שאתם רואים בצד שמאל, הוא היה מאוד מאוד קטן ומינימלי, כלומר למעלה זה התמונות המסומלצות, למטה התמונות האמיתיות. בפועל הרבה פעמים אנחנו רוצים לעבוד את דברים יותר מסובכים, למשל, פה רואים סביבה של שני אובייקטים חסומים בפריים, בפועל זה יכול לראות מאוד 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 שונה, גם מבחינת תאורה, גם מבחינת טקסטורות, גם מבחינת דיוק, אפילו או קליברציה של המצלמה, או בצד ימין שבנוסף לקובייה יש פה עוד המון אובייקטים אחרים שמפריעים, שבאופן תיאורטי אם המשימה היא לדחוף קובייה, היינו רוצים ללמוד להתעלם מהם. אני אדלג. אחת הדרכים בעצם שמשתמשים בהם בדרך כלל, במקרים כאלה זה domain randomization. אנחנו מניחים שהסביבה שלנו מורכבת מפרמטרים X, למשל במקרה של הקובייה, מיקום הקובייה, האוריינטציה שלה, חיכוך וכולי, ו-E, כל מיני דברים חיצוניים שהיינו רוצים ללמוד להתעלם מהם, טקסטורה, תאורה וכן הלאה. והאובזרבציה שלנו בעצם מורכבת מהשילוב ביניהם, כלומר, בהינתן E ו-X, אנחנו יודעים לייצר אובזרבציה שמתאימה להם, ואנחנו רוצים ללמוד איזשהו קידוד Z של המידע הזה. אבל היינו רוצים שהרפרזנטציה שנלמד, הם יהיו בהינתן X, לא משנה מה הסביבה שלנו, כלומר לא משנה מה התאורה או טקסטורה, אני אקבל את אותה רפרזנטציה. זו הייתה רפרזנטציה שהיא תהיה מאוד טובה מבחינתנו, כי היא תלמד להתעלם ממה שלא צריך. וכמובן שנרצה שהלייבל שלנו יהיה, אפשר לחסות אותו מתוך אותה רפרזנטציה. פה יש מודל קוזלי שמדמה את מה שאנחנו אומרים, כלומר בהינתן E ו-X אנחנו מקבלים איזושהי אובזרבציה, יש גם איזשהו תיוג, במקרה שלנו התיוג יהיה הטיימסטפ הבא, ויש לנו חיזוי Z, ואנחנו בעצם הלוס שלנו בין Z ל-Y, במקרה שלנו Z יהיה Z של T ו-Y יהיה Z של T פלוס 1, ונלמד את זה בצורה קונטרסטית על ידי זה שנציע עוד כל מיני Z'ים מזמנים שגויים. אני קצת אדלג. ספציפית שמשלבים את CPC, את אותו רעיון של Contrastive Loss עם Domain Randomization, אז בגלל שהדומיין, הלייבל שלנו, E, נדגם ביחד עם האובזרבציה, אז אנחנו מכירים שהשכנים הכי קרובים לדוגמאות רפרנס בצד שמאל, הם בעצם מאוד דומים בטקסטורה, כלומר הטקסטורה היא מאפיין דיסקרימינטיבי מאוד טוב, אז במקום ללמוד פיצ'רים שאנחנו בעצם יודעים להתעלם מהטקסטורה, למדנו פיצ'רים שנתפסים דווקא לטקסטורה. וזה איזושהי פינומינה הבעיה שזיהינו, שאנחנו מנסים לפתור. המאמר הזה בעצם מציע איך לשנות את זה, בגלל שאנחנו נגישים לסימולטור, אנחנו יכולים להתערב, לעשות אינטרוונשן בסימולטור, ובעצם לקחת את E ולשנות את זה באופן מלאכותי. למשל, לשנות את הטקסטורה רק עבור הלייבל, כלומר Z בטיימסטפ T יהיה מטקסטורה 1, והפרדיקציה שלו בפורוורד מודל, הטיימסטפ הבא, הלייבל Y, אנחנו נעשה לו אינטרוונשן ונשתמש בטקסטורה שונה, בתאורה שונה, או בכל פרמטר אחר שממנו אנחנו רוצים ללמוד להתעלם. זה שינוי מאוד קטן בלוס בעצם, בסך הכל זה להוסיף פה את E-Tag במקום E, ובעצם אנחנו כרגע חוזים לצורך העניין מצד שמאל מהתמונה, חוזים תמונות בדומיינים אחרים. הדבר הזה דומה ל-SimCLR במובן שבו אני בעצם לוקח איזושהי סביבה, עושה לה שתי טרנספורמציות, רק שפה הטרנספורמציות הן לא בממד התמונה, הן מתבססות על הסימולטור עצמו, ולכן אנחנו מסוגלים לעשות טרנספורמציות שהן בעצם מתעלמות ממה שלא מעניין אותנו, ושומרות רק את מה שכן מעניין אותנו. לאור קוצר הזמן אני אדלג קצת על ההוכחות. הדגמנו על זה על כמה סביבות, סביבות דינמיות שבהם יש אובייקטים שהם מתנגשים אחד בשני, וסביבות שהם controlled, יש איזשהו אובייקט שדוחף, וגם סביבות של בעצם זרוע רובוטית שדוחפת חבל, ובהמשך גם קובייה. איך עושים לזה אבלואציה? אז בעצם אין דרך מאוד טובה, כי אין לנו ground truth, אז אנחנו עושים אבלואציה בשלושה דרכים. אחד, אנחנו בעצם מגרילים את אותו X רק מדומיינים שונים, ורואים כמה זה קרוב. אפשר לראות שגם במידה MSC וגם בקוסיין דיסטנס, אנחנו משמעותיים יותר טובים מהבייסליין שלנו, שהבייסליין זה אותו מאמר של ברקלי, שבעצם עשה את זה בלי אותו טריק של לעשות את האינטרוונשן, וגם אנחנו משחזרים nearest neighbor למעלה, ובעצם מחפשים תמונות שהן מאוד דומות, ובודקים האם האוקלידיאן דיסטנס בין האובייקטים שבסימולציה אנחנו יכולים לדעת אותו, הוא קרוב, גם פה אנחנו משפרים בצורה משמעותית. בזמן ה-COVID-19, כמובן שהיינו צריכים לעשות על אבלואציה סימטוריל בבית, לכן נעזרנו בחפצים שהיה קל למצוא, ופה יש דוגמאות להשוואות איכותיות, למעלה זה התמונות רפרנס, באמצע זה התמונות שאנחנו משחזרים עם מאגר אקסטרנל של ה-nearest neighbor שאנחנו משחזרים, ולמטה זה הבייסליין, בעצם אותו עבודה מברקלי, אפשר לראות שזה הרבה יותר דומה גם בצורה איכותית, אנחנו ביצענו את אותו דבר על כל הסביבות, גם על סביבות קצת יותר קשות, כמו חבל שהוא דיפרמבל, והאבלואציה האחרונה שביצענו היא בעצם לבצע עם זה פלנינג. אז אנחנו משתמשים ב-one step MPC, בכל רגע אנחנו בעצם דוגמים הרבה אקשנים, מריצים אותם בפורוורד מודל, בודקים מה הכי קרוב ב-L2 distance ב-latent space, ובוחרים את האקשן שהוא הכי טוב ולוקחים אותו. הסיבה שבחרנו באלגוריתם פלנינג כל כך פשוט, הוא כדי לנקות רעשים ורק להראות אבלואציה טובה על הרפרזנטציה, כמובן שאפשר לשמש ברפרזנטציה הזאת בכל RL אלגוריתם אחר, או בכל שיטה אחרת של פלנינג. נדגים איך זה עובד, בעצם יש לנו זרוע רובוטית שדוחפת את הדברים, בכל רגע היא בעצם מקבלת את התמונה, בכל רגע היא מקבלת, יש לה איזשהו גול, והיא מנסה לדחוף, בכל רגע היא מקבלת את התמונה הבאה, והיא מנסה לדחוף את הקובייה למקום, אז בצד ימין רואים את הגול, הגול יכול להיות או בסימולציה או תמונה אמיתית, בצד שמאל זה התמונה שהוא מתחילה, ואפשר לראות שהוא מצליח להתעלם בצורה די טובה, בצורה מאוד טובה, גם כשההפרש בין הסימולציה לריאליטי הוא מאוד 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 גדול, גם שיש אובייקטים שהוא לא ראה בכלל, ובעצם לגשר על הפער הזה בצורה מאוד טובה. פה אנחנו עושים גם השוואה כמותית עבור פלנינג, ומודדים את המרחק הסופי שהוא מגיע אליו, בהשוואה לבייסליין, שהבייסליין זה כמובן אותה עבודה של ברקלי, ומראים את זה גם על דוגמאות שהן מאוד מאוד קשות, למשל מוסיפים פשוט לוח שחמט עם המון המון חלקים, שזו טקסטורה מאוד מאוד שונה כמובן ממה שהוא יתאמן עליה. לסיכום, אני אגיד שהדבר הזה הוא בעצם מאפשר לסגור את ה-sim to real gap, גם שהוא מאוד 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 גדול, והוא מאוד כללי, כלומר אפשר לקחת את השינוי, את המודיפיקציה הזאת של לעשות האינטרוונשן בסימולטור לכל אלגוריתם שהוא RL, בין אם זה אונליין או אופליין, כמובן שמבוסס על קונטרסטיב אובג'קטיב. תודה רבה.
תודה כרמל. אז עכשיו יש שאלות למישהו? נראה שיש שאלה. רועי? רועי?
כן, שומעים אותי?
כן.
אז קודם כל, כרמל, תודה רבה על ההרצאה. יש לי שאלה לגבי למיטב הבנתי, ההורדה של הדיקודר מכל הסיפור של ה-representation learning יכולה ליצור מצב שהלוס שלך מבוסס על פרדיקציה של הצעד הבא, אז ברגע שאתה מחשב את ההפרש בין הרפרזנטציות שלך, אתה יכול להגיע למצב של איזושהי נקודה סינגולרית כזאת, שכל הרפרזנטציות נראות אותו דבר, כי כל מה שניסית זה למזער את הלוס. אני מבין שמה שנותן לזה בעצם קונטרה, מה שגורם לזה שזה לא יקרה, זה הדוגמאות הקונטרסטיות, אבל אז יש תלות מאוד חזקה במטריקה שאתה משתמש כדי לחשב את המרחק ביניהם. אתה השתמשת ב-L2, אבל אפשר לחשוב על הרבה דוגמאות מהעולם האמיתי שאוקלידיאן דיסטנס הוא לא בכך מטריקה מספיק דיסקרימינטיבית בין מצבים שונים. אתם יצא לכם להתעסק עם מטריקות אחרות או עם איזושהי שיטה לנסות להכליל את זה מעבר למטריקה של אוקלידיאן דיסטנס?
אז יש כל מיני שיטות, יצא לנו להתעסק ספציפית גם עם קוסיין דיסטנס, יש גם אפשרות של לעשות בעצם ביליניאר, כלומר מכפלה פנימית משוקללת, שזה מה שהציעו ב-CPC המקורי, יש גם לדעתי לא מעט מאמרים שמתעסקים בדיוק בסוגיה הזאת, ספציפית בעבודה הזאת כאמור, זה לא הסוגיה המרכזית, זה יעבוד, בדקנו את זה, זה יעבוד די טוב גם אם נשתמש, חלק מהניסויים גם משתמשים בקוסיין דיסטנס, זה יעבוד טוב, אמור לעבוד טוב בכל מטריקה, הרעיון המרכזי כמובן הוא ההתערבות בסימולטור, בשביל לוודא שאנחנו שולטים בתוכן של הרפרזנטציה, כלומר ממה אנחנו לומדים להתעלם, למשל טקסטורה, תאורה וכולי, ועל מה אנחנו בעצם שמים את הפוקוס, אבל כמו שאמרתי זה אמור לעבוד עם כל מטריקה, לאו דווקא L2.
תודה.
בבקשה. אוקיי, תודה כרמל. אם תוכל רק לעצור את השאר. אוקיי, אז המציג הבא שלנו זה דן.
היי, שלום לכולם. Okay. So I'll give my presentation in English. I think it's actually a perfect timing because the last question was really what this work is all about. So this is a joint work with me and Jia Song from NYU. Impact-driven exploration with contrastive and supervised representation, and I'm working currently at Bell Labs in New Jersey. I'm going to touch on some of the basic challenges that I think were maybe discussed a few times, but just to give the right framework to everything. If the reward is sparse, then random exploration can be insufficient. Essentially, without positive feedback, a random agent may never see the reward within any episode, and just these two illustrations show the difference between just a random agent and an intrinsically motivated agent. Some of the challenges that we also cope with is that these policies that we often train for can overfit to a specific environment. Agent may really even fail to generalize to very similar environments. So to tackle these issues, we looked at the mini-grid environment, right? So we chose to look at partial observation, right? So in this little videos, what the agent really sees highlighted. It's about 9x9, 3x3 rectangles. Dynamics is deterministic. Environments are procedurally generated, so they're generated by an algorithm. They're not fixed. And there are diverse tasks available, like a key corridor where you have to pick up a key and open a door, or just a multi-room, all kinds of complex configurations of rooms, navigated to a target. And this is really allows us to focus on exploration and not on other, nuisance or environmental issues that can happen in real life. So to encourage exploration, there's some very basic approaches like entropy bonus, which is encouraging policy output to have high entropy, and that's standard in every package now. And also the issue of intrinsic reward, where intrinsic is really called like this because it doesn't depend on the external reward. So we can look at the basic scheme like rewarding visiting novel states by maintaining a count of the visited states, or rewarding visiting states that have high uncertainty. For example, looking at the prediction error of a forward dynamics model, like in PATHEC, the work from Berkeley. And we focus here mostly on the state of the art from Facebook called RIDE, which also builds on the previous work of PATHEC. And it essentially designed an intrinsic reward that is based on state novelty, which is measured with an L2 distance in state embedding space, right? So we have on the right a forward inverse dynamic state embedding training, right? So we sort of have two networks here to learn on one hand predict the action, on the other hand predict the next state, and that's how we sort of train them and obtain a certain representation, embedding representation phi, and to create the intrinsic reward, we're looking at phi and at phi t plus 1, and we look at essentially the L2 distance between them. However, as was addressed, we can ask what does this L2 distance in state embedding really measure? I mean, the way we trained phi was not done with this metric, right? So why should this really work, and why should we use that? And the question is, can we really train a state embedding function with a natural measure of similarity? So to answer this, we used SimClear, is a recent breakthrough in self-supervised learning. It's called contrastive learning. The SimClear is essentially the algorithm. So the idea is essentially, given an anchor sample, we label sample in the batch as positive, negative by doing a sort of a perturbation to a pivot. And the training objective is to make positive pairs similar and negative pairs dissimilar. And they're using a cosine similarity as the similarity measure. Positive pairs are really given by generating these two randomly transformed data. And we just count the remaining pairs are all negative pairs. And this has shown really a surprising, very good performance on various tasks and benchmark data set. So the idea again is to sort of take ST, state T, generating positive pairs, by choosing AB within up to K step, and K is a hyperparameter here. And the remaining pairs are all negative pairs. We're using the cosine similarity, and then we define the intrinsic reward to be a 1 minus this type of cosine similarity from SimClear divided by 2. So schematically, once we have this contrastive loss, we can embed it sort of in the model that creates this intrinsic reward. And then we take it another step. So instead of just looking at the pivot, now we look at the episodic memory, and the episodic memory is the set of state that was visited during this particular episode, and we can potentially use this kind of SimClear framework also with this episodic memory. And the idea here is that everything that is not reachable in K steps is considered a negative pair, and everything that is within this K is considered positive. So we're looking at a set of 4 different methods for rewarding. As you can see, phi can be trained by forward inverse or can be trained by SimClear. And then we have 2 aggregation methods to rewarding. One is by essentially looking at the last state and dividing by the total number of visits done during that episode, or looking at the minimum function over all the episodic states. And what we can see is that essentially this approach that is based on SimClear is typically leading. So the top row is a key corridor, is actually showing that as the complexity of the problem goes up, so in key corridor S4, S5, actually only EC SimClear is converging. And if we go to a multi-room environment, also we can see that EC SimClear and the SimClear approach is really helping out in terms of the rate of convergence. The other thing that we did is sort of look at the prediction power of using this kind of embedding that is based on the cosine similarity, and this is the ROC curve, right? So we can see the ride-based in red, and the blue is our Sinclair-based approach, and we see that the significantly different performance here for in prediction of pairs using Sinclair. The other thing we did is we tried to understand qualitatively what does this cosine help us with, and what is the emphasis here. So you can see that we have 3 columns here. One is the reward on opening doors. The other one is reward on moving forward and reward on making turns. And we can see that ride has a big emphasis on just opening the door, right? On the other hand, Sinclair has the reward on sort of moving into a new room, like opening up, right? So seeing something that you haven't seen before. So it's kind of pulls him out of this egocentric situation. We see that also moving forward, moving forward through those doors really shows that. Also taking certain turns that are critical to move you towards the a new vision of where is now the door, for example. Then it kind of helps you more emphasize in Sinclair. So I don't know if I'm too early, but essentially the purpose, so we propose a conceptually clearing measure of impact by training observation presentation with the cosine similarity objective instead of doing the forward inverse model. We managed to connect ride with episodic memory, and we've seen that essentially we can outperform ride with the EC extensions. We essentially defined a novel intrinsic reward that is based on state novelty to encourage this type of efficient exploration. All right.
Okay, thank you, Dan. I see we already have a question from the audience. So Roy, again.
No, I didn't press any button.
Oh, sorry. I see that. Okay, so do we have any other questions for Dan? Okay, so thank you, Dan.
Sure.
So our next speaker is Alap. Hi, you're still muted. שלום לכולם. אז אנחנו חוזרים לחלק האחרון. אני מאוד שמח להזמין את תום, שיעשה לנו טוטוריאל על Meta Gradient Reinforcement Learning. תום, אתה מוזמן להתחיל. אתה על מיוט.
שומעים אותי?
כן.
וגם רואים את המסך?
כן.
מעולה. So, hi everyone, my name is Tom, I'm a research scientist at DeepMind, and I'm going to present some of our recent work on meta-gradient reinforcement learning. I'll focus on works that I participated in, but I'm also going to show works that was done by others in the group, including Vivek, Zhongwen, Matteo, Junio, Kado, Dave, and Satinder. So before I begin, I want to start with my motivation or why I started to do research in machine learning. And it was 2012, and there was a TCE conference at the Technion, and I remember Andrew Ng gave a talk, and he showed us how convolutional neural networks discover structure automatically without being programmed explicitly to do so. So in the image here, you can see features that are discovered in the lower layers of convolutional neural network, and it's a very famous image. When I started my PhD, I tried to do something similar to DQNs. So I tried to look at the structures that DQNs discover and see if it makes, if it includes some patterns about how to solve a game. So in this figure, you can see a TSNE image of a DQN playing Breakout. And you basically can see small images in this figure that are connected with arrows, and basically this image describes an abstract MDP that lives inside a DQN. And the main conclusion that came out of this work was that these deep RL agents really discover temporal structure in the form of options when they try to solve Atari games. And more recently, we can see the success of AlphaGo, and I'm using a citation here from Gary Kasparov. Deep Blue was the end, AlphaGo is the beginning. And this citation is basically referred to the fact that AlphaGo is learning patterns when it is doing search, and it basically replaces all the brute force approaches that preceded it, like Deep Blue. And when I'm saying that this is my quest, I'm basically referring to the fact that I believe that methods that are able to discover structure by themselves are the methods that are going to succeed empirically. And that is also going to be the focus of this talk. If we think about reinforcement learning from a higher level perspective, so we usually have a simple recipe. We want to optimize an objective. We want to do it end-to-end from experience by doing exploration, and we usually do it with some gradient descent algorithm or a temporal difference algorithm. And basically, the role of theory is to show that if we have an update rule, it will learn efficiently in any MDP or everywhere. But if we look at what happens in practice, then there is a big variety of update rules to choose from. So we can use TD lambda, we can use distributional reinforcement learning, we can do Q learning, we can do double Q learning, and there's a big variety of algorithms. Most of them have theoretical guarantees in the tabular setting, but when we face a new problem, we really don't know how to choose between all of those algorithms. So if we look at this, we can say that we've moved from handcrafting features to handcrafting update rules. And the focus here is will be to answer the question if we can discover some part of that, if we can kind of merge algorithms in an efficient way, or even discover them completely from scratch. The approach that we'll focus on is the meta-gradient reinforcement learning approach. And the goal is, again, to learn an update rule and to end from experience. We're going to use gradient descent, and the goal would be to learn better in a specific environment. So again, if we think about what the theory tells us, so the theory tells us that there is an algorithm that is going to perform well in any environment, but it doesn't mean that it performs the best given an environment. So the approach that we take here is basically to find an algorithm that can learn faster and faster while it's interacting with a single environment, because some environments will show us these regularities in the data itself. I'm not going to talk a lot about theoretical foundations of this approach in this talk, but if you are curious about it, so there is theoretical foundations, mainly in the online learning literature, and here I recommend works by Maria Florina Nina Balkan, and there's also some nice works in bi-level optimization by Massimiliano Pontil. Cool. So the TLDR of the meta-gradient approach is that we are going to have two optimization loops. In the inner loop, we are going to optimize the agent parameters. So that's basically the standard optimization loop that all of our agents have. Here we can optimize the policy, the value function, we can optimize the model, and the goal is to minimize some inner loss. It can be an actor critic loss or any deep reinforcement learning loss. But the observation here is that we can parameterize this loss by meta parameters. And these meta parameters can be the discount factor, the learning rate, some parameters that are related to off-policy learning. It can be the loss coefficients. Basically, any parameter such that the loss is differentiable with respect to this parameter. And then we have a second loop, which is the outer loop. And what we do in this loop is that we basically represent the gradient of the inner loop as a function of these meta parameters. So now the new parameters, after we took one gradient step, these new parameters become a function of the meta parameters, and we can take the gradient of the meta parameters with respect to a different loss, which we call the outer loss. So if you look at these heuristics at the right, we start with these parameters and meta parameters. We take the gradient, we get the new parameters, which are a function of the meta parameters, and then we take a gradient of the meta parameters to improve a different loss, which we call the outer loss. So that's the TLDR of what we are going to do. So the most reasonable question at this point would be, okay, so we want the meta parameters to optimize the outer loss. So if we really care about the outer loss, why do we need this inner loss? Why do we need this inner loop? Why do we need something else to happen in the inner loop instead of just optimizing the outer loss? And this slide is actually about suggesting that there's a lot of motivation for having these two loops. So the most classical example is regularization. So if you think about what we do in regularization, we change the loss that we optimize by adding a regularizer, and we measure the performance of the model for each regularizer on a cross-validation loss, and then we choose the best model using this outer loss. So in the case of regularization, the outer loss is basically the cross-validation loss, and each model is optimizing a different inner loss. And there's a ton of motivation for why we want to do regularization, but the most classical interpretation is that we want to balance bias and variance. So you can think about all of this meta-gradient approach basically as a way to regularize your model by doing cross-validation online. Another example that is more relevant to reinforcement learning is the concept of auxiliary tasks. So it's a way to introduce regularization, basically. And the focus here is on representation learning. So you can see an example from the Unreal agent, where basically the agent gets additional losses for predicting depths, for controlling features, for doing many auxiliary things. And by optimizing these losses, the agent enjoys better representation. And this better representation helps it to find better control policies. And the last example that is also very relevant to reinforcement learning is exploration exploitation. And here I'm basically saying that we want to optimize our behavior policy, but we act with respect to a combination of the uncertainty of our model and our current prediction. So it's basically saying that we have many reasons to do something else in the inner loss. because maybe we are uncertain about the word, we don't get enough feedback. So there's a lot of motivation for this metagradient entities. And just the main thing that you should take from these slides is that metagradients are basically a way to do online cross-validation with gradients. In this line of work of metagradients, we made a few distinctions between the approaches. The first one is between single lifetime approaches and multi-lifetime approaches. So in single lifetime approaches, we have a single agent that is acting with a single environment, and it wants to adapt its learning so it can learn quicker over time. It's harder to learn because we must get some sort of credit assignment in the metagradient update, and I'll talk more about it later. And the second approach is the multi-lifetime, which is more similar to what people are doing in meta-learning. And in this case, basically, the agent is making interactions with environments. After each interaction completes, the parameters are restarted. And then you can get feedback about how the agent was learning through the entire interaction with the environment and get some metagradient from that. So I'll focus mainly on single lifetime approaches in this talk. The second distinction that we make is between white box and black box approaches. So in the white box approaches, we usually have a very well-defined update rule. So it can be TD lambda, and then we are going to meta-learn the lambda parameter, or it can be the learning rate or anything else. And what's common to these approaches is that we usually understand the rule very well. We know how to initialize it from a previously pre-trained, pre-tuned update rule. And if we think about black box metagradients, so in this line of work, we basically use a neural network to model the entire loss function. So we use transformers or LSTMs that take sequences of data and basically produce a loss function for our agent in the inner loop. So I'm not going to cover a lot of black box metagradient stuff in this talk, but if you're interested, there are papers online. And if we take a perspective on what was being done in this regime, so there are lots of works on metagradients, and they usually differ in the single versus multi-lifetime, white box versus black box, and also in what is meta-learned. So today I'm going to start with some works that focus on meta-learning meta-parameters, but I'll also show you some works that learn structure, like options, and we have other works where we can learn intrinsic reward or auxiliary tasks. Cool. So the first work that I'm going to cover is the self-tuning actor critic algorithm. It's a work that I led at DeepMind with all of these great collaborators, and it was presented in the last NeurIPS. So what is this self-tuning actor critic all about? It's based on the Impala agent. So for those who don't know Impala, I'll present the loss explicitly in the next slide, but it's an actor critic, and more specifically a distributed actor critic. The main thing that is important about Impala is that it has multiple actors. So all of these actors have a copy of the policy parameters, and they act in different environments. They collect data from the same policy, but in a distributed way. They provide data to these learners. And the learners use the data from the actors basically to make updates to the parameters, and everything is synchronized. The important thing for this talk about Impala is that there might be a parameter lag between the actors and the learners. And because of this parameter lag, we will have to face some issues with off-policy learning, because the policies that collect the data are not exactly the policies that make the updates. So we'll touch more about the off-policy corrections in Impala in the next few slides. The second thing about this agent is that we implemented it in JAX. So for those who don't know, JAX is a very trending language for deep learning. It has two main advantages. One is the vectorization, so you can do operations on batches very easily. And the second thing is its autodiff capabilities, so you can basically get a gradient of any function, and you can write a function in NumPy and get all of its gradient from different orders very easily. And the reason that I'm pointing JAX out in the context of metagradients is that it's basically you can get the metagradient almost for free if you write it with JAX. So implementation-wise, it's very simple. The second point about this agent is that it's going to use a single metagradient update rule to update all the differentiable hyperparameters in the loss. So again, it's a white box approach, but it's ambitious in the sense that we scaled previous methods and we really want to optimize all of the metaparameters. The last point is that it's a single lifetime, so you can think about an agent that is playing Atari and it's learning the metaparameters in a single interaction with the same frame budgets that other agents face. And the highlights of the results is that we got very good performance boost. So the relative improvement in Atari was from 240 to 360. And that's the median score, so it's like the median over the 57 games. It's the third best agent that there is in Atari. And the interesting point is that it can tune the hyperparameters differently in a given task. So it's not like giving a schedule for changing the parameters a priori. It really adapts for a given game. We did some robustness experiments, so we can show that if you initialize the algorithm from different hyperparameter settings, it performs better than the baseline. And at this point, I think that most of the people that listen to this talk probably think that this is a very complicated agent that requires lots of compute. So it's actually very simple and it's very slim in compute. It only takes 30% additional compute, and in terms of runtime, it takes like 1 hour and a half to finish to play Atari in 200 million frames. Cool. So let's go a little bit more into the details of stack. The inner loss, again, is a standard actor critic loss. And you can see the equation here. So when I'm saying standard, it basically has this critic loss where GS is a rollout, and we approximate the value function to fit this rollout. It's weighted by this GV, which is a loss weight for the value for the critic loss. The policy gradient loss is basically an advantage actor critic. So this term here is the Bellman error, and we add entropy regularization. The outer loss is also basically the same loss. So we use the same actor critic loss in the inner and the outer loss, but we add one additional regularization term that makes the policy after the metagradient update to stay close to the policy before the update. Cool. So like in the previous slide, I showed you how to basically model all the metaparameters as a differentiable function. But in this work, we wanted to take one step further. And basically, we wanted to embrace self-tuning and extend our agents. So I'm going to show two examples. One is a self-tuned parameterized leaky V-trace operator. So it's basically a way to extend how we do off-policy learning in the agent. And I'll go into the details soon. And the second thing is that we added many auxiliary loss functions to the actor critic, but everything about these auxiliary loss functions is self-tuned. So we don't introduce any new hyperparameter to control these auxiliary loss functions, and they are basically learned online, including all of their metaparameters. And the main point here is that you can basically regularize your agent to have a specific structure and see if this structure helps you to find better update rules. So a little bit about V-trace. V-trace is a way to do off-policy learning using importance sampling. The main thing that is different in V-trace compared to standard importance sampling is that we clip the importance sampling ratios. both the Cs and the rows. I'm not going to cover all the details in depth, but the nice thing about Vitris is that you can show that it converges in the tabular setting, and that instead of converging to the true target value function, it converges to the target, to a value function of a policy, which is somewhere between the behavior policy and the target policy. So in this case, mu is the behavior policy, the policy of the actors that generate your data, and pi is the policy of the learner. And basically what we want to do in off-policy learning is to use data that is generated from u to learn about the value function of pi. But when we use Vitris, we clip the important sampling ratios, and then we learn about the value function of this policies that is between them. There are some things that we need to satisfy, like we need the truncation ratio of these rows to be larger than the truncation ratio of these Cs. And the second observation about all of this update is that these truncation ratios are not differentiable. So it's really hard to meta-learn them. Maybe the last thing that I want to say is why we need those truncation ratios is basically, for those of you that know importance sampling, it tends to suffer from very high variance. And by clipping those importance sampling ratios, we can show theoretically that there is some sweet spot in the contraction variance trade-off. So if you're interested, you can check the Impala paper for more details. The thing that we did in StackX was actually to focus on how we can differentiate the truncation levels. So we proposed a different formulation, which we call leaky Vitris. It's basically replacing the clipping by a leaky way of doing clipping. And because it's leaky, it's going to be differentiable. So instead of clipping, we allow something to leak in. And the nice thing, so this is the formulation of the leaking. We basically take the clipped version and we take a convex combination with the regular importance sampling ratios. And the nice thing is that we can now get a different bias variance trade-off for leaky Vitris because the importance sampling is unbiased and the clipped importance sampling is biased but with less variance. So what we are going to meta-learn is basically this alpha parameters that trades off the two terms. So now it's differentiable, and we have the possibility to control the off-policy trade-offs by learning it. The second thing that we did in StackX was to extend it by learning these additional auxiliary tasks. So if you think about a standard actor critic that has a policy and a value function and the loss function, so we basically just replicate the heads and we get a set of policies and a set of value function. And the important thing is that we can learn different meta parameters for each one of these losses. So we basically have a set of meta parameters times the number of auxiliary heads. So the only new hyperparameters that we introduce is the number of auxiliary tasks, and everything else is discovered by the algorithm. Yeah, so these loss functions are basically the previous Impala loss functions with leaky Vitris, and we learn the meta parameters for each one of these heads. One thing that is important to mention is that these heads are never allowed to act. So only the first head is acting in the environment. And basically all of these other heads only act as auxiliary tasks, and they have to learn off policy. Cool. So here I'm showing the learning curves of StackX and some of its ablations. In Atari, this is 200 million frames. For reference, DQN, Rainbow, A3C, all of these algorithms from 4 or 5 years ago get around here, around a median score of 100. If you look at Impala, so Impala gets to around 200 median score. And if you add these auxiliary tasks to Impala without learning them, so basically something that is very similar to Unreal, you get this dashed blue line here. And what you can see in the solid lines is what happens when you expose the algorithm to self-tuning. So you can see that in both versions, both the green one that only has a main head and the blue one that has 2 auxiliary tasks, the dashed lines are learning much better than the green lines. So by exposing the agent to self-tuning, we really improved the results. The second thing that we did was ablative analysis. So here the y-axis is the number of tuned parameters in the agent. In here, for example, you can see that we tuned the discount factor, the lambda coefficient, 3 loss coefficients, and the leaky v-trace parameter. And we do it 3 times, so number the times of auxiliary tasks. So the blue bars correspond to 2 auxiliary tasks, and the green bars correspond to no auxiliary tasks. And you basically can see this trend that as we expose the algorithm to self-tuning more hyperparameters, its performance keeps improving. And this ablation analysis really looks very nice, almost monotonic. And you can also see some baselines in red in between. Okay, so we got good results in Atari, but we were also curious to see if it transfers to other domains. So again, you can see this color coding where stack X is the blue line and stack with only one auxiliary task is the green line. Solid lines are with self-tuning and dashed lines are without self-tuning. And these 3 domains are basically all of the DM control domains. So it's about 40 Mujoko domains, and we take the average score over them. And you can basically see the same trend that we get relative gains from self-tuning in all of these domains when we learn from features, when we learn from pixels, and when we use the real-world reinforcement learning suite that Daniel probably presented to you this morning. So we really gain a lot from using self-tuning, and it generalizes to many domains. The next thing that we checked was adaptivity. So here you can see different meta parameters. So for example, in this graph, you can see the discount factor, and you can see how it changes through training. The blue line corresponds to the main head. So this is the head that actually acts in the environment. And the other 2 lines correspond to the auxiliary tasks. So one interesting thing to note is that the main head really behaves differently than the 2 auxiliary tasks. So for example, they learn different discount factors. And this gives the agent the possibility to understand about different horizons in a single environment. The second thing that we noticed was that if you look at the leaky v-trace parameters, then the main head really prefers to use v-trace at the beginning, but it tunes to doing important sampling towards the end of training. And we have the curves for all of the games in the supplementary of the paper. Another interesting thing that we found was the discovery of contraction. So just to give a quick reminder, to have contraction in the algorithm, we need this rho bar contraction coefficient to be larger than the C bar. So what we did in this experiment was not to enforce this rule, but to see if the meta gradient can discover it by itself. And basically what you can see on the right is that in 3 domains in this case, the blue line is larger than the orange line in 99% of the time. So it really means that because the algorithm wants to discover contraction, contraction is useful for learning, it also discovers it, which was interesting. So to summarize this part of the talk, StackX is general. It can self-tune all of the differentiable hyperparameters in a single lifetime. It uses a single update rule to do it. It can richly hyperparameterize the model using auxiliary tasks or combining different off-policy algorithms. It improves the performance as we self-tuned more. It's very simple. You can see the compute runtime here. It really doesn't take much compute. And some of the stuff that we did after it was to extend, this agent is completely online, so it's super fast, but we can also add replay to it and do some off-policy learning, and then we got a median score of around 500, which is the second best reported score in Atari. We also got bigger gains in DM control from using replay. We tested it on more agent and algorithms, so it generalizes across algorithms. And one thing that didn't work is that we tried a version where the auxiliary policies are also allowed to to act, but it didn't perform well. How much time do I have? Is there anyone here?
Yeah, about a few minutes.
Okay, so let me try to cover very quickly one more work. So this work is about discovery of options. So basically, options are a way to learn temporal structure in reinforcement learning. An option is typically defined by a tuple, where there is an initialization set, an option policy, and a termination condition. And if you want to learn more about these options, and there's this seminal paper by Rich, Doina, and Satinder. Let me try to go a little bit quicker. Okay, so in DeepRL, we know that if we have a good set of options, then we get easier learning. And the first paper to show this was the Minecraft paper that Chen Tesler did, where we basically pre-tuned options, and we showed that we can learn very good with them once they're pre-tuned. And the other approaches take the opposite approach. So they initialize a very good policy over the options, and then they show that it's easier to discover options. But what didn't work so well in the community so far was to discover options while learning. So people tried unsupervised methods and tried to do it end-to-end, but we usually see that this type of methods is being outperformed by flat policies, or not HRL policies. So the hypothesis that we took in this work was that structure will emerge for the right combination of environment, architecture, and algorithm. So what we mean by that is that if the environment is going to require usability, then there is a reason for options to emerge. If our architecture will allow the agent to capture temporal structure, then there is a possibility to learn it. And the meta-gradient algorithm will allow us to achieve that. So what we basically propose here is a manager that picks options. Once it picks an option, it executes it until it terminates. And the learning is performed in the following way. The option policies try to maximize some cumulants, rewards, basically, and they have terminations. The manager's policy is the HRL policy that controls them, and it tries to maximize the task reward. And we use meta-gradients to learn the cumulants of the terminations for the options. So basically, we learn sub-goals, and these sub-goals are used to learn the options. So these are now the meta-parameters. They are not hyperparameters anymore. They are neural networks that model the cumulants and the terminations for the options. How it looks is that the manager gets the state information and the goal information, and the options only get the state information, and they output a probability over the primitive actions. And then the manager selects between options and primitive actions. Here, the meta parameters are the cumulants and the termination options, and we use this meta gradient to learn them. And I won't go over the details of the exact calculation because we are short in time. But let's look at the experimental setup. So the main questions that we wanted to ask is, does the discovered options transfer to new tasks? So what we did here is that we took an environment, we sampled random tasks in this environment, and we learned options that are useful across many of these tasks. And when we test the agent, we basically take a new agent, we initialize the agent, we fix the parameters of the options, and we let the manager to learn how to control these options, but we do not do any meta gradients at this time. So here is one example where the training tasks are sampled in 3 rooms and the test tasks are in the 4th room. And what you can see is a comparison between MODAC, which is our approach, and 3 other approaches like a flat policy and two other policies. So what you see is basically that when this agent is using our options, it can learn faster in a test environment because these options capture something about the dynamics of the environment. Another thing that we tested was if these options are really used by the agent. So here you can see the usability of the options in red and the usability of the primitive actions in blue. So this result is very similar to what we saw in the Minecraft paper a few years ago. And basically what we see is that once the agent starts to get high reward, it prefers to take primitive actions. So it learns to refine over the imperfect options. But at the beginning, these options really help the agent to explore and to find good rewards. Let me skip this one. Here you can see the execution of the options. So different segments correspond to different options that were executed by the agent when it tries to reach a goal. So you can see that it's not perfect, like it's taking a large circuit in this case, but it does switch a lot between options, and these options look like as if they make sense. In the test case, it looks actually quite better. Another thing is a visualization of the option policies. So here you can see there's the agent and the goal state, and each one of these policies can take it to the goal, but not necessarily in the short way, because these options need to be good across any environment. But then if you take a look back at what this HRL agent is doing, so it really learns how to combine these options very efficiently. Okay. The last experiment we did was in Atari. In this case, we pre-trained options to do feature control, and we got some nice improvements in most of the games from pre-training, pre-learning these options. Cool. So I'll finish now, and I'll leave time for questions. I won't cover the last part.
Okay, תודה רבה. So does anyone have any questions? Okay, so I have one. So in the first part, you were saying that you're also optimizing the learning rates, maybe, or because I didn't see it in the slides. So how do you keep the system stable? Because if the learning rate becomes too high, for instance, then maybe the agent won't learn at all. So do you have any strategy for that?
Yeah. So we don't tune the learning rate itself. We train these loss coefficients that are almost equivalent to learning rates because they control the magnitude of the update for each one of the loss components.
And they're not bounded? They're not bounded by some?
And we use gradient clipping. So the gradient clipping is actually what makes the entire update bounded. So when we analyzed what happens is basically that because we have some gradient clipping on the norm of the gradient, the agent basically tries to balance how much magnitude it puts on each one of the loss components, but everything remains bounded. So that's how we basically balance it.
Okay, see, we have another question.
In the chat?
No, from Roy.
Hi, thanks for the talk, very, very interesting. I have a practical question about this part, the first part. You show really great improvement over the Impala and HPC methods in terms of steps, accumulated steps. But then on one of the first slides, you told something like adding meta learning adds like 30% more compute time. So compare wall clock time. My question is, did you compare it, and do you still see the same gains or considerable gains in wall clock time?
Yeah, so we can try to do it now. So if this blue line is 360 and this one is 240 and it uses 30% more compute, I think it's still slightly better, but I'm not sure if it's the most important question, because in many cases we care more about sample efficiencies and compute efficiency. So, if you compare this agent, for example, to DQN, so DQN requires 8 times more compute because it uses experience replay. If you look at SOTA agents like mu0, so mu0 is doing search, which is also compute heavy. So if you only care about compute, I think that the gains that we show here would be less significant, but I think it will still be better to use metagradients. But the more interesting question is about sample efficiency.
I think it boils down to whether the compute goes mostly for the RL part or the simulation. If the simulation is very heavy, you really care about steps, environmental steps. But if the simulation is very cheap, then you spend the majority or this considerable amount of the time computing gradients.
Yeah, I agree. It depends on the application. I'm just pointing out that there are many applications where we care more about sample efficiencies and compute.
Yeah. Thanks.
Okay, so any more questions? Okay, so thanks, Tom. Great talk. נחליף לעברית עכשיו. אז תודה שהשתתפתם ב-RL Day הישראלי הראשון. תודה לכל הדוברים, ואנחנו נשמח לראות אתכם שוב שנה הבאה, אם יקרה. תודה.
ביי, תודה על הזמנה.
ביי.